Welcome to the 2021 XSEDE Summer Boot Camp. This is, I think, the most intense but most rewarding event that we do all year. This is brought to you by XSEDE, which is an NSF organization that exists to bring you computing resources. Resources not only like this training, but also like the computational platforms and the software that we'll use this week. So if you find this to be a useful event or useful software, useful platforms and whatnot, I hope you'll feel free to take more advantage of XSEDE. I'm John Urbanek. I'm a parallel computing scientist here at the Pittsburgh Supercomputing Center. I spend my time parallelizing codes with the kind of techniques that we're going to talk about this week. These days, that also includes a lot of big data and machine learning, which is also part of the world of parallel computing. And this is one of our series of workshops. We've just posted our calendar for the rest of the year. So we'll have something that looks fairly similar to last year's calendar as we go through the events. But the boot camp, as I've said, is by far the most intense. It's the only really week-long event that we do. So welcome. Our philosophy with all of these workshops is that they're only as long as they should be. So we don't have to pad things out. We're not flying you in here and we don't feel the need to fill the time. And so it's going to be very intense and packed this week, but only with stuff that I think is really important to learn and relevant to the topics at hand. There will be plenty of hands-on exercise time because this is not a just talking head jargon workshop. This is kind of workshop that you should leave here being able to use these techniques. People typically leave our workshops and are able to go back and apply them to their own research codes immediately. That's our objective here. So the schedule is not padded, it's intense. This is going to be a really packed week, but you're going to leave here with a tremendous amount of content. Most of the guts of what would really be a semester-long course in concurrent or parallel computing or something like that. I recognize that you have real lives and we're working in many different time zones here and your lives don't come to a halt. So again, we're going to try to keep to our schedule as closely as possible here, start and stop time, so that you can work your life around this appropriately. Learning is also a social process. This is something we've come to appreciate as we put these together. So this is not just a MOOC, one of those online courses where I'm just a talking head, just spewing stuff at you, for days on end. Instead, this is meant to be very interactive. And so I hope that you'll take advantage of it. It's not our normal wide area classroom that we do in pre-COVID times with satellite sites. And so if you don't have the luxury of students sitting next to you, which is what we prefer, but this has been working pretty well for the past year, so please bear with us as we go through this. The agenda is going to have a lot of different topics, but I think by the time we're done, you'll see that they all really tie together. There is a theme here, things build, so it is important that you kind of don't jump around too much because it's foundational and things do relate and chain one to the next. As we go through this stuff, we're going to stick to the agenda as closely as possible. Sometimes talks will run a little bit long, typically because of questions, and questions are very welcome. So we have a lot of questions coming in and things go a little bit long. We'll push back. If we think go a little bit short and we gain some time, we'll take advantage of that. But on average, we should stay pretty close to this schedule. The one exception being today, the first day. The first day is unusually packed just because of the way the topics break down, in particular because the intro to parallel computing is the one kind of overview talk we give where we do introduce a lot of technology or terminology and jargon and whatnot that we're going to use the rest of the week. So we're really cramming a whole lot into this intro to parallel computing to prep you for the more hands-on stuff that's going to follow, most immediately the intro to OpenMP. So today is going to be really, really packed. As a matter of fact, if today spills over a little bit into tomorrow even, that's going to be just fine because tomorrow is going to be probably the lightest day because we cover so much of tomorrow's material today. One of the things I think you'll find outright delightful about this is that an awful lot of what you're going to learn today with, say, OpenMP is going to apply tomorrow to OpenACC with GPU programming. The two are very related. So you learn an awful lot with just learning how to program multi-core CPUs, regular old CPUs, that will apply to tomorrow. It's going to save us a lot of time there. So of our agenda, today is going to be the most packed day. Tomorrow is going to be the most mellow day. We might bump a little bit of material into tomorrow if that happens. And then Thursday and Friday are going to be mostly themed about MPI, which is the kind of the queen of parallel programming approaches. And it's how we're going to teach you how to scale things up to run on tens of thousands, or these days, potentially millions of cores. And you will leave here with the ability to program million core machines like the Exascale machines that are becoming available this year. And that'll be Thursday and Friday. And at the end of Friday, we're going to tie all that stuff together and how you can mix and match these techniques, because they are designed to do exactly that with our hybrid computing. That is one of the benefits, the unique benefits of this boot camp, is that all of these parallel programming techniques are designed to work well with each other. However, normally we don't have the luxury of discussing that at all, because if we have a course on GPU programming, for example, I can't assume that anybody knows MPI and knows how to connect GPUs together. So we can't really have a serious discussion about how to do that stuff. Or, if we talk about MPI, I can't really assume you know how to use GPUs. Well, with the summer boot camp here, it's the one time all year where by the time we get to Friday, I know that you do know how to use GPUs. You know how to use the cores on a CPU, and you know how to tie them all together with MPI. And so we can have a really great discussion about how to use them all together, which is important in this age for reasons that we'll talk about very shortly. So this is, for me, it's always a treat to be able to talk about that to a non-expert audience. The only other time I can really talk about how to use these things together is when I'm talking to a bunch of people that have a lot of years of expertise. And you will have the ability to have a meaningful discussion about that by the time we get to Friday. Okay, so that's our agenda. And so as we work our way through it, you have a number of resources available to you, because this is a very hands-on event, including our TAs. So our TAs will be monitoring the chat channel there. You'll see them answering questions. Tom and TJ and Steve will chime in and out. And so please take advantage of them. If you send me questions, I answer questions too live as we go along. So please post your questions there. Please don't post them private though, so that people can see the questions you're asking. Sometimes people will send me the questions privately, and I'm trying to answer questions for everybody. So if your question is interesting, don't send it to me privately, so everybody can see the chat and the question that we're discussing. But at any rate, the chat channel will be it turned out to be a very effective way for us to answer questions as we go along. So please do ask those questions. What I will try to do is take a pause every now and again to catch up with the questions, because we'll be in the midst of a topic and everything, and I'll get absorbed into it. I won't want to digress too much, and then I'll take a pause and answer a bunch of your questions. So that'll kind of be the rhythm that we'll get in throughout the week. And then we'll have exercise sessions and hands-on sessions and Q&A sessions, where that'll be pretty much our focus. We'll just be picking off your questions as they come in. So when we get to the hands-on sessions and you ask questions, we'll be right on top of those in real time. The talks are posted online if you haven't found them already, and that's a very useful resource. As we do the hands-on exercises, you'll want to refer back to the online talks for content. There's a lot of code in the things that we're doing this week. Again, it's a very hands-on workshop. And if you're going to cut and paste the code, I suggest that you don't do it from the actual PDFs, because they're prone to too many mistranslations when you cut and paste code. Instead, we'll have online versions from your accounts that you'll be able to cut and paste code from much more easily and reliably. So that's my suggestion. The YouTube channel is also out there, XSEDE Training, and that's where we post events, including this one eventually. And you can refer to that for previous versions of the events. And again, this one will appear there eventually. The platform that we're going to be using all week is Bridges here at the Pittsburgh Supercomputing Center. And it is one of the platforms in the constellation that XSEDE supports for your research purposes. Again, everything's free. I can't emphasize that enough, that the platforms exist to provide free computing resources to researchers. And so you do not have to pay money to use them. You just apply via this process right here, and you get access to these platforms. So please, if you're interested or find yourself finding this useful, go ahead and look at the allocation process. In particular, a startup grant, which gives you 50,000 core hours, is an extremely trivial process to apply for. And so it takes like 20 minutes to apply and get 50,000 core hours that you can use for the rest of the year. Otherwise, you'll have the accounts that we've set up for this workshop, and they'll be good for the next couple of weeks for you to use to do exercises after the workshop is done. We have a code of conduct for all of our XSEDE events. And so you can see the full code of conduct posted as here. And there are organizers and ombudsmen for you to contact. So please feel free to contact any of the ombudspersons listed here. And if you have any concerns whatsoever. Likewise, the XSEDE has a very active terminology board that, in line with their code of conduct, exists to make sure that our terminology does not provoke offensive terminology, is inclusive. And so please, if you have any concerns about the terminology that we use here this week, don't hesitate to contact them with your concerns or suggestions. And the last thing we'll talk about before we jump into some real material here is that there is a post-event survey that you will be mailed to let us know how useful this was to you. And I really hope that you do respond to that, because we take the surveys very seriously. If you find this week to be useful, it is because previous people who have taken events here have answered and shaped the form of this one with the feedback that we get from that survey. And we really do pay attention to it. I read every single written comment. There's written comment boxes on those surveys. And if you write comment in there and go into detail about what you thought was useful or what wasn't useful, we pay attention to it. So please, give us your feedback. Okay, with that, I'll take a pause here. Questions, and already Tom is on top of questions here, so I won't. There's nothing for me to pick off there. We're going to jump into our first bit of content here, which is the computing environment. Now, the computing environment we're going to use all week will be one single machine, one environment. It's very friendly, and it is I think going to take no time at all for you to get up to speed in using it. And our goal here is that everything we teach you this week is open source, open standards. MPI, OpenACC, OpenMP. These are all standards. And they are not only just standards on paper. In reality, they are very well supported portable standards you're going to find apply to any compiler you're going to be working on that's serious these days, be it from Microsoft or Intel or PGI or GNU or Clang. They all support the stuff we're going to be doing this week. And all the code that you're going to learn this week, you could take and put on your laptop with any of those compilers, and it will run byte for byte. So my goal is to do everything in a very platform independent, portable way. However, we are going to use one particular platform for the exercises. And the reason for that is that we don't want you to have to worry about installing the software, although it's open source and you can install it. We don't want to have to worry about, if you've got a bug, how does it show up in your particular environment? Instead, we're all going to be working in the same environment. So it is very helpful for us with hundreds of people to have, one unified environment that we're all sharing and we're all on the same page. But it is not my objective to teach you any more about any particular computing platform, including bridges, than necessary. So we're not going to spend a lot of time learning about bridges in particular, because you're not going to have to learn a lot about bridges in particular. Everything we're going to do this week is very, very portable. But you're going to need to know a little bit about bridges in particular, and we're going to cover it all in the next 5 minutes here because it is the platform we're going to use. So bridges is a supercomputer in the XSEDE constellation. It's mostly for big data and data analytics, although it runs all different kinds of sciences. There are thousands of projects that are running away on it. It's very straightforward for us to connect to. You should already have received some email instructions on how to do this when you registered, and you should probably already have set your initial password. If you haven't, go to apr.psc.edu and set a password. And then we're going to be spending all of our time working on bridges2.psc.edu, and you can get to there with any terminal client. So you probably have one built into whatever laptop or workstation you're sitting in front of right now. PuTTY is a very popular free one, for example. Whatever it takes for you to just be able to SSH to the machine is all you're going to need to connect up this week. When you connect to the machine, you're going to find yourself on a login node. Now, login node, as the name implies, is really only for logging in. You don't want to try to run code there or compute there. The login node is shared by everybody to connect to the machine. If you do, you'll get a little bit confused. Things won't run right. It might outright tell you you can't do that here. But at any rate, we're going to actually want to connect to a compute node to do all of our computing. And the compute nodes, as the name suggests, are for computing, and they're easy to connect to on bridges. There are different ways to connect to the different resources on bridges. It's got a lot of different pieces on the machine. It's got GPU nodes, it's got large memory nodes, it's got regular memory nodes, it's got all these pieces that we don't want to bother you with the details of. So instead, the way we'll access them this week is just simply using the interact command that says, give me an interactive shell on one of the compute nodes. And so, for example, later on we start doing exercises, you'll type interact-n8 to say, give me 8 cores of bridges, and it will come back and you'll have 8 cores. And the main way for you to tell, or an obvious way for you to tell that you're on a compute node instead of login node, is that your command prompt will change from one of these login nodes to one of these compute nodes. So we've gone from login node 11 here, which is what you connected to when you SSH in. And then when it's time to do the exercises or do anything really, you get on your own compute node. This is a regular memory compute node, number 590 here, for example. And so this is the standard pattern this week, is when you log into the machine. So if you go away for lunch break or overnight or whatever, and you come back, log into the machine, and then get on a compute node before you try to do anything. And so again, it's easy to, to forget to do this step and things won't work quite right. So if you find yourself things behaving a little oddly, or it's telling you can't do something, you go, oh, geez, I'm on a compute node, and make sure you ask for interactive node. And it'll take a second when you type interact to find you a free interactive node, but not long. Okay. We're going to be doing lots of coding this week. That's the theme of this workshop. It's hands-on. It's not just buzzwords. And so you're going to need an editor. And for those of you that are familiar with Unix or Linux type environments, you might already be using Emacs or VI as your editor, and they are of course there. For those of you that aren't used to those type of environments, fear not. I'm not making that assumption this week at all. And so there is an editor, for example, for you to use that's very friendly. It's got simple little menus there. It's going to be more than sufficient for everything we're going to do this week, called Nano. So if you're not an Emacs or VI person, just use Nano and you're going to be fine with everything we're going to do. I'm going to give you a chance to try this out. You don't have to test anything out. We're going to take a few minutes as soon as I'm done talking here and make sure everything works for everybody. So that'll be our first kind of exercise session here. We'll make sure everything's working in a moment. Compiling on the machine, we're going to do everything with standard Fortran and C compilers. Those will be our two languages here that we're going to use this week because those are the two standard languages of high performance computing, Fortran and C. And so C++ people will be fine working with the straight C stuff. Those of you that are mostly coming from other backgrounds, Java or Python or whatnot, I've tried to not get fancy. I'm not trying to impress you with how clever I can be with the code. So I hope if you're pretty much new to C or Fortran, or you'll be able to follow along pretty well. But that will be what we're programming in, and we're going to use very standard compilers this week. And so the compiler we're going to settle on for just by default will be the NVIDIA compiler. And the reason I've mostly chosen that is that we have multiple choices on bridges. We could use Intel compilers or GNU compilers or the AMD Clang compilers. So we have lots of choices, but I picked the NVIDIA ones just for us to use because that'll work best for the portion of the agenda that's GPU computing. No surprise that NVIDIA's compilers are the best for GPU computing, right? And so we'll use the NVIDIA compilers for everything so we don't have to switch back and forth. But it is very easy to switch back and forth on bridges between compilers. And so if you really are a hardcore Intel person, for example, you could load the Intel compilers and use those for the exercises instead. And on bridges, the way we do that is with the modules commands. That allows us to load different software packages. And so the only module we'll need for all week actually is this one right here. It's the OpenMP, so this is the MPI version that loads the NVIDIA compiler. So I'm going to put this command in your startup script. It'll automatically be running for all of us, but this is all you would actually need to select the compiler we're going to use for the entire week. You might find it helpful to have a couple of windows open onto bridges at a time, one for compiling and running and one for editing. That's a common thing to do. A lot of people like to work that way. They'll open a window where they can edit the code, and then in their other window, they can compile it and go, syntax error on line 13, and they go back to the other window and just fix line 13. And that way, they're not starting and stopping the editor all the time. And if you like to do that, feel free to do that. We're going to find that all of our exercises are going to be in one directory, and it's going to be in your home directory once we get things set up here in the next slide. And you'll find in there some subdirectories for the different things we're going to go through this week. We'll have a little test one in there that we're about to try right now to make sure everything works. We'll have the OpenMP directory that is going to be where we're going to start today. And it has within it different sample codes and source codes that we're going to use to start for things, and solution folders. So there's lots of solutions for things we're going to do this week. So you can cheat at any point in time and spoil things for yourself. I suggest you don't and wait until we actually cover the solutions. But at any rate, you'll find this kind of theme throughout the folders that we have here. And we have an OpenACC folder if we get on the GPU computing, and an MPI folder. We'll be roaming around in there when we get onto the MPI topics. So it's pretty straightforward. Now we're going to take a moment and make sure everything works for everybody. In the event that things don't work, it'll be okay, because our first exercise session isn't until the other end of our intro to parallel computing. And so this will give us lots of time to fix any problems if you have any, without us panicking right now. So we're going to take, let's say 10 minutes, and we're going to step through these. So what you're going to do is you're going to log on. We just talked about all these things. Log on to bridges. You're going to run, and we didn't talk about this though. You're going to run to set everything up this week. You're going to run a setup script, and it'll set up everything for the rest of the week. And so what you want to type is tilde training, and capitalization is important when you're working in a Unix type shell. So tilde training / capital S for the setup. And if you run this script, it will go and it will copy over the exercises folders and set up your bash RC. That's the startup script that every time you log into to the machine, so that everything will work for the rest of the week. It'll also tell you to log out and log back in again to make sure everything takes effect. And so do that. Then when you're logged back in, you can go ahead and grab some compute nodes with this interact-n8. That's asking for 8 nodes, 8 cores, for example. Go ahead and edit a file using one of the editors, and then make sure the compiler works right. You can go into the test directory that's sitting there. You can compile that test program that's there, either the Fortran or the C1, whichever one you prefer. And again, we'll have both tracks kind of all week. And then you can run the resulting executable. The compilers, if you don't tell them what to name the executable, by default, they spit out something called a.out. So after you compile something, you'll see sitting there executable, a.out. So if you just type a.out, it'll run, and that program does nothing more than say congratulations, but it means pretty much the environment's set up and good for you. So go ahead and give this a shot, and we'll also give this a use this as our first example of how an exercise session will run. And the way an exercise session will run is you work away. I will sit here largely quiet unless there's a question of general interest that I should bring to everybody's attention while you work on the exercises. And I will pick off the questions that are pending as well. So I'll see if there are any here that Tom, you haven't already caught up with. Nope, it looks like we're all caught up on questions. So go ahead and get on this. And if I jump back in to answer a general question, you can choose to ignore me if you don't care about that question. I'll help Tom out here. I'm picking off some of these questions here. Let's see. If you don't have an exercises directory, it means you didn't run the setup script yet, because that's what will create the exercises directory for you. If you ran on a compute node instead of a login node, if you follow these instructions, it's all the same. It'll work just fine. The compute nodes and all the login nodes, they all share the same directories. So you don't have to worry about if you're moving back and forth between them. Where are my files? They all share a shared file structure. And so in this case, if you ran the setup script on the login node or the compute node, the end effect's going to be exactly the same. Command to log out is log out or exit or Control-D, commonly used. How do you go back to the login node from a compute node? Well, you'll notice that when you type interact and it puts you on a compute node, when you log out of the compute node, you'll find yourself back on the login node. So it's kind of inception there. You go from connect to the login node, connect to the compute node. You log out of the compute node, you'll find yourself back on the login node. Your old bash RC. So for those of you that have existing bash RCs, when you run the setup script, it will copy your existing one to a bash rc.back. So yeah, for those of you that have your existing environment set up like you prefer them, it's not lost, it's the .back, and when the workshop's done, it is up to you to copy it back over, and your environment will be restored. Default time limit for the compute node reservation. Okay, that's, in other words, interact is actually setting up, for those of you that realize that you're working on a system with reservations and a scheduler and whatnot, interact is actually asking for a slice of time as well as a number of cores. By default, interact is normally set to 60 minutes, I believe, but for the workshop, I think we've set it up to a number of hours, like 4 or 5, something that shouldn't bother you. It should be through the rest of the schedule for the day, so it's pretty long. But after the workshop's over, if you type interact and you want to stay on for more than an hour, you should also use the -t command to ask for a longer amount of time. But we won't, again, we're trying to keep things simple for this week. But interact has, if you type interact-help, you can see it has a bunch of different options associated with it that you can use. It is possible to set up passwordless authentication with SSH, but we are not going to get into that because that requires a lot of details. If you care about that kind of stuff, you are welcome to visit the Bridges user guide at psc.edu. You'll see a Bridges user guide there, and it has very detailed, straightforward instructions on how to set up SSH authentication there. But we don't want to get into supporting the many minor but non-trivial issues that can show up when you're doing that. We're using C and Fortran because of NVIDIA support, because the only language used in HPC. Okay, well, I'll take a second. We'll come back to this topic as we go through things this week. It has nothing to do with NVIDIA in particular. We're using this compiler, this NVIDIA compiler, just because it works pretty well with GPUs, but other compilers do as well. The reason we're using C and Fortran, those are the official languages of HPC in the sense that the standards, all the ones we're talking about this week, MPI and OpenMP and OpenACC support those. If you go to the manuals, the official user guides and documents and specification, most importantly for the things we're going to talk about this week, you'll see that those are the two languages that they are written with in mind, that they are by default compatible with. And so that's the main reason we're using these two, because they are the official languages kind of high performance computing anywhere. Now the reasons that other languages, but other languages have lots of interoperability with the things we're going to talk about. They're just not the official ones that are tied to the specification, but it will vary between them. So for example, MPI works with many, has bindings to many other languages, like lots of Java code is written with MPI. But Python is an interpreted language. So with Python, it needs a special kind of version. So Python has MPI for Pi, which is a project that some guy has, kind of supported for a number of years now to give wrappers to support MPI with Python. But that's just some guy's, private project to do that. It's not part of the official specification. And so it's usually not up to date with the latest, greatest changes and whatnot and implementations. And so I'll talk about individually when we get into different specifications, how well they interoperate with other languages. But if you're going to be in the world of high performance computing, you will find that everything always works with Fortran and C, and then by extension, C++ in a pretty non-trivial way, in a pretty trivial way, I should say. But by default, everything works with Fortran and C. Those are the languages of high performance computing, and because they have compilers, which are high performance. And then because these things become important, they propagate out and they work with lots of other different languages and approaches, but they're not the officially supported ones. And so the support and the compatibility and the performance vary very much. But we can talk about those specifically, and I'm glad to answer questions about them as we get into the particulars, as we talk about one thing or another. I'll be glad to digress and talk about support for something that you're particularly concerned with. Let's see. What's the difference between NV Fortran and G Fortran? Well, NV Fortran is just the name of the NVIDIA Fortran compiler. G Fortran is the name for a GNU Fortran compiler. And so every piece of code we're going to do right here this week will work fine amongst, you can port them between any of those. And for those of you that don't believe me or want to try it out, you could load other modules. We won't, I shouldn't open that can of worms, but you could load other modules and try them with other compilers, and you'll find out the things we're going to do are compatible across other compilers. Why didn't NVC test.c prompt to load the NVC module? Well, first of all, the setup script makes sure the module's already loaded. Second of all, if you don't have a module loaded and you try to use software, it will just say command not found. It won't prompt you, it won't know what the module is. So you need to load the software modules before you use the commands. Otherwise, things will just say command not found. But in this case, the setup script makes sure that the module that we're going to use all week, that OpenMPI module, is already loaded. The C++ work with OpenMP, OpenACC? Yes, it does, very much so. We'll have some examples about it. We'll be mostly using straight C just to keep, because we have limited time. We want to keep things as understandable as for everybody as possible. But C++, actual bona fide C++ works well with OpenMP and OpenACC. Like, you can use objects, for example. Well, but when we get to those, we can dive into that in more detail. Let's see. Yes, Fortran is still very relevant in the HPC world. Modern versions of Fortran, not the version that you learned in the 80s at all, but modern versions of Fortran are still very relevant in high performance computing. As you'll see from our examples, Fortran still has by default the best performance of any language, and there are reasons for that we can get into. How to save and get out of VI. Yeah. Welcome to the user friendliness of VI. You can start it up a lot easier than you can even figure out how to quit. VI is not user friendly in the least. It has an incredibly steep learning curve. So please don't try to use VI for the first time right now. Just use Nano. It is a steep learning curve. It is nice when you know how to use it, but it is not something to just start using this week spontaneously. How do you edit a file in Nano? I think you'll find it very straightforward. Cursor keys, and there's a little menu at the bottom of the screen to tell you how to save and whatnot. So you should find Nano pretty straightforward. Julia compared to Fortran performance? That's an interesting question. I think Julia is the only contender these days to replace Fortran in performance-sensitive environments. I don't want to take a digression here. Save that question for one of the Q&A sessions when we have more open-ended time to answer things, and we'll come back to it. Screen. You can use sessions if you're familiar with that. Go ahead and use sessions. The goal of these preliminary exercises is to make sure everything works right now, because when we do the hands-on exercises next, I don't want to waste time with people's, password problems or account problems or anything else. That's the whole reason we're getting this boring stuff out of the way right now. We're going to jump into the next exercise session. It is going to be exercises, real interesting content. So this is boring, awful stuff to worry about right now, and we're getting it all out of the way for the rest of the week. And for matter of fact, we're going to move on right now. And so any of you that are still dealing with any account problems, we still have time before we get to that first exercise session to sort it out in the background. But it looks like people are doing pretty well. So we are going to move on from this. And again, any of you that do have any issues, there's plenty of time before we do the first real exercise session, which I guarantee will be much more interesting than this. But before we get there, we do have to do the one, I shouldn't say have to, because I hope you find it to be interesting material. We do have to do the kind of an overview of all the stuff we're going to dive into, because before we dive right into the trenches, I'd like to give you some orientation on how these things are going to fit together. And we're going to use a number of different software approaches this week, and they all make sense if you know what they're trying to accomplish and the kind of hardware that they're meant to deal with. The choices aren't arbitrary, and so it makes things hang together and make a lot of sense if we kind of give you a little bit of an overview first before we dive into the details. And so that's what this is. This is kind of an overview of the landscape. Now, at the very end of the week, we'll have an outro to parallel computing talk, because at that point, you will know how to do all these different parallel programming approaches for real. And so we can come back and revisit a few of these topics and tie them together at the end. But by then, a lot of it will make sense. That talks a lot less information than this one. So the idea here is that you're going to walk away being a hands-on real user of these things. And so before we get into that real hands-on user exercise kind of stuff, let's give you some idea of where this comes from. Now, a lot of you are coming here with applications of your own that you're interested in accelerating. You need them to speed up by a factor of 2 or 10 or 10,000. And all those are reasonable things to do with this modern parallel computing. And so you've got an application in mind. You don't need me to give you a big list of applications. And I could go on for hours about applications that I've personally worked on myself over the past couple of decades. But we could go on for hours about just applications that are running on bridges right now. So I'm not here to give you an exhaustive list of the kind of things that happen in high performance computing, because it's endless. It's pretty much any area of modern science today has some simulation component. And anything that's being simulated, the people that are doing the leading edge simulations, that are doing the publishing leading edge work, are using supercomputers, scalable computing to do that work. But I'll give you just a couple so that we can have some touchstones as we come back and talk about things. One that I'll come back to a lot is going to be weather simulation and modeling, because it's something everybody can understand. So when we start doing our first exercises, I'll refer a little bit to some weather simulation. But the big, grandest weather simulation thing going on today, and one that's very important, is climate change analysis, for example. So if you're doing climate modeling today, it's almost all computationally driven analysis. And climate modeling is like trying to do meteorology, trying to do weather prediction, except instead of trying to do it for the next 3 days, you're trying to do it for the next 3 decades. And instead of trying to do it for your neighborhood, you're trying to do it for the entire globe. So you can imagine how computationally intensive it is. We can't have enough computing power. And so these are very important applications that are going to run on the latest Exascale machines. I'll define what those are. What's an Exascale machine? We'll get to it in a moment, but it's the biggest, fastest machines in the world. Climate change analysis is an important project that runs on them. Now, it's not only things that are huge in some physical simulation sense, it's also lots of things in this world exist at a small scale, but still computationally, they're enormous in terms of what you're trying to compute. Combustion simulation is a good example of that, where you might only be trying to do a model that's the size of a power plant turbine, or maybe even a piston in an engine. And yet the simulation for it, because it's turbulent fluid flow, it's got multi-physics going on, you've got chemistry and thermodynamics, and fluid dynamics, all this stuff going on in a turbulent, chaotic way, it's the kind of problem that can challenge, again, even the largest supercomputers with millions of cores. It's a challenge to run just one turbine simulation. And so these are the kind of basic everyday problems that challenge the biggest machines. Last one I'll talk about here, just to give you an idea of different kind of direction. The world is not just fluid dynamics. It's also, very, very diverse applications. Again, I could go on for hours, but here's one that's in a different direction, which is human brain simulation, or brain simulation in general, which over the years has gone from being able to simulate a mouse, with its millions of neurons and billions of synapses, up to human brain, which the latest Exascale computers hope to simulate in real time with billions of neurons and trillions of synapses. And so this is kind of the march of supercomputing, and this is all reliant upon the kind of techniques we're going to learn this week. Now, that's all I'm going to talk about. I have in the outro to parallel computing talk, I do have an appendix of a lot more applications just to kind of stimulate you, or maybe to stimulate some conversation as we get to that point at the end of the week where you have a lot of these techniques in hand, and we can talk about how they apply to particular applications. We'll be talking along the way. A lot of you will raise concerns about your own applications, and I'll talk about lots of applications as they become relevant throughout the week. So I'm not going to go on my endless lecture about these, although I personally find it very, very interesting and enlightening how many diverse different areas of science have become dependent upon simulation to really drive them these days. Instead, we're going to take a step back and talk about hardware for a little bit, because this is what's really shaped modern computing. And maybe the most important phenomena in modern computing, and by modern, I mean the trend over the past 20 to 30 years, has been the fact that serial computing, writing just standard serial, writing some Python script and just running it, and hoping that next year it runs faster, computer equipment is faster, that notion is dead. For a long time, it was actually a very fair idea to say, hey, if I write a computer code in a couple of years, it's going to run twice as fast. At the end of the decade, it's going to run 100 times faster if I don't do anything, because computers are just getting better and better. And that was true for many, many decades. This graph only goes from the early 90s, but we could extrapolate this back all the way to the mid 40s, to the beginning of digital computing. It was true that every couple of years, computing speeds doubled. And that remained true for decades and decades and decades. And now all of a sudden we find ourselves in an era where that's not true anymore at all. As a matter of fact, from about 2004 on, things have really plateaued a good bit. We're already very far behind where we'd be if things hadn't plateaued. Why is this? Well, we're going to understand exactly why this is, but this has huge implications. These days, if you want to have a code that's going to run any faster than it is now, in any short amount of time, it's because you're going to go parallel. You're going to use parallel computing, not because the computers next year are just going to be faster. Okay, now is this because Moore's law has abandoned us? Now, what is Moore's law? Everybody, probably all of you have heard the term at least. Many of you have probably used it. Many of you have probably misused it. Moore's law has become some kind of thing that gets applied to any technology that has kind of geometrical improvements in it. But Moore's law is a very specific thing that Gordon Moore came up with in the mid-60s, where he observed that integrated circuits, which were very new at the time, they were able to double the number of transistors that they could put in a given area of an integrated circuit every 18 months or 2 years or so. And so he made a prediction that that was going to continue for a while. Now, neither he nor anybody else dreamed that 40, 50 years later that would still remain true, and yet it has. So Moore's law has remained true for decades and decades, although it finally, at long last, is kind of hitting the end of the road. People predicted it would happen a lot sooner, and the engineers, through heroic efforts and many, many changes of fabrication technologies, kept things moving. But we finally hit the wall where things are kind of starting to run out of steam. And as a matter of fact, these numbers that they use for feature size these days are kind of outright lies, as a matter of fact. They don't really even mean anything like they used to. They used to tell you how, kind of the pitch size, the smallest feature that you could find in a great circuit. Nowadays, it doesn't mean anything like that. But at any rate, Moore's law has continued until about nowish. It's starting to peter out, but it really, did deliver for a long time. Well past this 2004, where things kind of slowed down a whole lot. So it's not Moore's law. It's not that the engineers failed us in making smaller and more dense electronics. As a matter of fact, you can see that if you look at the number of transistors in modern computer chips. They've continued to cram more and more transistors. So modern chips now have billions and billions of transistors. So this trend has continued. So the engineers have delivered the transistors. What happened instead is this. And these are probably, this slide right here is probably the most important slide of the entire week if you really want to understand what's going on in computing and where things are headed in the future. as simple as it has the most important information in modern computer architecture design. And that shows us why the clock rates of modern computers have plateaued over here. So on the right-hand side, we've got clock rates of just a bunch of different common important processors. And we can see that right around 2004, the clock rates quit improving. For any of you that are old enough to have been around in the 90s, you would know that clock rates back then used to double every couple of years. It was called the megahertz wars back then, because if you bought a computer, a laptop or a desktop, and it had a 300 megahertz clock, well, your friend a year or so later would buy one with a 600 megahertz clock. And indeed, things would run twice as fast, be it a video game or just a computer code. Your Python script back in the 90s, if you wrote one in 95, and it ran at a certain speed, by 97, it would be magically running twice as fast without you doing anything. And that was the era when the clock rates were climbing and things were just magically getting faster. And so that stopped again, right around 2004. I showed you those, benchmarks, that spec-in benchmark, basically. It's just a common generic benchmark we used for the earlier graph. Well, it was true of almost everything. And it's because of these clock rates plateauing. And indeed, today, if you buy a computer, it's going to run at, 3 gigahertz plus or minus. If you bought a computer 5 years ago, it ran at 3 gigahertz plus or minus. And if you buy a computer 5 years from now, it's going to run at 3 gigahertz plus or minus. And that's very different than the earlier eras of computing. Now, why is this? Well, that's the other half of this slide here. And that's this, the temperature that modern chips are running at. This is the watts per square centimeter that modern computer chips are dissipating. And that's actually not that inaccessible physics to understand. Watts per square centimeter, we're now running at about almost 100 watts per square centimeter. And if you think about a 100-watt incandescent light bulb, which, those are still around, right? 100-watt incandescent light bulb is a lot of heat. If you put your hand on it, you would burn yourself immediately, right? That's an awful lot of heat. And yet that's how much modern chips, when they're running full out, are expected to dissipate in a postage stamp size area. And that's asking a lot from the electronics and from some little fan that's sitting on top of it trying to blow some air through maybe even your laptop. And so this is the reason why clock speeds have plateaued, is that the computer chips are running hotter and hotter to the point where they were on the edge of melting down. And they run on the edge of melting down. And so they couldn't just keep cranking up the clock speeds or they would melt. And this is not exaggeration. Modern chips do run considerably hotter than a hot plate. Hot plates do not run at 100 watts per square centimeter, not even close to it. Your modern computer chips are running hotter than hot plates. As a matter of fact, every once in a while, let's see, there's an animation here. Can I get it to run without me turning off my cursor now? Here. Every once in a while, somebody figures this out when they're building a new computer and does decides to be humorous and post something like this on the internet. And so this is reality. This is a modern computer chip there. You can, fry things on top of it while it's running. Not going to last too much longer without the cooler on top of it, sucking all that heat away. But this is the temperature that modern computer chips inside of your desktop on your GPU. This is how hot they run. And so the engineers couldn't just keep cranking up the clock speeds because that makes them run even hotter and because they're on the verge of melting down. Now, it's not a new problem. Here's a Cray computer from the mid 80s because, it was running on the bleeding edge of melting down as well. So they had liquid coolers on it. This thing in front is a heat exchanger here. And when it was running, would be bubbling away with some blue fluid. Looked very artsy, actually. The Florinert bubbling away, keeping the machine from melting down. So it's not a new problem, but it's certainly one that intruded its way into the desktop world, or even your cell phone. Your cell phone, when you're playing back a movie, you notice it gets noticeably warm, sometimes uncomfortably so. That's the thermodynamics of modern electronics. So the engineers recognized that they couldn't just keep cranking up the clock speeds, not without trying to put liquid cooling on your cell phone, which is not very desirable or practical. So they turned instead to the only alternative that we have, which is to run more parallel. And here's the mathematics of that. It's basically, if we had an old single core chip and it had a certain voltage and frequency that it ran at, and it took however many watts, well, if instead we used two of those chips and we throttled back the clock rate sum and we throttled back the voltage sum, and those kind of go hand in hand, then we find out, because of the way power scales, and we won't go into the formulas for it, but because of the way power scales, that means these things are only using, both of these chips together are only using the same amount of power as our original chip did itself. So we've got 1.8 times the performance, but with the same amount of power, same amount of heat that we need to dissipate. The power that you put into a computer chip, all it does is turn into heat, right? So when we talk about heat dissipation, talk about how many watts a computer uses, it's the exact same thing. All the power your computer uses, its end product is just heat. And so we've got here, with the same amount of power, the same amount of cooling we need for your laptop with its dual core, these days 4-core, 8-core laptop. We've got same amount of power, same amount of heat, but we've got 1.8 times performance. But it's now parallel computing that we need to be involved with. So the old serial computing doesn't work anymore. Now we've got to do parallel computing. But this is the physics that drives modern computing. So when I was saying that earlier slides, maybe the most important thing to understand about modern computer architecture, it shows you this is not a trend that is favored by engineers or software designers. Instead, it is the laws of physics. They're not likely to change anytime soon. So computing for the past couple of decades has been driven by these physics right here. And for the foreseeable future, this is how it's going to work. This is why parallel computing has become so incredibly important everywhere. And if you want to see how, when I say everywhere, how important it is, here's just a generic Intel processor, different generations over the past 20 some years. So starting out with Pentium 3s, all the way up to, a fairly modern Skylake processor, like I'm sure at least a few of you have sitting in your laptops. And so these Intel processors over the years have gotten incredibly parallel in ways you may not be aware of, to the point where back at the turn of the century, they used to do about 3 floating point operations per cycle. So flop is a term we'll use a number of times this week. It stands for floating point operation. And the standard way to refer to it's a 64-bit. Most of you think of that as double precision floating point operation. So that's to keep everybody fair. That's the scale it's used, is a 64-bit floating point operation. So an add or a multiply or divide, for example. And a chip at the turn of the century could do 3 of those for every clock cycle. And that, at the time, as a matter of fact, we thought, hey, that's parallel. Well, today, a Skylake processor can do nearly 2,700 floating point operations for every clock cycle. And that's because it's gotten extremely parallel. And these are the ways it's gotten parallel, and we'll dive into these. They'll make a lot more sense this week as we talk about things. It's got vector instructions. It's got a lot of cores. So Skylake processor, it's like we had in our last Bridges machine, had 28 cores, for example, per processor. So it's gotten very, very, very parallel, and that's why it can do 2,700 operations per floating point clock cycle. Now you might think, okay, that's all just plain wonderful, but it also, the converse of that is that if you don't program in parallel, if you don't use parallel programming techniques on a modern microprocessor, you don't even get a fraction of a % of its performance. If you write just inherently straight serial code and you're only getting 1 floating point operation per clock cycle out of the Skylake processor, you're getting a fraction of a % of its potential performance. So it's great that they've gotten very parallel, but it means the obligation is on you now to become a parallel programmer if you want to use anywhere near the potential performance of this chip. So to combine all these things together right here, this is kind of what we've been talking about here. We've said the transistors have kept coming. So Moore's law isn't dead yet. Computer chips have continued to evolve dramatically right up into the current day and for the next couple of generations to come. The roadmaps are still there driving this onward. But the single-threaded performance, the serial performance, has definitely plateaued. And that's because the clock speeds have plateaued. And that's because things got to the point where they were just going to melt. They kept cranking up the clock speeds. And so the answer to keep the performance going on is that the number of cores has skyrocketed on these processors. And we'll get into the details of all of this, fear not. But this right here is modern computing in a nutshell over the past 50 years. This is what's happened. And this is the way it's continued to go. And again, it's not because of design choices made arbitrarily because engineers love parallel computing or software people do. It's because of the laws of physics. So this is where parallel computing comes from. Let me take a moment here and see if there are any non-logistical questions. See, Tom's been picking off all the access questions and whatnot. Let me back up with chat here. Let's see. I think I probably answered most of these. Oh, well, quantum tunneling is one of the limitations of making transistors smaller, but you can see, and that's what we're hitting now. If you look at modern transistors, they're now only, dozens of silicon atoms wide on the gate, but we haven't hit that limit yet. So this limitation here has nothing to do with quantum tunneling. This is power. It's all about power. It's not about quantum tunneling. Believe me, the smaller, closer transistors that have been happening over the past 20 years mean you can technically run the clock rates much higher than they can. But it's just power dissipation. So this graph is all about the power. We're slowly now with Moore's law, like I said, Moore's law is finally coming to its end. So Moore's law now is finally starting to run into issues like quantum tunneling and lots of other issues too. Even before quantum tunneling, you run into lots of parasitic, current issues, current linkage and whatnot. So we're running into small to scale issues, but it's not what happened 20 years ago to cause everything to take this abrupt turn here. Instead, it was power dissipation. Let's see. Do you mean to use 2,700 flops? One has to use parallel programming? Absolutely, yes. Let's see. How many OpenMP threads does a single processor handle? We will get on to that today with OpenMP, so we'll answer that question in more detail. I don't want to give you a superficial answer right here. It's got a few subtleties to it, but we'll get on to those in detail this afternoon. Okay, that's the y-axis on this figure. I'm not sure which figure we were. Oh, in this figure right here, the y-axis is multiple things. It's transistors, it's watts, it's a bunch of things. It's just mostly to show you it's a logarithmic axis. So there's a lot going on. We overloaded this graph with 4 different things here. So it's the number of cores right here is getting up into the hundreds. The frequencies are getting megahertz, gigahertz range here. So there's a lot going on the y-axis, but I think I labeled it all right. Okay, so now parallel computing. That's what we're going to spend the rest of this week learning how to do, because you have to if you want to use modern computer equipment. And parallel computing kind of has this one central idea to it, which is that you can make most science will turn into parallel computing, because as we do more and more and we look at more and more examples, you realize most of the world is very parallel, and most science is amenable to be turned into parallel computing. However, a number of algorithms, just ways that you happen to scratch out doing something on paper, can be very problematic to turn into parallel computing. And so the real art of being a good parallel programmer is to embrace the science, the simulation you're trying to do, and find out that very often it turns into parallel computing in a natural way, because nature is very parallel. And to recognize when you're beating your head against the wall of an algorithm that you happen to be fixated on, because it happened to be the way you wrote something, it's very difficult to make parallel. And so one way I think sums this up pretty well is a analogy from Fred Brooks' Mythical Man Month, which for any of you involved in that want to get serious about software, it's essential reading. So it's taught in all kinds of software engineering courses. You'll read this book, because he covered lots and lots of issues, a lot of them more managerial about developing software. But one of the things, the analogies he brought up, which is timeless, is that if one woman can make a baby in 9 months, then certainly 9 women can make a baby in 1 month, right? No, it's ridiculous, right? You can't just parallelize everything. But on the other hand, 9 women can make 9 babies in 9 months. So there is, and that's the theme of parallel computing, that most problems in this world, most physical simulation, and we're going to mostly fixate on physical problems, scientific type problems, because I'm assuming that's most of our audience here. Most scientific problems do have a mapping to parallel computing. Nature is very, very parallel, but you can't just take any algorithm that you happen to use in the serial world and make it work in parallel. So let's look at an example here to bring this to life. And the weather model is one that we'll come back to time and again, because I think it's very intuitive. It's easy to understand everybody what we're trying to do. We're trying to simulate the weather, and everybody's kind of comfortable with the weather. And the way we would have done this in the 1970s is we would have a computer with a very fast CPU, the fastest available in the 70s. Our weather map might be this 2D grid. In reality, it'd be a 3D grid, but we'll think of it as a 2D grid for our problems right here. It'd be a 2D grid that we've broken up our map into. And our program would just go over this grid, and for each point in the grid, it would have the data from, for the wind velocities and the pressures and the humidities and whatnot. And it would take, and using those variables and the variables from the surrounding points in the grid, it would calculate a new value for the weather a minute into the future. And then it would go to the next grid point and calculate that a minute into the future. And so it would scan over the entire grid, use the mathematics of weather prediction here to advance the simulation 1 minute into the future. And then we'd have the prediction. If we started out at noon, we'd have the weather at 12:01. And then we repeat the whole process again, and we get the weather at 12:02. And if we run over this whole thing 60 times, we predicted the weather an hour into the future. And that's how weather modeling would have been done. Now, a guy named Richardson back in 1917 figured out a way to do this in parallel. And you might right away say, why was a guy in 1917 concerned with doing this in parallel? Well, his notion was that he would have 64,000 meteorologists in a room, and they would be the national kind of weather prediction service, and that they would do all of this. They would predict the weather. And his insight, which we still use today, is that they could do this in parallel because the weather is only dependent upon the immediate surroundings for the next time step. So if we're sitting here and we want to know our weather for a minute in the future, if we stick our head out the window and we look a couple kilometers to the north, south, east, and west, we know everything we need to know about the weather a minute into the future. Yeah, sure, there might be a weather front, 100 kilometers away coming in, but for a minute into the future, we only need to know north, south, east, and west, our immediate neighborhood. And so if we just exchange some information with our fellow meteorologists in north, south, east, and west, we can now predict our weather 1 minute in the future. So our meteorologist does that right here. All the other meteorologists, her fellow meteorologists here off to the sides do it. And then we all predict the weather a minute into the future. And now we sit down and do the exact same process again. And now we're 2 minutes in the future. And we do it 60 times and we're an hour into the future. And we've never had to do anything more than exchange information with our immediate neighbors. And as the weather propagates across the map, it does it neighbor by neighbor. And eventually something over here affects us here, but we never needed to talk to anybody besides our immediate neighbors. And Richardson's scheme is very naive in the sense that we now know, weather prediction by nature of it being chaotic fluid dynamics is incredibly numerically intense. You're not going to do it with pencil and paper. It's challenging enough to do with modern supercomputers, but the algorithm is sound. And so it's exactly how we do weather prediction today, is we do it by having each cell just communicate with an immediate neighbor. Again, it's going back to the theme. Nature is inherently very parallel. Nature says whatever weather's going on over here happens in parallel with the weather going on over here, and they're kind of each local phenomena. They'll eventually affect each other, but they're fairly local. And we'll find, as we look at examples throughout the week, that applies to weather, or molecular dynamics, cosmology, whether it's general relativity, or quantum mechanics. So this locality is something that's very universal, but we'll stick with the weather problem for now. Okay, well, the way we would have done this, as soon as we decided we wanted to run this faster and we want to run it in parallel, the easiest way to do it, and the way that we'll cover today, might be using OpenMP on a shared memory machine. So this is what we're going to get into today. We're going to look at computers where all the memory is shared, like your laptop. Your laptop might have 4 cores in it, but it shares, all the memory is shared amongst those 4 cores. Any one of those cores can see the entire memory inside of your laptop. In other words, if you pop the top off your laptop, the RAM chips in your laptop are shared by all 4 cores equally. And so that's the weather map sitting on those RAM chips. All 4 of the cores can see it. But if we want to speed things up, the way we do it is we'd have each core just be responsible for 1/4 of the weather map instead of doing the entire weather map. So by only having 1/4 of the calculations to do, we would hope that this would run 4 times faster. And each core only needs to worry about its own region, with the exception of along the borders. Weather does move in along the borders. So these 2 cores do need to be in sync along the borders. But the way this core does it, it just peeks over here across the border and says, hey, what weather is coming into me from the calculations that this core is doing? And likewise, this core can say what weather is moving into me from the north. And by doing this, we can go ahead and calculate our weather a minute in the future, do it again and again and again, and be an hour to the future, except 4 times faster than we could do it before. So this is like having 4 meteorologists in a room, and they're all sharing the map. And so if this meteorologist needs to look to the south, she just looks down here across the map at what this core is doing down here. Boom, calculation is done for this entire core of the map. So this is what we're going to do today with OpenMP. And we'll find out that it's pretty straightforward to do this. All we need to do is throw some directives in front of our major computational loops, and boom, we can get some very effective results. But we're a little ahead of ourselves. We'll come back to this very shortly. Now, another way you can do this that's quite popular and important these days is to use GPUs, or basically repurposed graphics cards, video game cards today, that are very good at doing numerical calculations. And we'll get into this topic a little bit more tomorrow, but basically the fact that video game cards were a cheap source of flops and are also power efficient source of flops, so they're good from that heating perspective too, meant that about 20 years ago, scientists started thinking about how could we possibly use those flops for science instead of just video games. And to the point we are today, where there are accelerators, these cards that are dedicated to doing scientific computing, and they're very good with it. And the evolution of these things continues. We're going to talk an awful lot about this tomorrow. But basically, the way GPUs work is that we have our weather map sitting over here on the CPU, and we communicate it over to the bus, the PCI bus. So you might think of the GPU as really connected to the CPU, but it's not. It's plugged into this. So if you have a workstation, if you have your monster video game workstation at home, and you pop it open and you plug in your, your fantastic new NVIDIA video card into it, you plug it into this PCI slot. And the PCI slot is actually quite slow. It's very much a bottleneck compared to the normal speeds that CPUs can access their RAM. And so you think of a PCI slot as fast because it can do tens of gigabytes per second data transfer, which is fine for moving a video frame, but for purposes of scientific computing, it's this bottleneck. So we move it over this PCI bus. Now it's in the GPU. When it's in the GPU has thousands of cores, literally thousands of cores to work on this weather map, and it's very fast. But those thousands of cores are quite stupid. They're not nearly as flexible and smart as the CPU cores, so they can only do limited types of calculations, but they're very fast because there are thousands of them at doing those limited calculations. So they work on the weather map, and then they have to send it back to the CPU for anything they can't handle. And this back and forth is a big issue. It's one we're going to get into tomorrow. So you can think of this as it's like one meteorologist who really knows what they're doing, and they're coordinating with 1,000 math savants. So math savants are really good at number crunching, but don't really have a lot of flexibility. They all got to do kind of the same thing. And so that's the way GPU computing works, and we'll get into that tomorrow. And it will also work. There's different ways of doing it. We'll talk briefly about doing it with CUDA, which is a painful way to do it. And then we'll talk about the modern way of doing it, which is OpenACC, which you will learn. And very similar to what we're going to do today with OpenMP. The last way of doing this is with MPI. Now, MPI is where we take this weather map and we break it up amongst a bunch of different workstations. So instead of just having 4 cores in the same laptop break the map up virtually into 4 pieces, but they're all really sitting in the same memory, now we break our weather map up into a bunch of different pieces. Maybe one state is each piece, and we stick them on different workstations that are connected together with Ethernet. Now, why would we do this more complicated scheme that requires us now to send our data back and forth over the network? Well, the reason is that this can scale as large as we want. Instead of just being stuck with the 4 cores you have in your laptop, we can have 50 workstations. Or if we have enough money, we could have 50,000 workstations. And so the big supercomputers, which have millions of cores these days, have millions of different pieces they can break the map up to and speed things up, hopefully millions of times. So this scalability is much, much better. It's open-ended. There's no ceiling on this outside of your budget. So you can run your code as large as you can afford to buy a machine or get access to a machine. But with it comes increasing complexity, the way we break our code up. So MPI coding is harder to do. It takes a lot more effort. And that's why, one gross way of seeing that is to look at our agenda. There's 2 days basically for MPI, right? It only takes us a day to learn OpenMP, a day to learn OpenACC. It takes us 2 days to learn MPI. And again, that's a fairly crude way of looking at it, but it's not completely unfair. MPI is harder to do, takes more effort, but the reward is that it's got infinite scalability. So you can think of this as like 50 meteorologists, except now they're not in the same room just sharing the data casually. Now they got to communicate over a telegraph with their neighbors. So it's more painful communication, but it's got potentially infinite scalability. And we're going to learn to do that with MPI. So here's how the pieces fit together. Is we've got a modern CPU, which might have 6 cores in it and some chunk of memory. And every modern CPU has multi-core. You can't even buy a CPU anymore that's not multi-core. So everything is multi-core, and we're going to learn how to program that with OpenMP today. Take advantage of those multiple cores, whether it's your cell phone or whether your cell phone has multiple cores. You can't buy a cell phone that doesn't have multiple cores. So it's your cell phone or your laptop or a high-end workstation. We're going to learn how to program those with OpenMP today. Now, you might decide that you can get extra flops, extra performance by buying a GPU. And when you plug that GPU in, you need to program it in some other additional way. It doesn't magically program itself. And OpenACC is by far the superior way to do that. And that's what we're going to learn tomorrow. And if this isn't enough for you, and it may very well not be, with these combinations of techniques, we might be able to speed our codes up. We'll find, 30 or 40 times. That might be it. That might be the game changer for you. Now, instead of your simulation taking 30 hours to run, now it takes an hour to run, and that's fine. Now you can run a couple simulations a day and you're happy, and that's it. But if you want to go beyond that, if you want to get up to scalability that allows you to run things hundreds or thousands or millions of times faster, then you need MPI to connect together a bunch of these different kinds of nodes or workstations. And so this is how the pieces fit together. And by the end of this week, you're going to know how to use all the pieces. Okay, let me take a pause here and scale up and see. Let's see. Okay, can CUDA be considered as an analogy of MPI but for video cards? No, we'll get it. So tomorrow we'll talk. So CUDA is basically a low level. CUDA is the machine language version of OpenACC. It's a very low level, painful to use, more painful to maintain, I think is really the biggest issue. CUDA is the low level way of programming GPUs. And we'll come back to this in more detail tomorrow. So we'll get into this question. To tell the computer how many cores you want to dedicate, or does it do it automatically, figure it out? We'll get into this afternoon with OpenMP. So we have different ways. We can tell the computer how many cores we want, or we can hope it defaults to some reasonable thing. We have control over that. We can go with the flow with the default, or we can more manually control it. And we'll find out how to do that with OpenMP this afternoon. So MPI is the only option for nodes to talk between them. And the answer is, for practical purposes, yes, absolutely. It's, these other things, OpenMP is one of, we'll talk about alternatives to OpenMP when we're done with OpenMP today. We'll talk about some alternatives to OpenACC. We've already mentioned one, CUDA, for example. But for doing communication across nodes, MPI is pretty much your only choice. If you right now go on any supercomputer and look at any of the codes that are running across the nodes, they are all using MPI. And when I say all, I mean greater than 99% of them. There are some attempts, and we'll talk about those at the outro to computing talk at the end of the week. After you know MPI, and you can appreciate that MPI takes some effort, and you can see why people might want an alternative. We'll talk about some of the alternatives that are emerging or have been emerging for a long time and aren't quite getting there. But at the moment, if you get on any large cluster or any supercomputer, everything is MPI. So MPI is pretty much the only option to get to scalable computing today. And we'll come back and talk about some of the nuances of that. People are attempting to have, PGAS languages and things like CoRay, Fortran, and whatnot. And with the outro talk, we'll talk about that a little bit. But at the moment, the only thing that has any traction at all in this space here of connecting together multiple nodes is MPI. And there are software packages built on top of MPI. So a lot of people don't even realize they're using MPI when they're using a software package. But beneath those, that is MPI. Okay, let's see. Strictly dealing with cores or threads. Okay, well, that's a good introduction to my next slide here, which is terminology here is going to get to be very confusing this week if we don't sort some of it out right now, because people throw around a lot of terms and they don't always use them appropriately. And so I've already used a number of terms and haven't absolutely defined them. And so let's talk about some of the terminology we're going to use this week. And we'll introduce some more as we go along, but these are the big ones right here. And especially these are the ones that get confused an awful lot. Now, a core is basically something that can run its own independent little program. It's got enough smarts to be able to go off and run its own, video game or its own browser or whatever you want to think of as an independent program. A core runs an independent program. And in a modern processor, when you buy a GPU, when you buy your laptop today, if you peel the top off and you look at the chip in there, that chip will have in it multiple cores. So your laptop probably has maybe 4 cores in it. So those cores, each one of those cores is an entirely independent little processor that can run away and do its own thing. And that's the reason people often call it a processor. So I even used that term just now. So it's an independent little processor. But technically, the way what a processor technically is, the proper terminology is a processor is the actual physical chip. So again, if you pry off the lid of your laptop, the physical chip that's sitting in there, so whether it's Intel or ARM or AMD, that physical chip has multiple cores inside of it, but the chip is what you should call the processor. So if you have a workstation, you want to upgrade it, you go on Amazon, you can upgrade your processor. The thing they ship you is a processor. Inside of it is multiple cores. So that's the way you should technically refer to things. It's the processor is the physical chip, and it has multiple cores on it. And each one of those cores can independently go and do its own thing. A node is a term that's most commonly used when you get into serious data centers and supercomputers and whatnot, where you start to have these, you go into a data center and you see these cabinets along the floor. And if you open one of the cabinets, inside of it, you see a bunch of blades, a bunch of motherboards basically in each cabinet. Each one of those is usually referred to, or commonly referred to, as a node. A node, technically, to be most specific, a node is anything that's got its own independent connection to the network. So if you go into that data center again and you pop open that cabinet, if you walk around the back of the cabinet, you'll notice that each one of those blades has its own connection, cable connection to the network. However big the network is, if it spans the whole room or whether it just spans the cabinet, each one of those blades has its own connection to the network, its own endpoint. That's what makes it a node. And you start sticking nodes in cabinets, and you start sticking a bunch of cabinets in a room, and next thing you know, you have a supercomputer, or you connect a bunch of workstations you have around your own department together, and you can construct your own cluster. but each one of those is a node. So that's when I use the term node, that's what I'm basically referring to is some collection of motherboards we've networked together one way or another. And each one of those motherboards, it might have multiple processors on it, and each one of those processors that probably has multiple cores, but that's what makes up a node. Now, because this terminology is so overloaded and ambiguous and people misuse it, it's become common for people to do programming to instead to kind of disconnect from all that luggage that comes along with it, that baggage from traditional usage. And I'm going to try to use this week the term processing element a whole lot. When I talk about a PE, a processing element just means, hey, something that can run its own independent program. So when we start talking about spreading our code out with MPI over a bunch of, over the network and over a bunch of cores and everything, I'm going to actually say we're going to spread this out over 1,000 PEs. And so a PE or a processing element, that's just a nice way to get rid of all this baggage right here. But these days, whenever I say PE, it's almost always going to refer to, practically to a core. So if I talk about your laptop, we're going to say we're going to run on your laptop on 4 PEs. It means we're going to really be using the 4 cores on the single processor inside of your laptop. So again, this terminology is a little bit fuzzy in the way people use it, and it gets overloaded. And so that's why I'm going to use the term PE as much as possible, just to kind of prevent any confusion there. But this is technically the way we should refer to the different pieces that make up, any pretty much interesting modern computer. Okay, let's see. Some questions coming in. Whether it's in a core and a thread. Well, threads, when we get to OpenMP, we'll talk about this more. Threads run on cores, but we'll come back to the nuances of that in more detail. So threads a software concept. And so we're going to stick with the hardware right now because we're going to come back to this afternoon with OpenMP. We'll talk a lot about threads. You're going to know what threads are very, very much before we get very far today with OpenMP. But threads is a software idea. Threads run on cores, but we will come back to that in more detail. The difference between a physical processing unit and a node. I don't know what a physical, so PPU, I don't know that terminology. I don't know what a physical processing unit is. So you Google it and you tell me. So I'm not sure what a PPU technically is supposed to refer to. A thread is more about logical tasks and programs, not the, okay, so it's core thread. Okay, so if we look at a modern if we look at any modern machine here, like I said, we got a lot of pieces going on here in parallel, lots of parallelism at all different levels. A lot of it is even hidden. I showed you those processors, and a modern Skylake processor, for example, does almost 2,700 floating point operations per cycle. If you're using it well, that's because it's got a lot of low-level stuff built in hardware into the processor itself. And you hope that the compiler can take advantage of most of this. So a lot of the times the compiler can do some of the vectorization stuff in particular, and we'll come back to what that means. But the vectorization stuff, you hope the compiler is smart enough to do a lot of this kind of stuff. And modern processors do have an awful lot of cleverness in them to do things in parallel. They can shuffle the order that things happen and do speculative execution and all kinds. It's gotten so complicated. This is where the meltdown and Spectre security vulnerabilities that are plaguing modern processors. This is where they come from. Is too much cleverness in here. Intel in particular got super clever about this stuff to the point where they overlook things themselves. But at any rate, you're lucky in that the compilers mostly deal with this kind of stuff. Now, OpenMP can help, because a lot of times if you were serious about performance and you're just rely on the compiler, you're going to sometimes get disappointed, and then you have to go back and figure out some way to poke the compiler and make it smarter about doing this. OpenMP is helpful here. We'll get into that this afternoon, but mostly the compiler worries about this. On the other hand, as soon as we start talking about doing multi-core programming to use multiple threads, that is where OpenMP comes in. Or if you have a higher end motherboard and it has multiple processors on it, so that's quite common in big data centers and on supercomputers, is that your motherboards, your nodes or your blades, however you want to call them, they don't just have one processor on them, but they'll have multiple processors. Each one of those processors with multiple cores. And so if you have a multiple socket motherboards, OpenMP helps you there too. Now, if you start plugging in GPUs, that's where OpenACC allows us to program the GPUs. And at the end of the day, when you want to really scale things up and you want to use more than one node at a time, that's where MPI comes in. So these are up to you. This, you can have hopes the compiler will do a good job of taking advantage of. And by the end of the week, you're going to know everything here. Now, there are a couple other things that are also important, but we won't go into because they are specialized. They may or may not apply to you and your work that's joining the future. But these days, there are a lot of more or less custom hardware kind of architectures that are interesting and important, whether they're completely custom chips, ASICs, or whether they're field programmable gate arrays, these kind of semi-reprogrammable hardware. People are using that a lot in science to do, if they've got a very well-defined task, you can use this to kind of configure your hardware to address the task. Digital signal processors are very important in lots of instruments these days. And these things are also parallel computing, very much so. And they also relate to some of the things like OpenACC and OpenMP that we're going to talk about. But we just won't have the time to get into this kind of specialized semi-custom hardware and the algorithms that apply to them this week. Another thing that's very parallel and important these days is I/O. All I/O systems these days that are any good are parallel. They're RAID systems at the lowest level, and at large scale, they're big parallel file systems. And they're all very, very parallel, and they use lots of the kind of parallel techniques we're going to talk about. But we mostly are going to hope that that they're transparent, that they just work magically for us, that they do all the parallel stuff for us automatically in the background. And that's largely going to be true. There are some exceptions to that. We get into the end of our MPI. We'll talk a little bit about using MPI in massively parallel I/O systems. But by and large, you hope that most parallel I/O is just automagical as well. Okay. Let's see, does memory get shared among processor node or cores on a processor? So memory typically gets shared amongst everything that's on that motherboard, that blade, which at the very least, if it's a single processor, it's shared amongst the cores. If there's multiple processors, it's shared amongst the multiple processors and all the cores on those multiple processors. And with OpenMP today, we'll have some examples of that off, some pictures and whatnot that'll bring that to life. But the memory gets shared on the motherboard and it can't be shared off the motherboard is basically the principle. Let's see, presentations are already posted. All the materials should already be posted out there. Let's correct guessing. OpenACC and OpenMP would improve performance most on a laptop, and MPI would not help there. That's mostly true. By the end of the week, we'll be able to discuss some of the subtleties there. That's not always true, but that's mostly true. That's generally true. Yes. Presentations. When I said presentations are posted, I meant the materials, which Tom pointed you at. Let's see the slides. Okay. Vector lanes present inside a core or processor. Yes, so vectorization is an important part of modern processors and how they get their speed up. If you go back to that different Intel processor over the past 20 years, you'll see that vectorization or the AVX instruction sets are an important way that they get their parallelization in modern chips. And we will talk about that some, and particularly with OpenMP today. But you hope mostly that the compiler deals with that, mostly. And sometimes it can, and sometimes it cannot. OpenMP can help you there when it's being obstinate. Okay, well, today if we look at the big machines that are out there, as I've said, a picture a lot of you have for a supercomputer or just a data center in general are these rows of cabinets. Each cabinet, if you pull open the door, has got a bunch of blades inside of it. And those blades are basically, motherboards, which have multiple processors and multiple cores on each processor, and that's what makes them up. So here are just a couple of machines, and I'll show you the definitive list in a second here, but this is kind of what modern supercomputers look like. And again, even generic boring data centers like Google or Microsoft or Amazon don't look a lot different from this. This is the top 10 list as of last June. It will be updated very shortly this month. So there's an organization called top500.org. I think you'll find, if for those of you that are interested in this kind of stuff, it's really a neat conglomeration of all this, basically what's going on in the fastest 500 machines in the world. So it's a site where you can submit, you run a standardized benchmark, the LinPack benchmark. It mostly does linear algebra. And you run this benchmark, and then you can get your machine on the list ranked here. And most of the fast machines in the world do that. And so you can kind of see at any point in time the top 10 machines. It's updated twice yearly. Again, the new one will be out the end of this month, and so updated. It changes a little bit, not a ton, from one iteration to the next. Although in the next year, I'll talk about Exascale machines. We hope there are a few really exciting machines that will jump to the top of this list coming online in the next year or so. But at any rate, this is the current or fairly current-ish version of the list. And if we look at the machines on this list here, you'll notice a couple of big themes, that the big machines these days all have hundreds of thousands, if not millions, of cores in them. So everything is parallel, is how you effectively use these machines. If you're not running in parallel, you shouldn't even be on these machines. The power, I was talking about heat and power dissipation earlier. You can see we're getting up into the tens of megawatts now on these machines. That's an immense amount of power and heat to dissipate, on these machines. We talked about some of the architecture, the pieces that go into this. And we look at, it's the way I've put this information in this column here, is we've got the chip here and the number of cores it has. So we look at machine 2, just to pick a random one here. We can see the Power 9 chip. So that's an IBM processor. It's 22 cores running at 3 gigahertz. So all the chips on here are all multi-core. This one down here, 64-core EPIC chip. So everything's multi-core. Most of them have accelerators. So here's an NVIDIA Volta card in this one, or in this one here. Here's a Xeon Phi, it's Intel's accelerator. So most of them have accelerators in them, or these GPU type plug-in devices in them to give them a boost. They're all multi-core, and of course they're all multi-node, hence how they get to millions of cores. So you can see all of these big machines have this kind of layering of the different kinds of parallel hardware. And if you go to 500 on this list, you'll see that's true all the way back at the end of the list too. All the top 500 machines are all very, very, very parallel machines. And if you want to use them well, you need to be a parallel programmer. And poking around that list and looking at different things on it can be interesting for those of you that are interested in using leading edge machines. And your institution may have something somewhere even in the top 500 on that list. Okay, well, we talked about the processors a whole lot here and the different ways they might layer. But the last thing I want to talk about hardware-wise is the networks that make these things up, because the networks are very important in terms of performance. When you start writing, MPI code that runs across a bunch of different nodes, those nodes need to be connected and shuffle a lot of data. And we could talk a lot. We could talk for hours about the details of networks, but really, there's only 3 important characteristics at the top level that sum up a network. And so, network engineers will be offended by my oversimplification, but this will get you pretty far, just understanding these 3 kind of things here: the latency, the bandwidth, and the topology. The latency is basically the time it takes to get a byte from one place in the network to the next place in the network. So if you got a small message, how long does it take just to move from one node to the next? Or the furthest node away maybe is your biggest concern, your slowest connection. But the latency is just for a small message. And there are codes that send lots and lots of small messages, and this is the important part of the network for them. On the other hand, there are codes which send huge messages, and the time it takes to start to get there isn't nearly as important as the rate at which a huge message can get through the network. So this is kind of the length of the pipe. This is the width of the pipe, is the way to think of it. And some programs send huge messages. They might not send that many messages, but each one's big, and they care more about the bandwidth. How fast can you cram a fast message through the network? So these 2 pieces right here will give you the ability to predict the total time to get a message, whether it's small or large, across the network from one node to the next. The third piece of the puzzle is the topology, or the shape of the network, because the way you connect these things together is infinitely flexible and has a big effect on performance and for different applications. And so we'll take a moment here to talk about the topology. You might have, in the simplest type of network, like an Ethernet here, with a bunch of workstations just connected together, serial daisy chain kind of manner like this. And it's very easy to build a network like this and maintain it. So a lot of computer clusters and labs are built like this, because again, it's easy to build and maintain. And that's fine, except if you start trying to run parallel codes on this, you right away find out that the fact that when these 2 are talking to each other, they're hogging the wire, means that these 2 can't talk to each other. And so it becomes very unsatisfactory, given that an awful lot of codes, nodes want to simultaneously exchange data. Our weather code, for example, at the end of calculating one time step, right after we calculated the weather to 1201, all of the nodes need to exchange information with their neighbors. So if they're all trying to use a network at once, this is a terrible network. And we'll find in scientific computing that kind of compute and then communicate cycle is fairly common. And so having everybody want to communicate at once is not what this network is good at. On the other hand, a network like this is great at this. What if we have a network with complete connectivity? Every node's connected to every other node. Well, this is fantastic, and it's the ideal, and nobody would argue that this is the ideal. The only problem is this is extremely expensive or impractical to build at scale, because if the number of connections here scales as n squared. So, if you have even 1,000 nodes here, you have, like 500,000 connections. So this is not a practical network to build for any sizable cluster. And so we can't build, complete connectivity, although again, it's the ideal, it's what you'd like to have. So a compromise you find for a lot of clusters in universities that build smaller clusters is something like a crossbar network. And a crossbar is this switch you buy that tries to fake like it's complete connectivity. It tries to look like it, but because it's not really complete connectivity, at some point you saturate it, you hit its total bandwidth limit, and then it kind of exposes that it's not really complete connectivity. But it looks good up to a limit. So crossbars are popular for that reason. They're a practical solution. Instead, what you find when people start building larger networks, a very popular approach is to build a tree. And a tree allows you to scale this thing up infinitely. You can just keep building a bigger, bigger tree. If we had a small tree here with 4 nodes and we bought another 4 nodes, we could just build the tree out like this. And trees are nice because they are scalable. The only thing that might not be scalable in your tree is the fact that the top node in your tree is having to carry more and more communication the taller this tree gets. As a matter of fact, there's a term for this called the bisection bandwidth. If you take your network and you bisect it in half, what is the bandwidth from one half to the next? And the bisection bandwidth for binary trees is terrible. The taller the tree gets, the bandwidth, the bisection bandwidth stays the same. It doesn't grow with the size of your machine. So this would be not very good for a large network. On the other hand, we can take the idea of a tree, and if we make it fatter and fatter at the top, so as we go up on our network from the compute nodes at the bottom, as we go up and we add more and more nodes and connections at the top, so it's not this peaky binary tree, now we have much better bisection bandwidth. If we cut this network in half right here, we have lots of connections from one half to the next. So fat trees turn out to be a nice way to build large networks. And indeed, there are different ways of visualizing fat trees. And if we look at some machines here and ways of visualizing, we'll see there are lots of different fat trees out there with different topologies to them. You have a choice when you're building a fat tree. How much fatter do you make it along the way? How many connections up and how many down? And so there are lots of fat trees out there with, parallel with clusters and parallel machines and different alternative designs for them. Well, over the past 5 or 6 years, we've seen a lot of attention and now finally the deployment of kind of a refinement on the tree idea, which is, you want to have good bisection bandwidth and fat connections, but you want to take advantage of the fact that modern networks have switches that can have lots and lots of connections to them, high-rated switches, that routing can be smart. Instead of old simple-minded routing that, to get from point A to point B, here's the way you go, networks can have adaptive routing, letting things move in different ways. And that's nice to keep congestion from happening. So you can keep, if you've got a lot of communication going on, congestion will happen with this pattern of communication. Maybe there's an alternative pattern of communication or a random pattern of communication that works better. And maybe most importantly, the fact that optical links are finally making their way into modern computing equipment is becoming an important thing. And optical links are much faster and can go much further without paying a performance penalty than copper, than wired connections. And so you want a network that's maybe a mixture of these optical and copper connections, and they have different bandwidths and latencies. And so you might want to start to build networks that have locally clustered wires and longer connections on optical. And anyway, Dragonfly networks get into that. If you're interested in networks, Dragonflies are the kind of latest, greatest thing that are being practically deployed. Take a look at that. So just here are some different examples of Dragonfly networks where the purple links are optical connections and the blues are electrical, copper connections. And you can see you have a lot of flexibility there. So that's becoming a thing we'll see on the latest, greatest Exascale machines being deployed. The last network design I'll talk about is one that seems to be a step backwards, but still has a lot of virtues to it, which is a simple-minded torus, a 3D torus, which is basically just saying I've got a lattice connection here, a nice Cartesian lattice. The torus just means the ends are wrapped around. That's the torus. So A and B are actually connected. I couldn't draw them here, but A and B are connected. And that means that data that has to get from A to B doesn't have to tunnel all the way back through the middle of the network. So toruses have these kind of edge wraparounds. And these seem, again, simple and unsophisticated, but since a lot of problems in the real world are three-dimensional, and a lot of our nearest neighbor communication, like in our weather code, is going to be this three-dimensional connection to our neighbors, this can be a very, very effective network, even though it has a lot fewer connections, because fewer connections mean you can make each connection faster. And if it maps well to your problem, it can be very good. So you'll still see 3D toruses are interesting. Okay, that's it for networks. When we come back to MPI, we'll see how we can either acknowledge or pretty much hope to ignore the different networks that we have that we work with, but the performance will matter a whole lot. Certain applications will really demand that we have a good network. Parallel I/O I mentioned briefly earlier is the kind of thing we just.
Hey, John, just to interject a second, there were a couple good questions that came in there that I didn't want to. I thought would be good for the whole group to hear.
Thank you. Let me back up there. Okay, and I'm always happy for the questions. I just out of the corner of my eye, I'm not always noticing if the stream that's flying by are logistical questions for Tom or technical questions for me. So let me back up. Let's see. What does one CPU having multiple core mean? Does it mean it can run multiple threads? Yes, it does. That's exactly what it means. And we'll see that more with OpenMP this afternoon. Let's see. I'm going to have to go back and check out the stovetop analogy here. That might be a winner. I'll have to see if it's appropriate or misleading, but it sounds good. Let's see. Does latency add up linearly as data size being sent grows or independent of data size? Latency is supposed to be, so the way you define latency is it's a message of 0 bytes technically. It's the smallest message you can send is what latency is supposed to be. So latency is the time it takes the message to start getting there. So it should be independent of data size. It's not always completely, but yeah, so latency is supposed to be independent of data size. Bandwidth is what is data size related. Network topology strongly correlate to shared memory or distributed memory usage? No, not at all. So network topology, the network is for distributed memory machines. That's the network is how you connect the distributed memory. The shared memory is on the node itself and is independent of that. So the shared memory is always on just the node on the motherboard, and the way we connect the motherboards together is the network. So they're two independent concepts, and we can mix and match between them. Latency is why if you have a very small computation, I'll try to use many cores. So latency is in the networking sense that we're concerned with right here, not the memory access sense. So there's latency is a term that's also applied to memory access. And we'll talk about that more with OpenMP. The latency term, I've been talking about networks here. If we're talking about memory access, memory also has latency and bandwidth. It's the same thing. Latency is how long it takes to get 1 byte for memory, and bandwidth is how long it takes if you start want to get megabytes and megabytes for memory. So it's the exact same concept. I've been talking about it applied to the network. With OpenMP, we'll apply it to memory. But so far, I've been talking about latency and bandwidth with the network. But the idea, again, is that some algorithms are concerned with small bytes they're gathering random bytes scattered all over memory. Latency is going to be the dominant factor there. Whereas other algorithms, they work with big chunks, big strips of memory at a time. Bandwidth is going to be the major factor there. Let's see. Okay. So, and I'm glad for all the questions, but we're also running a little bit behind. But I said today is the day we're going to probably run a little bit behind, and we can make it up tomorrow. So I'm not going to let myself get concerned because questions are what we're here for. Okay, parallel IO, as I mentioned before, you hope it all happens magically and the system administrators are mostly responsible for it. But at the end of the day, when your application doesn't have good IO performance, it can be a huge, we have many people who, when they scale up their application, all of a sudden find out that something they thought was so boring that they could ignore it before is now taking 40% of their runtime as IO. It's not uncommon when when you scale up your code successfully, so now it's running on 200,000 cores. It's a big win, except that 200,000 cores can suck in a lot of data very fast and generate a lot of results. I mean, that's what you were working for, to get something that's a real number cruncher. But now you need a system that can supply that data and offload the results fast enough. And that's where IO can become a thing. We'll talk about this a little bit more with MPI at the end of MPI, because that's where we can have some effect for it. Okay, but I hope I've given you some idea of the hardware and everything that's floating around, the network stuff, the cores, the CPUs, the motherboards, all this stuff that kind of you pile together to build a supercomputer. Well, you happen to be coming into this stuff in a year that's particularly exciting because exascale computing is finally reaching us. And what is exascale computing? Well, for the past decade plus, we've really been reaching towards this next goal since we hit petascale computing, which is exascale, or the ability to do a quintillion floating point operations per second, 10 to the 18th floating point operations per second. And so that's again, we've been working very hard to build machines that could possibly do this. It's been a long road to get here, and it's finally happening in the next year or so. The first machine will come online, whether it's here or China is going to be an interesting question, but the machines are all designed and being built and deployed as we speak. And so Frontier and Aurora are the machines that are first in order here to come online. And to put it in perspective, this is, or some perspective at least, for those of us that have been around a little while, a supercomputer that took up an entire room and was fastest in the world back in 2004 was the Cray Red Storm. And if you do 42 teraflops, this machine is equal to 23,000 of those. So it is a serious piece of computing. Or another way to look at it, it's a little more contemporary, is that a modern GPU that's pretty good, a Volta, like we're going to use in our workshop tomorrow, this is 133,000 of those Voltas running full out. So this is where we are. Now the reason, say we've been striving for this for a long time, is that if we look at that top500.org I was talking about, and if we look at the fastest machines in the world from the beginning of that list basically until today, the list began in the mid 80s, we can see we've been on this pretty steady climb. And it's had, so the fastest machine, the number one machine is actually here in the middle. This is the aggregate, this is all of them together, and this is the slowest machine. So if we look at the number one machine here, we can see it's been this kind of steady climb. It's had some quantum jumps here. We'll talk about that in a second. And it's gotten a little scary, and it looks like maybe there are some plateaus. The plateaus scare us once in a while, but in general, it looked like somewhere around 2020 or so, we should be getting to exascale. We should be getting this 10 to the 18th floating point operations per second. And so for the past 10 years, that's been the goal. Can we get to exascale in 2020? Well, we didn't quite make it in 2020, and there were signs that we wouldn't because things are getting harder and harder as we go. But we're hoping late 2021. Well, this is at least the exascale computing project in the United States. And again, the United States and China are the two contenders at the moment with immediate plans to deploy exascale. This is the current exascale computing project in the United States. It's dumped billions of dollars into this and for a number of machines. And this has been the roadmap to get here. So they've been working their way towards it with machines that are pre-exascale. And hopefully one of these machines comes online very shortly and will be the first exascale machine. And you can see, again, no surprise. They're very, very parallel. In order to get exascale or better performance, they take a lot of power. So this is the grid as it's filled in so far. These machines are still under development, might be an overstatement. I mean, they're pretty crystallized in terms of their plans, but they haven't released the final numbers and power and everything for all of them yet. Well, one thing that is interesting is you can notice that they've all decided to go with a Dragonfly network. So that is definitely the thing here. But they have fairly different architectures on the nodes. Some of them are AMD processors, some of them are Intel processors, some of them are Volta GPUs, some of them are AMD GPUs or Intel GPUs. But you will notice they've all got accelerators. They're all very multi-core, and they all, of course, are many nodes. So if you want to use any of these machines right here, you're going to use the techniques that we're learning this week to use them. Now, the way to get to exascale, the road to exascale has been these quantum jumps. It hasn't been smooth sailing. As I said, Moore's law hasn't been driving this for a long time. For the first however many decades of this, it was just Moore's law. Everything just got faster. But recently, it's been much more of a battle. So the first jump here was about 10 plus years ago when Moore's law started to die. We saw around 2004, right? We weren't getting, wasn't Moore's law dying, but the serial performance was dying, right? The clock speeds were plateauing. And so the first answer to keep things moving were accelerators. This is where GPUs came along to save the day. And indeed, they kind of kept boosting things along. The second boost is one that many of you may not be aware of at all, which is 3D electronics and 3D packaging, which really came along as people were getting more and more concerned with this packaging and and the fact that moving data around these machines now is taking way more time and power than the actual number crunching. And so getting the electronics packed closely together has been a huge effort in the electronics industry to deal with the fact that Moore's law isn't giving us the densities quite anymore. And so the way we get densities now is we stack things on top of each other. And this has been happening for the past 5 years very aggressively, not just in supercomputing, but also lots of consumer devices now are stacked. Lots and lots of consumer devices. Any GPU, for example, you buy these days, very much the HB RAM is stacked. So lots of 3D electronics have kept things moving. And the last thing along the lines, which has really just started phasing in now, we can see with the Dragonfly networks, is to go to silicon photonics, or in other words, put more and more photonics, more and more fiber optic connections all the way to the chips, more and more types of fiber instead of using electrical signals to connect things. And that's been, that for the Dragonfly network is going to be a huge part of this. And the idea is to keep moving more and more of this stuff closer and closer to the chips. So we've had these kind of quantum jumps keeping things going, but it has been a battle. And so what else is it going to be? What other technologies will we have after this right here, after these mature, to keep things moving? Because we said we can't count on Moore's law anymore. Well, we'll look at a few of them, but mostly for you right now, and as of the next 4 or 5 years, where we do have good roadmaps, you're going to see that the battles that are being fought right now are different than the old ones. In the old days, it was just crank the clock speed up, and try to get as many floating point operations as possible done by the CPU, because that's what the hard part was getting good floating point performance out of the CPU. Well, I won't go through this list one by one here because we are getting a little tight on time. For those of you interested in the future of computing and supercomputing in particular, I'm glad to come back and answer questions about this. But the battle's changed now. Now it's about power, keeping the machine from melting. Now it's about minimizing the data movement or improving the data movement, because data is sloshing back and forth over these massive parallel machines so much more this time is not spent waiting for the CPU to calculate. The time is spent waiting to get the data to the CPU. So these are the issues that are being waged. The battle's being waged right now as these exascale machines come online. This last one there probably deserves at least a mention. Reliability. When you have millions of cores in one place, reliability becomes an incredibly difficult thing to solve, because you might think that a mean time between failure of, let's say, 10 years. You might think if a CPU core lasts 10 years, that's pretty good, right? That's reliable. But if you put 10 million of them in one place, all of a sudden your machine has cores breaking down, on an hourly basis. And so that becomes difficult to get any application to be able to run reliably unless you start putting in very expensive fault tolerance mechanisms that are incredibly expensive in terms of performance and hardware. So reliability is a big one out of that list. But anyway, I said, what does the future hold? Well, this is something we won't get into in any detail this week, although I'm happy to entertain discussions, offline and during Q&A. But the architectures that we've all been talking about so far have all been CMOS, or basically silicon electronics, standard electronics running. We say a von Neumann architecture. It means your normal computer today is some registers that go out to memory to grab some values to compute on, and they put stuff back in memory. That's the way every computer works today, whether it's an ARM or an AMD or an Intel, or something you might think of as even more exotic. They're all pretty much silicon-based electronics that run the standard kind of computer design. On the other hand, maybe we can, now that Moore's law is shutting us down here, maybe we can go to something beyond silicon, beyond CMOS, like graphene-based computers. And there are lots of efforts being done there. They're all pretty much laboratory today. Nobody's building any fabrication facilities that do anything besides silicon just yet. But that's the hope. The hope is that we can move, as Moore's law peters out, we can move on to something besides silicon. On the other hand, maybe we can go in a totally different paradigm of computing altogether. And it won't be silicon-based, but it also won't be anything like we think of as normal computing, which is going to memory and grabbing some values. Quantum computing is the best example of that. Quantum computing is a very dynamic field right now. And the hope is, again, to go with a completely different algorithm paradigm as well as hardware paradigm. And lastly, there's a big effort right now because of the successes in AI and data analytics to build neuromorphic computers, which use the electronics we know how to build so well. So we're very good at making silicon electronics, but maybe instead of building things like computers, we build them more like a human brain architecture. And neuromorphic computing is big. I could talk about this a little bit more in our big data workshops where it's more appropriate, but there's a lot of things going on right now that are very exciting there. Here at PSC, we have, for example, NeoCortex, which is a Cerebrus computer, which has trillions of transistors that are laid out to be strictly for doing AI, for doing tensor-based kind of computing. If you're interested in these kind of things, we can have some discussions offline or in the Q&A sessions. But quantum computing, if you're interested, the best place to get started by far, I find, is the American Academy of Sciences Quantum Computing Report. It's great. It's written for somebody that's just got basic freshman level engineering kind of education. It doesn't assume quantum mechanics or anything else in any great detail, and will give you some idea of the challenges that are going on there. If you're interested in neuromorphic computing, lots and lots going on there. It's really exciting. But if we do have to make a shift, it won't be the first one. We've just gotten very spoiled. Computers have went from being mechanical devices, mechanical relays, to vacuum tubes and transistors. We've just gotten very spoiled in this integrated circuit era because it's lasted so long. So we keep thinking the computing just is integrated circuits, and that's not true. It has been other things in the past, and we will move on to something in the future. But I think that it is important to keep a perspective on it whenever we do think of how great and evolved our computers are, to recognize that we're trying right now to get these exascale machines online. An exascale machine is going to have somewhere between 20 and 30 megawatts when it comes online this coming year. And meanwhile, it's going to be able to simulate the human brain in real time. That's one of the project goals I mentioned earlier, right? And the human brain takes about 20 watts to run. So it gives you some idea that there's a lot of room for improvement. So on the architecture front, there's lots and lots of room for us to make improvements, although it might take a big paradigm shift. Now, one of the things that in a computational physics course that I teach, there's a pretty good book that's actually used mostly in the course, the intro course that's taught before mine, Neumann's computational physics book. And it's a great book, has tons and tons of great algorithms in it, good approaches to do things. And it is Python-based book. And one of the things that he says in there is, because I like the book, is very pragmatic. It's very much about, hey, this is stuff that will really work for you, in the real world. And he says in there, I think the very telling statement there, that with the kind of Python algorithms it's mostly serial stuff, and it's mostly Python. He says, we need to stick to things that are about 1 billion operations or less to do the kind of work we're doing here in this book. But it's an introductory book. It's meant to give people an idea of how to do the algorithms. It's not meant to teach them how to do leading edge science. And so you look at that and you say 20 billion operations or less, And then you look at our exascale computers, which are going to do a quintillion operations, and you say, geez, there's a difference between 20 billion or a couple billion operations and a quintillion operations per second. It's like 10 or 12 orders of magnitude. I'm a physicist, and even as a physicist, we like to think as physicists we're used to, not being daunted by large orders of magnitudes, right? What's 10 to the 42? That's no big deal, right? But this still catches me off guard when I think about it. The fact that a lot of people are doing desktop computing that's 10 or 12 orders of magnitude slower than what we're doing on exascale machines. I mean, that is an enormous gulf. As a matter of fact, when I first saw that quote, in my head, I'm like, I think that's bigger than like the difference between people and early computers. And indeed it is. I mean, this is a bigger gap. If you're sitting there doing Python on your laptop and that's the extent of what you're doing right now, you are at more of a disadvantage than a human being against a 1960s IBM computer. That's less of a gulf. These two are closer together than you are to an exascale machine. And so I hope that gets you excited, because you're going to learn how to do parallel computing and make an enormous jump of not an order of magnitude or two, which is in my mind transformative itself, but 10 orders of magnitude. It's ridiculous. But I hope you also appreciate that, again, laws of physics are drawing this. So do not get convinced that engineers or software people are going to save the day because they're going to become enamored with serial computing again, and your simple serial codes are going to just start running faster, because we can see that's not an option. They weren't driven this way because of philosophy. They were driven this way by necessity. But you're going to learn how to bridge that gap. So to summarize everything we've talked about once again, it's a slide we've seen and we'll see it again. OpenMP is the domain of learning how to program these multiple cores. We're going to get onto that right now. OpenACC is learning how to program GPUs. We're going to do that tomorrow. And before the end of the week, you're going to learn how to use MPI to scale that up to as large as you want. So, okay, let's catch up on questions here before we move into some actual real programming here instead of just talking about it with OpenMP. So we had a number of questions come in here. Let's see. So Python, we'll come back to Python and Cython, and the problem with Python, I mean, the limitation with Python is the GIL. So for those of you that are really Python proficient, you know about the GIL and that lock. We'll talk about with OpenMP locks, and that really is the bottleneck for performance of multi-core in Python, is that there's the GIL at least in CPython, which is what people practically use because it's where all the library. We'll come back to that with OpenMP. So it's a good point here. We'll come back with OpenMP in more detail. Let's see. For supercomputers, the architecture is the same for all the nodes. Well, I think with the Exascale alone slide that I had up there, I think you could see that the node. So let me back up to that real quick, because it just where are we here? I should just jump to it. Close. There we go. So, I mean, here are the different node types that you can find on the upcoming Exascale machines, and you can see I mean, in some sense, they're all very similar, and it's nice, and that the OpenMP technique we're going to learn, for example, would work very well across all of these, and so with OpenACC. But in another sense, they're all different, in that this is two Intel Xeon CPUs and some Intel GPUs. These are EPYC CPUs and Radeon GPUs. These are EPYC and Radeon. These are EPYC and NVIDIA GPUs. So to some extent, they're very similar, and depending on your perspective, they're very different because they're all different hardware. I think of them. I look at these and think they're very, very similar, just because the same programming techniques that I would use for any one of them apply pretty much to the rest. So, but this is how different nodes are on the Exascale machines, and it's not that different from any data center. So if you look at an Amazon data center and you look at AWS services and the kind of nodes that you can grab from their cloud, this is the kind of differences you expect to see. Different versions of GPUs, different generations of CPUs. Let's see. So you have to build in error correction reliability from the programming. So fault tolerance is a really interesting and intimidating topic. And fault tolerance on the biggest machines these days, yes, is up to your application largely. There's just two different architectures. chip to change its microarchitecture. I'm not sure which chip you're referring to. You'd have to show me. If it sounds like it's got kind of FPGA capabilities, that is a thing. And typically, the price you pay for having FPGA capabilities, you get great flexibility, but the performance is a lot worse because that flexibility comes at the cost of making the coupling between the different components have much greater latency. But you tell me a particular architecture. TPU. So TPUs we'll talk a little bit more about when we talk about OpenACC and GPU programming tomorrow. TPUs are, well, actually we won't talk about it a whole lot there. We talk about it a whole lot more in the big data and the machine learning course, because TPUs, which are, so Google decided that when they saw GPUs dominate deep learning and machine learning for reasons that, the simple answer is because most deep learning is matrix multiplication. And GPUs are fantastic at matrix multiplication. And so Google looked at that and said, that's great, only we don't want to spend all of our money buying a bunch of GPUs just to do matrix multiplication. So why don't we just build our own hardware that's really great at matrix multiplication? And that's what a TPU is, a tensor processing unit. And so Google's AI, a lot of their AI efforts are to use their own accelerator called a TPU. But that is strictly for deep learning and machine learning, where it's very interesting, very effective, but it's not as general as a generic GPU. So they're not used as much in generic scientific computing. Possible to reduce power consumption by using photons instead of electrons? Absolutely. And it's one of the reasons that photonics is such an enticing technology, and there's a big push to move to it, is photonics is much more power efficient. And if you can do it at the chip level, it's even more attractive, but of course, even more difficult to do. But that is the push. And so that is the reason, my next slide here. That's why photonics is a very, very interesting area of research, but it is, it's still mostly research. Well, no, I should say, there's lots of probably, we can see that the networking stuff has definitely moved to photonics. On the chip level side, it's still mostly in the lab. Spintronics. Yeah, spintronics is mostly in the realm of a lot of quantum computing. Some things that so small electrons just tunnel across transistors. Yeah, it's starting to happen. And not, somebody mentioned earlier, quantum tunneling. Quantum tunneling isn't a concern and an effect, but even just old school, leakage, current leakage, and parasitic losses have become really considerable on chips. So the fact that electronics have become really small has introduced a lot of physical issues and performance issues. And it's one of the things that sucked off the performance improvement. So even though Moore's laws continue, that our chips are much, much smaller than they were 15 years ago, our clock rates aren't better. That's, again, one of the reasons is the leakage currents and everything add into that heat. Okay, so I think I've caught up on questions. That means we can move on to actual get our hands dirty talk, where we're going to start programming. And OpenMP is the way we're going to start doing this stuff. Because it's very approachable. It's going to be a foundation we're going to build things on as we move forward. And we have until, I believe, our lunch break. And Tom or Steve confirm our lunch break is 12:30 Eastern time. Is that right?
1:30.
Oh, it should be 1:30. Yeah, we're not past it. Yeah, 1:30. That's half past the hour, I should have said. So our lunch break is still half an hour away. So we're good. We're not that far behind schedule, which is good. Okay, but not a point of concern. Keep the questions coming, especially now that we're getting into the technical stuff. This is where make sure you do understand what we're doing. Okay, so here is our OpenMP. This is the first technique we're going to use. It's going to be very effective, and I think you're going to find it to be surprisingly friendly to use as well. And OpenMP, the definition of it is a directive-based standard to allow programmers to develop threaded parallel codes on shared memory computers. Well, some of those words we know because we just talked about them. But maybe the biggest word in there, most important one, we're going to unpack this sentence as we go, is directives. So directives are going to be the real magic recipe to let us be so effective here with OpenMP and also tomorrow with OpenACC. That's why I said if we get a little bit behind schedule with the OpenMP stuff, it's okay because we'll get it back with OpenACC tomorrow because they both use this directive-based philosophy because it's so effective. And directives is the idea that if we can just give the compiler some hints, that maybe it can do an awful lot of the actual parallel programming for us. And with shared memory computers, that's actually a reasonable goal. Shared memory is simple because everything's just looking at the same memory. So the threads, as we'll see, need to cooperate in some pretty trivial ways. And so this can be very effective. Well, it is very effective. It's been used for decades now very effectively. So directives are this idea. We're just going to give some hints to the compiler. And again, as I've said, tomorrow, we're going to benefit from this because it's going to give us a big head start. OpenACC also uses a directive-based approach. So we're going to save an awful lot of time. We'll get back from our packed OpenMP afternoon today. Now, there's some huge advantages from this. First of all, we're going to be able to stay at a very high level. The directives we're going to add into our code are not going to be hardware specific at all. We're not going to have to get low level and worry about whether operating system has P threads. That's one way of doing threading in operating systems, or something else. It's going to be very high level. We'll see that as we do examples here. Another thing that's a pleasant surprise for a lot of people is that we're going to add these directives in, but our serial code is still going to be left untouched. Potentially, it can just sit there. Our original serial code can sit there and still live. So, for example, if you take and go back what you learned in this workshop and go back and apply it to your code with some colleagues, and your colleagues don't understand anything about multi-core programming or OpenMP, all they're going to find in the code are these kind of these directives that they can ignore. The original serial code is still going to be there and be perfectly functional. So we don't have to fork off a separate code. And that is a wonderful advantage. So we're going to have the same code. You can compile it and you can say, use the directives and be multi-core, or ignore the directives and just be a generic serial code. Now, the price you might think to pay for these kind of nice features is it's going to be less efficient, because that's often the price you pay to have life be more convenient for you, is there's a huge efficiency trade-off. And that is not at all the theme of this week. The theme of this week is to let you write codes that are going to run, you know, those 10 orders of magnitude faster than what you're doing on your laptop on an Exascale machine. We're not going to do anything this week that's going to be inefficient just to make life easier for you. So take that as a general principle. It's going to apply to everything we're going to learn this week. So if at any point in time something seems very convenient and nice, and you're thinking, yeah, but that's going to cost me performance-wise, that's not the case. That's nothing. We're here to learn how to use supercomputers efficiently, how to use machines that cost tens of millions or hundreds of millions of dollars potentially, and they don't want to hear about how something saved you a couple hours of programming time. So, you know, it was worth being slow. No, you want to run on the big supercomputers, for example, they want your code to run fast. But also even on your laptop, these are things that are going to run, you know, orders of magnitude faster than if you did them in serial. So everything's efficient, including this OpenMP directive-based approach. It is perfectly efficient, as in it costs us zero overhead to use this. It's going to be very, very portable. Everything we're going to do here this week, but certainly with OpenMP, is going to run on your laptop. It's going to run on bridges. It's going to run anywhere you care to take it without you having to change one byte of the source code. So everything is going to be portable, and it's going to perform well. Where, you know, as well as the code performs on your laptop, it will scale and perform that well on bridges, or vice versa. And this last thing here is probably the most important one, although you might not appreciate it yet since you haven't done much or any parallel programming, and that's that we can attack our code incrementally, one loop or subroutine at a time if we want. So we can go in, find the part of our code where most of the time is spent, and that's not uncommon. If you take and throw a profiler, which is a nice tool I'll talk about later in the week, profilers, but there are tools out there that allow you to figure out where the time is spent in your code. Although you might, from just intuitive knowledge of your own code, you might say, hey, these two loops right here where all the time is spent. And you can go in and just parallelize those two loops and completely ignore the rest of the code. And given in the real world, there are lots of codes that are, say, 80,000 lines. And meanwhile, the part of the code that does all the number crunching you care about might be 200 lines. It is awesome to have something that's incremental, because you don't have to go digging through 80,000 lines of code. You go to the kernel of your code where the 200 lines where all the number crunching's done, and you speed those up, and it's a big win. And so this incremental approach is fantastic. It's not a given. Don't take it for granted. We're going to find with MPI, we don't have this luxury, but with OpenMP, we do. Now, the compiler support for this is very solid, because OpenMP is an incredibly important widespread standard for a long time right now. So everybody takes it seriously. If you don't support OpenMP, you're really, not really a compiler. As a matter of fact, there are more I should add on this list. Like I should add Clang, because we have that on here now on bridges. But anyway, all serious compilers support OpenMP. Some of them are more serious about keeping up with the latest versions of the standard than others, but all the core stuff that we're going to talk about this afternoon, the basic stuff, which is the 3.1 and earlier versions, all of them support it. So that's very basic. OpenMP, as we'll find out in the next slide, I'll say, continues to evolve. So some compilers haven't caught up to the 4.0 or 5.0 stuff, but we're not going to talk about that until tomorrow for accelerators, basically. That's the stuff that is for GPU computing. But all the stuff we're going to cover today for multi-core computing, which is what OpenMP really excels at, this stuff has all been very, very well implemented in any serious compiler. And again, it's an open spec and it's an open standards organization. So you can go to openmp.org and find lots of resources there, not just, for example, a cheat sheet, but you can find a nice cheat sheet there. Might be useful for you for doing our exercises, although you'll find enough information in our slides, but it's not bad to have the spec next to you when you're working with something. It never hurts. And so that stuff's all out there. Okay, let's look at our first hello world program in OpenMP. And here's how we would say hello in parallel. We would stick around our hello world program. We'd say, do this in parallel with a parallel directive. It's that simple. Now, the parallel directives, in again, C and Fortran are the standards for OpenMP. The directives, and this will also apply to the OpenACC stuff tomorrow. The directives are very, very simple syntax. In C, they basically take advantage of the pragma directive in C. So in C, you know, there's this pragma directive that basically says this is a compiler-specific extension. It allows you to do anything that's not standard. Well, OpenMP takes advantage of that and says we're going to tack our whole standard on here by saying whenever we have pragma OMP, we can have directives here that are OpenMP directives, or your compiler can choose to ignore this stuff. So a compiler that's ignorant about OpenMP or you don't want it to use directives can just ignore these pragmas. A compiler that does care about this stuff and wants to parallelize your code can pay as much attention as it wants to. And so that's how the pragmas work in C. Now the pragmas apply to the next block of code. In C, a block of code is very well defined, right? It's, if you got a for statement, it's the thing that's in the for statement. You got an if statement, there are blocks of code. So in C, a block of code is a very basic concept to programming. And you can always make a block of code, like I didn't have to do it here, but I just made this a block of code by sticking some braces around something. You can always make a block of code. Usually you'll already, the braces of the block of code will already be there. You'll apply directive to, but you can make a block anytime you want. So that's as complex as the syntax is for those directives. Now Fortran doesn't have the same notion of blocks of code. In Fortran, you don't have blocks of code. So it's the same directives we're going to find ourselves using as C, only we'll have to put an end directive for each one of our directives to specify the end of the next block of code. So in Fortran, we'll have the very same directives, but an end directive. And in Fortran, we don't have a pragma statement. Instead, in Fortran, these things actually look like funky comments, right? A comment in Fortran is bang, right? And so in this case here, we've got bang $OMP. Anytime a compiler sees bang $OMP, it is allowed to either ignore that because that's just a funny looking comment, or if it's an OpenMP aware compiler and you tell it to, it can start trying to do things with these directives. So this is the magic of directives, is they either look like funny comments, basically, that can be ignored by the compiler, or they can be activated and do useful things. In our case, it says run this in parallel. So when we run this in parallel on 4 cores with 4 threads, it spits out hello world 4 times. Each one of our cores, each one of our threads is saying hello to us. So this is basically it. Or to reiterate what I basically said, here's the same thing, reiterated in a different slide, is we've got begin and ends in Fortran, and C, we just use the next block of code. They're pragmas or comment statements. Oh, and by the way, here's an important point, is I find it useful and actually quite sane to indent the directives with the code. So if we got nested for loops or something, I indent the directives just because it follows the code. It makes sense. But for reasons that I've never really agreed with nor really fully understood, there's a long-standing tradition. A lot of people like to make sure that directives are always aligned in the first column. And you'll see this not just in parallel programming, but you'll see a lot of people think and see that, for example, all defines need to be in the first column, and they're always aligned in the first column. So you'll see a lot of codes where everything's always aligned in the first column. You'll see me following the indentation. I think that's becoming an increasingly common idiom that people use, but it's just style. It's strictly stylistic. Compiler doesn't care. So I'll indent them, but don't get confused if you go look at some other sample codes and people always left align these things, the directives. It's just a stylistic thing. Let me see, put some questions here. Okay. Yeah, Tom is offline for a second, so I'll pick up any of his questions, but I think we're past most of the logistics stuff anyway. Let's see. How is the efficiency of OpenACC compared with native CUDA programming? We'll get on to that in detail tomorrow. It is excellent, and I have some studies and proof and whatnot. I don't expect you to take my word for it because it almost sounds too good to be true. And I'm always suspicious of those kind of things. Like I say, I'm after performance, not promises and productivity. So I will give you some proof that OpenACC is CUDA efficient. But we'll save that topic for tomorrow. But that's the bottom line: is OpenACC trades off nothing against CUDA. And by the way, it can interact with CUDA. You can mix and match OpenACC and CUDA. We'll get into that as well. Can you name some features which are missing in Visual Studio for OpenMP? I can if I think about it, because I've run into them. I'm drawing a blank at the moment, but they're not major, but they're also annoying. Let me get back to that. I've personally run into that. It's also documented pretty well too. You could Google for it if you don't have the patience to wait for me, but I'll have to think about it. There are some things missing. It's annoying. It's not a deal breaker. You know, people still use OpenMP widely, very widely with Visual Studio, but it's just their support for it, their commitment to it is not what it should be. Let's see. What compilers do I need downloaded into my computer? None. We're doing everything on Bridges, so you don't have to worry about any of that. Later on, you can choose whichever compilers you want for OpenMP. I gave you a long list of compilers you can use. You can download GNU or get a license for Intel, or you can grab Clang, or you can do whatever you want. Pretty much any compiler is capable, but we're all going to use Bridges and not have to download anything. Are you times when you run OpenMP and print out is messy? Yeah, we'll talk about that as a matter of fact. So yeah, doing output from a bunch of threads is a concern. You know, how do we keep things ordered and sane? And we will look at how to manage that. Why is the string displayed 4 times? Well, because each one of our cores is saying hello to us. So we're running this in parallel on 4 cores. So each one of our cores is saying hello. That's what makes it parallel. If we got rid of the directives here, it would just say hello once. So we are running it parallel. Some Python algorithms use num threads as a keyword argument. Using so when Python is using number of threads, so libraries in Python are all written in C or some Fortran for reasons that we're going to get into, because C and Fortran can be multi-threaded, and Python by default cannot. And so you'll see, yes, it will make a lot more sense to you when you're using C libraries in Python. It will make a lot more sense to you, and you'll be able to write Python libraries that are multi-threaded using C or Fortran when we're done here. Let's see how to run these. We need to specify different serial code. We'll get into that in a moment. Not really. You just need to specify num threads actually, but we'll get into that. We'll definitely step through it. How do I port Bridges program on my laptops or on locally? You can copy them over any way you like, SCP, or however you like to move files around. There's a million methods. There's user guide has a bunch of those methods listed. I like to use SCP to copy files around. On Python, people use multiprocessing. Well, multiprocessing, so this is good. You're going to have a much better understanding. Python, because Python can't do multi-threading, it can do multiprocessing as the MPI style of programming, multi-spitting off, so Python threads, as we'll understand, so we'll come back to this, will make a lot more sense. These are all good questions about what Python can and can't do. Because Python can't do multi-threading, it can't share memory, but you can spit off multiple copies of a Python program like MPI does. Now they're not sharing the memory, but they have multi-processes, not multi-threads, multi-processes. This will make a lot more sense as we go along. And so in Python, you have to use multi-processing because you can't do multi-threading. But again, it'll make a lot more sense once we cover these topics. Can you iterate over the cores, which core prints out hello world core num? Yes, we could have cores actually have numbers assigned to them if they care about it. Many times we don't. We'll come back to that at the end of the MPI talk this afternoon. We'll start using core numbers explicitly, because most of the time you don't care. You don't want to worry about how many cores there are. You just want to use it, your code, whatever machine it's on, just use however many cores are there. But we could say hello from core 1, hello from core 2, hello from core 3 if we wanted to. And we'll get to that by the end of today. Okay, so the older way of doing this, was back when things first started to go multi-core, well before things were forced there by our current crisis. Back in the 70s and 80s, in particular, in the 80s, multi-core workstations started to become a common thing. And the standard Unix way of dealing with threads was pthreads. And it is a low-level way of dealing with it. It was kind of the first pass at doing this. And it is quite painful. And the more you do it, the more annoyed you get, because you spend all your time writing boilerplate code instead of actually trying to do your multi-threading algorithm. And so pthreads, to do this hello world program, looks like this. And it's nothing we couldn't go over in 10 minutes and I couldn't explain to you, but you can see it is a combination of things which aren't nice. First of all, it's a lot more mess going on in here. Second of all, it is now no longer serial code. It's not like with OpenMP where the serial code's still there. This is now a dedicated threaded code. So anybody that doesn't understand P-threads would be very annoyed with you because they don't understand the code anymore. Whereas with OpenMP, we can say, just ignore those directives and just your serial code's still there. So it's a big difference. And it's the reason why the world moved on to OpenMP is that we had to change the structure. We weren't gaining anything in performance from it. We were just gaining a maintenance, issue. And we now have, separate sections for the code, for the serial and the P-threaded part. And it only gets worse. When real codes aren't just hello world, they have lots of stuff going on and it only gets uglier. So this is why OpenMP came along. Now, before we start talking and throwing around the terms threads and processes, it's important we understand the difference between the two. As a matter of fact, the Python question I was kind of half addressing right there was just talking about this. There is a big difference between a thread and a process. And the big difference is that processes are completely independent programs that do not share memory at all. As a matter of fact, they don't even share memory. They both think, for example, if we start two processes on your computer, two separate programs, they both think that they have their own byte 0 in memory and their own byte 1. And so if this process goes and changes byte 0 in memory, this process over here has its own byte 0, has nothing to do with it. The memory manager at the hardware level makes sure these things are completely isolated from each other. So if this process crashes terribly, it has zero effect on this process or anything else on the machine. So processes are completely independent. And indeed, when you bring up Task Manager, if you're in Windows, or PS, if you're in Unix, and you bring up all the processes, you can see all the processes. If you kill off one process, it has no effect on another. And if a process crashes terribly, it shouldn't affect the rest of the machine at all, if the operating system is at all reasonable. And so processes are completely independent. They have their own separate memory spaces. They not only don't affect each other, they can't even affect each other unless they want to start sending messages back and forth explicitly using something like MPI. So otherwise, they don't see each other. If this was a weather map, for example, and this weather map was running here, it can't look at the weather map over here. It's totally isolated. And that's processes. And that's a good thing because it keeps one bad program on your machine from crashing the whole machine. On the other hand, what we work with OpenMP are threads. And threads are in a single process and they always share memory. So with threads, the different cores that are working with different threads are all sharing the same memory. So when they look at array B, they're all seeing the same array B. If this core running this program over here changes array B, this one over here is going to see that same change in array B. If this core crashes and messes up everything and takes out memory, this core crashes too. And so with web browsers, for example, web browsers used to be written so that they were all multi-threaded. You'd start up a web browser, it would be one process, and then each tab would start up its own thread. And because all the tabs were sharing memory, it was nice and efficient in that, the things that were common between web pages weren't reloaded in memory. And so that seemed a nice way to go. Until the modern web came along. In the modern web, you've got all kinds of nasty stuff going on web pages, whether it's just terrible coding or whether it's malicious type of software, so that threads in their own pages would crash all the time. And when the thread crashed, it could bring down the whole browser. And you get very annoyed if you go to some bad web page and all of a sudden all your web browsing goes, your other 15 tabs you had open all just crash and disappear. So now web browsers instead said, well, you know what, it's less efficient, but let's move so each tab is a separate process. So now when that web page does something really dumb or nasty or malicious and we have to shut it down, only that web page goes away, only that tab goes away, and the rest of the browser can survive. And so if you look at a modern browser now and you pull up your process PS or you look in your task manager, you'll see each tab is typically a separate process. So it gives you some idea that two different things are between a process and a process with multiple threads. This is also a process. This is one process with two threads. These are two processes with one thread apiece. And so that's the difference. And so when we use the terminology today with OpenMP, we use OpenMP to run multiple threads in the same process. And so when we bring up more threads, they're all going to continue to work on the same chunk of data. And that's typically in scientific programming what we want. We've got our weather map here, and we want to have multiple threads so they can work on the weather map simultaneously. This is exactly what we want. And this is what threads are versus what processes are. So it's an important distinction here. And let me see if we've got questions about it, because I want to make sure everybody gets that. MATLAB's parallel tool is for processes, not threads. MATLAB does both, although I've used it. The parallel toolkit explicitly does multi-processes to really do things in parallel, but it does multi-core stuff just fine at the not parallel toolkit level. So it's doing both of these things. Hyperthread, HT, is that standing for hyperthreading? Let me see, I think, yes. HT is a different thing. It's a way to tell operators two cores. So yeah, you can get a little bit, hyperthreading is a important term to understand. Hyperthreading is where Intel first originally said they noticed with multi-core processors that a lot of times that the cores weren't busy because they were, a lot of programs have terrible memory latency issues. They go out and fetch stuff from all over memory. And so the cores spend almost all their time waiting for data to be fetched. And so Intel had the clever idea that, hey, what if while this core was waiting for something to get from memory, what if it loaded in data from another thread that's out there waiting? It could pretend to be two cores. And these threads, so if we had 8 threads waiting and we had a 2-core, 4-core machine, we could try to run all 8 threads at once. Whenever one thread gets stuck waiting for memory accesses, we'll switch over to this other core, this other fake core. So it's called hyperthreading. So Intel could double the number of logical cores basically by doing this hyperthreading thing. And a lot of other people kind of adopted it since, and then people, sometimes it works well and sometimes it doesn't, so people could turn it on and off in machines and whatnot. But hyperthreading is a way to pretend you have twice as many cores as you do, and your software hopefully works well with that. On bridges at the moment, we have hyperthreading disabled generically. Sometimes we have requests to turn it back on. Some software uses it effectively. A lot of scientific software doesn't. It's a little bit of an overhead handicap. So it's one of those things you can turn on and off. Typically in BIOS, it's a little bit painful to turn on and off typically, but that's what hyperthreading is. It's a way for one core to pretend to be 2. Can the core be both an individual process or a thread in a process? Physically, a core is the actual electronics. A core is the physical chip. And a core can run a thread at any point in time. A core is running a thread. That thread can be from a process that only has 1 thread. It can be from a process that has 2 threads in it. It can be one of those threads. So a core at any point in time can be running a thread of code. And of course, they can switch back and forth in your laptop right now. If you look at how many tasks there are going on, there are probably 100 plus. So things get time sliced and broken up all over the place. When we're talking about our scientific codes, we're going to mostly consider that your code's hogging the whole machine because that's usually how you want to run a simulation, but threads swap in and out all the time. Can Julia do multi-threading? Yes, Julia does multi-threading pretty well. So don't start trying to run examples just yet because I haven't showed you everything. So we'll get to hello world and compile it because I haven't shown you the OMP num threads thing. Somebody else just told you about that. Yeah, so we'll get there. You're a little bit ahead of me. Let's see. Test.c does not have an OpenMP. No, it doesn't. So that's not. We haven't really. So these are just some simple examples here. Don't get too serious about them yet. I haven't actually put them in your directory. Just to clarify, Python can only do multiprocessing. Yes, Python natively can only do multiprocessing, but Python uses a lot of libraries written in C and Fortran which use threading, so it gets to be a little more nuanced. But we'll come back to that probably after we cover some OpenMP. I can explain it in a more meaningful way. Let's see, I'll skip the OpenMP pragmas. Yeah. Okay, so yeah, so those of you that are trying to run and execute my examples here as we go, a little bit of patience. At least let me get to the first exercise break or whatever before you start trying to compile and run stuff, because I'm giving you everything you need to know just yet. Okay, so the idea is that you have a master thread when you run a serial program that starts, and if it has OpenMP stuff going on in it, it can launch other threads, and this can be a very dynamic thing. Again, think of your web browser. You open tabs, it can open more threads, and when you close tabs in the web browser, it can kill them off and kill those. So threads can come and go as things run along, and that's the way we're going to do our programs here. You can launch a bunch of threads, and if you launch more threads than you have cores, that's absolutely fine. It's just the cores will take their time getting to those threads. Just like I said, right now, you probably have 100 processes running on your laptop between all the nonsense that goes on in the background, and that's perfectly fine. It swaps back and forth between them. So again, this is my web browser example right here. You can launch threads and you can kill them off, and tabs can open more tabs and kill them off. And this is a typical application threading with something like a browser. But there are different ways you can use threads. For example, video game consoles very often have a thread assigned to a specific core that lives for the whole game. and maybe even different hardware devices. So a video game might have, video game consoles, by the way, are all multi-core these days. Everything's multi-core, right? Your video game consoles are multi-core. And a video game console might have a thread devoted to the game physics. It might have a thread devoted to working with the GPU for rendering stuff. It might have a thread devoted to the AI for the NPCs in the game. And these threads are all running independently, and they might talk between each other, communicate with variables because they're, they need to, but they're independent threads and they run the whole game. They don't start or stop. And that's a common type of application thread too. You start a thread and it's just responsible for functionality for your entire application. Here's the kind of threading that we're going to be mostly, and OpenMP can do all of these, but here's the kind of threading we're going to be mostly concerned with because this is most useful to people that do scientific programming. And that is the kind of program where you've got some serial stuff that doesn't do anything important, and then you run into a big loop that does tons of number crunching. In our weather code, for example, we might have some simple serial stuff that sets things up and tells the user the code starting, but then it runs into the actual weather map, and it needs to do a big calculation here to figure out what the new wind velocities are going to be based on the last one. And so it has a big loop it hits, and this is where we want all the cores to come into play. So it hits our big loop. Now we want all 6 cores. We want 6 threads, to get to work on our weather map. And then it's done with that number crunching, and then it's just doing some trivial serial stuff, and that's fine. And then we come upon another section of our code that might be doing temperatures now, and that's a big loop. And so we throw our OpenMP at the big loops in our code, and we don't really care about the trivial serial stuff so much. This is a very common pattern in HPC. So this is examples we're going to start out with. We'll get the flexibility that OpenMP has to do anything later, but we'll start out mostly fixated on big loops that do a lot of work, because that for a lot of HPC codes, as well as other codes, but for a lot of science codes in HPC, that's what they do. So we'll start there. So we're gonna focus on getting our big loops to parallelize well, but then we'll come back to, like I said, this other stuff later. So that's what this slide says. Okay, now if this looks a little too easy here right now, we're just gonna throw these parallel directives in front of our loops, and they're gonna, compiler magically does its stuff, then great, we're done, right? We can call it a day. Better yet, why don't we just have something that just says, hey, compiler, do parallel for every for loop in the code or every do loop in the code? Why don't we just do that? And the answer is that with these directive-based approaches, the directives can do an awful lot of heavy lifting, but you still have to bring some human level intelligence to the code to recognize some potential problems, in particular, data dependencies and data races. And these are the 2 things that we as human beings need to recognize before we just willy-nilly throw directives, because these are things that can make loops not behave well when we parallelize them. So we're going to investigate what both of these are. But these are the 2 main issues that prevent us from just throwing parallel in front of every for loop. So let's look at data dependencies. We can cover these before we take our first break here in a few minutes. The way that loops are broken up in with a directive in front of them across the cores is very, very straightforward. It just takes and it divides up all the iterations in that loop amongst the different cores. So in other words, let's say we have a simple loop like this that goes from 1 to 10,000 or 0 to 10,000 here, and multiplies the existing values in the array by 4, right? So we just want to multiply this array by 4. We go over the whole 10,000 element array. If we have 10 cores, this is basically what the directive will do. It will say core 0's job is to take the first 1,000 elements. Core 1 will take the next 1,000 elements, and core 2 will take the next 1,000, right? In this way, our 10 cores should hopefully run this code 10 times faster. All they have to do is just go and break the iterations up, spread them out across the cores. And the directive manages all of this. And if it runs on different numbers of cores, the directive knows how to spread things out. So the compiler is smart enough to distribute the work as evenly as possible and make it work. And indeed, things should speed up by, you hope 10 times right here. Very simple, very straightforward. And that's all there really is to it. So for an awful lot of loops, it is that simple and it is that successful and that easy to apply. But let's say we have a loop like this, and this is a perfectly valid loop. There's nothing wrong with this kind of code. So we've got the same multiply by 4, except now we want to subtract the element preceding it in the array. So we multiply the array by 4, and then we subtract 1. Okay, and again, nothing wrong with this code, perfectly valid code. The only problem is now when we go to run this divided up over our 10 cores, we have a little bit of an issue here. And that core 1, core 0 can get started. Core 0 goes to town, but core 1, it wants to start with element 1,000. Only problem is it needs the value in array element 999. This is core 0's responsibility, is to calculate this one. So core 0 isn't probably going to get here for another 999 cycles. So there's a problem. Core 1 now has a choice. It can either just go ahead and use whatever value is stuck in here, but it's not going to be the right one, right? It hasn't been updated yet. Or it could wait till this gets set. Well, if you throw an OpenMP directive in front of here, it's just going to go right ahead and use the value that's in here. And your code is going to give you what's probably an incorrect value. You're not going to get the correct results that you want. Certainly not the results you would get from the serial code. And so this is the problem of a data dependency. There's a dependency with one iteration of the loop with another iteration. That's a dependency. And so this is a problem. It's why we can't just, just blindly throw directives in front of all the loops. Now, they're not hard to recognize, the dependencies, because the obvious pattern, if we've got an index here that depends on, inner loop. So the code's written like this. So anytime you see the loop index and an iteration from an index that refers to another iteration, you probably have a data dependency right here. So this is a clue right here. There's a data dependency. Anything you've got a pattern like this. As a matter of fact, these patterns are so obvious, the compilers will typically give you a warning message about it. So you'll get a warning. They'll go ahead and do it because you put the directive there, but they'll give you a warning. So it's very easy kind of pattern to recognize. The dependencies aren't subtle things that are hidden. So anytime you see this dependence, the indices, that depend on a previous iteration, you probably got an issue. If you've got a variable that's written and also read in the same loop, that's a sign there could be a dependency like that. So again, the compiler these days are smart enough, they'll probably give you warnings. You shouldn't rely on it. You should instead look at the code. But even if they give you warnings with OpenMP, it's going to go ahead and do what you tell it to do, even if it thinks it's dumb. So now, can you fix these? And the answer is very often, yes, very often. You can rearrange the code a little bit and get rid of the data dependency. Because data dependencies are not a new thing. They're something that's been bugging code for many decades. People have lots of little tricks and techniques and whatnot to eliminate data dependencies in different conditions. I mean, sometimes it's just common sense says, oh, I can just get rid of this, just rearrange the code a little bit and go away. But sometimes you can go and look at some bag of tricks that says, here's ways to get rid of different data dependencies. Sometimes compilers will even do it themselves if you allow them to. They can even rearrange the code a little bit. So there are lots of tricks to get rid of data dependencies. OpenMP has some capabilities to maybe get rid of them. And sometimes there is bad news. Sometimes the algorithm you've got just has a data dependency as a fundamental part of what you're trying to do. I mean, it's perfectly possible to write algorithms just one iteration depends on the next, and you're stuck. In which case, you either need to find a different algorithm or that part of the code isn't going to get parallelized. So that's but with OpenMP, you've got to recognize these. So when you start putting a directive in front of the loop, take a look and say, hey, does this iteration depend on some previous iteration? Okay, let me take a pause for questions here. Okay, the Python multi-threading thing. Python, especially C Python, cannot do multi-thread. It has multi-threading library, but it's fake because of the GIL. We'll come back to this later at the end of today. Python has this. We'll talk about locks later today. And Python has a lock, a global lock on the interpreter that prevents it from going threading. That's the performance issue with Python. So we'll come back to it. But Python can't actually do real threading. It has the threading library, but it doesn't ever run in parallel. It's fake threading. But we'll come back to that after we do some more threading stuff. So this data dependency problem happens to weather forecasting problem of boundaries, right? The answer is no, it does not. With the weather problem, for example, at the boundaries, they can both, you have to, when trying to think of the best way to say this. The weather at one point in time, when we're calculating the new weather, depends on the last. So if we're trying to calculate the weather for 1201, and we're using the data from 12 o'clock to calculate the weather at 1201. So if the core, I don't want to reload the whole talk to go back to that weather map. We'll have a better example of it later on. But the weather map does have a data dependency because when you're trying to calculate the weather at 1201, I don't need the weather value for core 0, or let's say core northwest, the core that's in the northwest part of the map, and the core that's in the southwest part of the map. The core in the northwest part of the map, when it goes to the south to get data, it needs the data from the last time step, which is already calculated. So when cores northwest and core southwest start trying to calculate the weather at 12:01 p.m., they do not need to wait for each other. They're using the weather from the last time step, which is already sitting there. Core 0 doesn't need the weather for 12:01 to calculate its weather at 12:01. It needs the weather from 12 o'clock to calculate the weather at 12:01. So when it looks south to get the weather, it needs it from the already calculated last time step. It doesn't need the new time step weather, so it doesn't have a data dependency. And that's very often the case. That's mostly the case. So data dependencies are the exception, not the rule. So it's not the case in the weather map, but it's a very good question. And I'll try to make that clear with the example we're going to use of our Laplace code, which isn't a weather map, very shortly. Oh, we're at our lunch break. I want to respect these breaks because I know people have other things scheduled in your lives. So let's take a pause here. I'll answer the pending questions, but those of you that have a commitment right now, you can go ahead and disappear. You're not going to miss anything but me answering questions. We're going to take a lunch break. I'll make a note on the lunch break. This is very important. We found it helps reliability for the Zoom session for me to reboot this machine. When I reboot the machine, I lose the Zoom session. So any chat that you do when I'm rebooting the machine, I don't see. If you just Zoom is dumb and the chat channel gets purged. So I'll ask some of the other TAs to tell me any questions that are missing, but I won't see your questions that you post while I reboot this machine. I'm sorry about that. Because when it comes back, your questions, I just won't ever see them. The history gets wiped. I'm going to reboot the machine after I get done answering the pending questions. But please be aware of that. If you think I'm ignoring a question of yours, I might not have seen it if you posted it while I do our lunch break reboot. Okay, so we're on our lunch break officially. I'm going to answer questions now. You can leave and be assured you're not going to miss anything. And we will start back here in an hour from right now at 1/2 the next hour. Okay, so let's see. Data dependency happens in the weather forecasting problem. The answer is, I think I just need to know. Let's see. Okay. If you override an array, so yeah, so if we with the weather map, if we were overriding the data, yeah, but if you're overriding the data, then you're already got issues as to what are using, how is even that core? Well, anyway, we'll come back to this Laplace code. We'll have some better examples. I can show you the details, but typically you don't want to overwrite one array when you're solving a problem like that. It does save space, but it also means now you got an issue where you've updated some of the elements of your array and some of the neighbors even within that same array, and some of them are from the current time step and some will be from the last time step. So typically you have a temporary array. But unless you're starting to do something like Gauss-Seidel, or well, we won't get into those details yet. Not well, everybody's not here at least. Let's see. Yeah, we'll talk about this. The next example we have coming up is a code that it's similar to the weather code, and it's an actual real code. It's going to be your exercise, and I'll talk about the data dependency issue in more detail there, and it applies exactly to the weather code. It's the exact same situation. So it'll become very clear where there is or isn't a data dependency with the weather code example when we do the Laplace code example. It's the next exercise. We're almost there. Is there a way to read and write specifically a scratch space with OpenMP? Well, you got to define scratch space there. Scratch space meaning what? George, I'm happy to mention the NVIDIA boot camp, and I assume it's one of their GPU programming boot camps I've worked with in the past. That's probably appropriate to mention tomorrow. So if you send me when we're doing GPU computing, so if you send me a message tomorrow, send a private message to me. So one of the exceptions of when to send a private message, send a private message to me tomorrow at some point when we've got a breather, so I can give it its due attention. I'll mention GPU hackathon opportunity. It'll make a lot of sense after we do the OpenACC material tomorrow. Local nodes, local memory. Well, local nodes is just generic memory. So if that's what you mean by scratch space, then whenever you're writing to your local, whenever your memory is memory as far as OpenMP is concerned. So if you're writing to your local nodes, with OpenMP, that's the only memory you have access to is your local nodes, local memory. So that is the only memory you have. So in that sense, everything is scratch space. With multi-threading and multi-processing, don't need multiple cores, right? You can run everything that we're doing here with one core, only it's going to be time sliced and not speed up at all. So that is true. As I said, your laptop right now is running 100 processes and it's fine, even though it's only got 4 cores, right? It's just time slicing it all. So if you do multi-threading or multi-processing and you only have one core, you're not accomplishing anything. You're just going to slow things down a little bit with some overhead, but they still should run and should give you the same result. And yes, we are going to learn multi-threads and multi-processing. Multi-threads is what we're running around OpenMP, and multiple processing is what MPI does. And if by scratch space you mean cache on a CPU, well, cache is managed by hardware almost by and large. I mean, there are some exceptions. There are some directives, machine language directives that try to manipulate, but cache is pretty much managed by hardware, which is pretty much because you want it to, because it'll hardware in real time figure out spatial or temporal locality. You have the ability in OpenMP, in OpenACC to use GPU cache. Explicitly, there's a cache instruction, but CPU cache is pretty much something that you can't manage explicitly. You can very much manage it by the data access patterns you have. So good cache use is incredibly important for performance on modern GPUs, or CPUs, excuse me, and GPUs, but CPUs. But it's because of your data access pattern that's going to manage it. It's not because of explicit instructions. It's the way you lay out your data. If you have 4 cores in your computer and you use OpenMP and specify 4 threads, then the same thing is the operating system is going to give you 1 thread per core, and that's going to give you a 4 times speed up, just like you'd expect. So yes, that is the case. There's a memory architecture change when you shift from OpenMP to MPI within a single node. Well, MPI uses multi-processes, not multiple threads, and so it does split things up into separate isolated memories, and it does change things. So it does, and we'll talk a little bit more about the implications of that, but not till we get to MPI, because otherwise we're getting ahead of ourselves. It's hard to have a meaningful discussion. But when we get to MPI, I'll be able to compare it to OpenMP, and we'll talk a little bit about that. Using hyperthreading, a single core can run 2 OpenMP threads. Yeah, that's exactly the idea. Is hyperthreading is, the idea is that one core looks like it's 2 physical cores, and then it can run 2 threads, switching back and forth. Is there advantage to use more threads than cores to make better use of cores? Typically, no. Actually, the overhead starts to get you, and this is a thing we'll actually test with our exercises here with our because it's easy enough to check. And we'll do some simple experiments, and you'll see that when you start getting more threads than cores, typically it's a little bit of it depends. Some operating systems are really dumb and the overhead can be enormous and it really slows down. But at best, operating systems that are good, it just doesn't slow things down, but you don't get a speed up. So typically matching threads to cores is the best pattern. And is it for sure that multiple threads will use each available core? It's not for sure. It's up to the operating system as ultimate boss. But the answer is in almost all normal cases, yes, unless there's something weird is going on your machine, or you've set it up weird, or the system administrator has some weird configuration. The operating system says these four threads are really busy and doing a whole lot, and I got 4 cores, put them on there. And you can also try to override things by pinning them in certain ways and everything. But by default, that's the same thing that should happen, and that's by default what the operating system should do. Is it should say these are 4 threads that have a lot of work to do, keep them going. Okay, let's go ahead and get started, because we do have a lot to cover, and I mostly am excited to get on to the first hands-on exercise, because that's where the rubber hits the road. But I want to pause here and make sure that everybody is clear on this concept right here of data dependency, because it's pretty much the most important thing to understand in terms of potential pitfalls in using OpenMP, and also in terms of understanding how fundamentally OpenMP works. It takes this loop right here and just divides up the iterations amongst the different available cores, and it's that simple. But because it's that simple, it also can run into this potential problem right here, whereas a core working on one iteration of data depends on an iteration that some other core might be working on. So this data dependency issue right here is something you need to be aware of. Keep your eyes open. And so we went over these slides right here and said sometimes you can just rearrange your code a little bit and get rid of them. Most of the time you can, and sometimes it's fundamentally you've written an algorithm that just is inherently serial, but you've got to catch those. Okay, but I don't want to scare you too much. I mean, plenty of loops don't have data dependencies, and then life is just this simple. I mean, this is just throw parallel for or parallel do in front of your loops, and boom, you've sped things up. So life can be and often is that simple. And to compile and run these, so a couple of you were anxious and getting ahead of me and trying to run these examples, and I applaud your enthusiasm, but beware getting too far ahead of me before I explain all the logistical details. When you have a compiler that's OpenMP capable, it usually wants to be told to start digesting those OpenMP directives instead of ignoring them. And the way we do that with the NVIDIA compilers is, oops, this should be NVCC. I should update these slides here. This was the old PG. This will still probably work, but this should be our compilers, the NV Fortran and NVC. And we use the -MP flag. NVIDIA bought the Portland group and renamed the compilers to NVIDIA compilers. So that this was the old Portland group naming, and it works exactly the same. It's the same compiler. So NV Fortran and NVC, but use the -MP flag. The -MP flag says, hey, start paying attention to these OpenMP directives. And when you do that, what gets spit out will be an A.out that's capable of running with multiple threads. Now, just because it's capable of running on multiple threads doesn't mean it will grab those threads at runtime unless you tell it how many threads to grab. So the standard way to do that in OpenMP is to set the environment variable. Those of you new to Linux, Unix type environments, these are just variables sitting around in your command shell that you can create and set. Well, we set this environment variable called OMP num threads. That's the standard name used for this variable. All OpenMPs will pay attention to it. And so if you say OMP num threads equals some number, that's how many threads it will choose to use. In some environments, in some machines, if you don't set this, it'll grab all the available threads. On most environments, if you don't set this, it'll default to 1 and your code will just run serially. But at any rate, you probably almost always want to manually set this to be sure. So you set this variable, you export OMP num threads equals 8. And then when you run the code, that's how many threads it's going to grab to run. And that's how many times roughly you should expect the code to speed up. So this is a very straightforward thing to do. Just remember your runtime setting is not, and your compilation is very flexible. Your code can run on any number of threads, and at runtime is when you determine how many threads it's going to run on. Okay, what happens when OMP num threads is set higher than available threads? I assume you mean cores, probably. If it's set more than the number of cores you have, then that's fine. It's just like, it'll just create a bunch of threads, but the cores will have to time slice between them. It's very similar to the fact that right now your laptop, again, has 100 processes running, even though you've only got 4 cores, and that's fine. It'll just swap between them. So you won't get a speed up by having extra threads. It may even, depending on your implementation, slow things down a little bit because it's swapping threads, which just adds a little overhead, but it won't break the code and it won't speed things up. So ideally, you set OMP num threads equal to the number of cores that are available in hardware. But setting it to too few won't kill you. It'll just won't use all the cores. Setting it to too many won't kill you. It just will introduce some overhead and not speed up beyond the number of cores you have. Okay, so it is that simple. Now, there's one other thing I mentioned when I said we had to beware of when we're implementing directives in OpenMP beyond the data dependencies, and that is that I call it data races right there that sum up a category of problems where we've got variables that are shared amongst the cores, but they're not arrays that we can just divide up spatially. So with our arrays, when we share them amongst the cores, we say, okay, this core is responsible for some section of an array, even if it's a one-dimensional array or a vector like we've got with our current examples. Some cores do the first 1,000 iterations and work on that part of the vector. Other cores do the next 1,000 iterations and work on that part of the vector. Well, instead, if we have variables that aren't vectors, and the term for these, and I'll use it repeatedly throughout the week, is a scalar. So if we have a scalar or a non-vector, a non-array variable, we have a scalar variable that's shared amongst the cores, we have a potential problem. Let's step through and see how that would work here. So let's say we have a simple little loop right here that does nothing but calculate the cost of paint to paint a bunch of rooms that we have. And it does that by going into each room's area, calculating each room's area by its height times its width. And then it calculates the cost of the paint by taking the area times the price per gallon. So it's a simple little contrived loop here to basically just sum up the cost of painting a bunch of rooms. No big deal, very straightforward. We can throw our parallel 4 in front of this and hope it speeds up. And if we do that, indeed, we'll find that the loop speeds up. But if we run this a bunch of times and pay attention, we'll find out that we don't get consistent answers out of this. We start to get answers that are variable and certainly not correct. And so, and by not correct, whenever you've got parallel code, it means not exactly what you get with the serial code, just to be clear. So we're going to find out we get an answer that's different from what we get the serial code, and it might not even be, it typically won't even be repetitive. It'll be variable. It'll change all over the place. What is the problem? Well, the problem is that we have a single variable, a scalar variable, right, a non-array variable that is shared amongst all the iterations and hence amongst all the different cores that are working on this loop. And the problem with that is that one of the cores, say core 0 comes in here and it starts getting to work and it sets area equal to height width for the first room it's working on, so room 0. And meanwhile, about the same time, core 1 starts working here on iteration 1000 and it sets area equal to the value for the room at 1000. Well, we got a problem here because we got one variable sitting out there in memory and we got a bunch of different cores setting it and resetting it every iteration. And so when core 1 or 2 or 3 gets down here to figure out the cost of paint and it goes here to use area, who knows which core last got done setting area. They're all setting area on top of each other. They're all stepping on top of each other and setting this one variable in memory. And so core 0 set this to what it thought was the right value, but by the time it gets down here to the next line to use it, core 1 or 2 or 3 may have messed with it. And so this is the problem whenever we've got a shared variable, single scalar variable shared amongst the different cores. And this is a problem that we need to fix. Now, the fix for this in OpenMP, because it's such a common problem, is very easy. It's that we need to take these shared variables here and decide when some of them should be private. Really, each core should have its own copy. So here are 2 threads running away on different cores. And at the moment, they're sharing all the variables. And that's fine for height and width and cost of paint, because if there were only 2 cores, this core gets this half of the array and this core gets this half of the array. And that's fine. Everything's good. The problem is we've got a variable like area, and there's only one of them. And so what we want to do is give each one of these threads its own private copy of area. And OpenMP makes that trivial to do because it's an important thing to do. It just has a private clause. So by adding on to our loop a private clause and specifying which variables within that loop need to be private, we can do exactly what we want to do. We can make sure that each one of the cores, each one of the threads running has its own copy of area and they don't step on each other's toes. And so we fix this problem. And so this is a common enough issue that when you look at a loop and you say, I'm going to throw a parallel 4 in front of it, you should say, are there these scalar variables, these single variables aren't arrays, so they're not being split up properly and they're being shared. And if they're written to, if it's just being read from, that's okay, because they're all reading it, that's fine. They can all read from the same place. But if they're messing with it, if they're writing it in memory, so if it's sitting here on the left-hand side of an assignment statement inside of a loop that you've made parallel, you probably need to make it private. And so this is what you do, and that solves the problem. Let's see a bunch of questions here. Let's see. Bunch of questions. Okay, the fire hose has really turned on here. Give me a moment to catch up. So this variable needs to set once. I'm not sure which variable you're referring to. So you have to know what happens if one of the threads hits an exception, such as dividing by 0. Will all the threads fail? It will throw the exception in the code, and the code will quit if you're not error handling there. So if you hit an exception like a divide by 0, yeah, the code will fail. How can I check the available number of cores on compute node? It's very platform dependent. How do you find out how many cores you have? Usually the best way is to look in one of the Linux configuration, hardware configuration files and see what it is there, but it's very platform specific. So I'll leave you to, if you Google, how do I see how many cores I have, you'll see it depends on where you are. If you're on Windows, you bring up Task Manager, will show you how many cores. So it's a little platform dependent. Let's see. If you have multi-threading enabled, should you set, and I assume I mean hyper-threading. So if you have hyper-threading enabled, and you want to use hyper-threading, then you should set it to, the number of hyper-threaded cores, or 2 times the number of physical cores would be a smart thing to do. And then you test that and see if it works. Like I said, hyper-threading isn't always a win, or else everybody would just use it all the time 100%. So you can check hyper-threading out and see if it's a win for your code, and in which case, yeah, stick with that. It's very easy, of course. You can see just setting OMP num threads and running your code, it's trivial to find out what the performance is and experiment around. We're going to do some experiments ourselves. So you shouldn't be hesitant about experimenting. Once you've written an OpenMP code, it's so easy to just experiment and see what an optimal core count is. Permission denied. You shouldn't be logging into XSEDE.org. So go back and look at our instructions on how to log in. Let's see. For the paint example, could we fix this problem by making area an array? Sure, you could, but is that really what you want to do? And first of all, so now we're messing with what the normal serial code is. So yeah, we could fix this by making area an array, but does that really make sense? Should it really be an array? Not kind of, maybe not. Certainly it's going to take more memory. Certainly it's going to mess up our serial code. It's not going to make much sense anymore. And that's kind of against our philosophy of directive. So yeah, you could do that, but let's not. Let's do it the more elegant and direct way to address the problem. Let's see what happens once it's an exception. Let's see the paint example. It can also be double. Area equals. I'm not sure what's different there. I mean, you're creating it, instantiating it in there, but inside the block it's going to live on. So no, that won't really work. What if there are many private variables? Can one continue the line? Oh yes, so line continuation with the backslash. I'll have some examples later on just to point that out. So it's not uncommon to have a lot of multiple private variables in here. You'll want to continue. If you got a big loop with 200 lines in it here, it's easily, you could easily have a dozen variables that you want to make private in a real complicated code. And so yeah, it's not uncommon to have these spill over. And the backslash character is a line continuation thing. And I think I have some examples of that later on just to make it clear, but it's just backslash. And yeah, so that is to define multiple private variables. Same related to that thing. Yes, it's just one variable comma the next. So you'll often have that be the case. And talking about getting access to variables outside the loop, we'll get onto that in just a couple of slides. Let's see. What if we want an accumulator? We'll get onto that in a couple of slides too with reduce operations. So your questions are just leading me a little bit. So at the end of parallel computing, do all the areas get added together automatically? Nope, they do not. They're at the end of the parallel region. They are each, you got a bunch of different copies of area. So that's, you're leading me into my next slides perfectly. So bear with me. What if you want to keep track of the maximum area? That's also, we do a max on area. You're leading me right into the next slides. Okay, you're all just a couple slides ahead of me. Some supercomputers have more than one hardware thread on each core. Well, core is kind of a hardware thread, but I think you mean hyperthreads, which we've been talking about. With hyperthreads, if they're turned on, then you do the multiple, you probably want to use 2 times the number of physical cores, at least to check and see if hyperthreading is helping you. Okay, so in this case right here, private fixes our problem and we're good to go. And there are some variations on private. So you might, by default, all your variables are going to be shared that you don't make private. So you can put a shared thing in there if you want to list them. Most of the time that's just for clarification purposes unless you change the default value, which probably isn't a good idea in general. So by default, everything's shared that you don't make private. Sometimes you want the value to be initialized coming in. And if you don't, so you can say first private instead, and then it will inherit the value of the variable before the code starts. So in this case right here, what if area was equal to 42 up here? Well, in our case, it wouldn't make any sense to worry about that because it gets set within the loop. But if we wanted area to have some value that inherits coming into the loop, we need to use first private. Otherwise, that won't happen by default. OpenMP won't go to the bother of initializing all the private copies because most of the time you don't. So if you're an exception, make first private. Likewise, when we're done with it, you've got a bunch of copies of area. And if we want to save one afterwards, well, if we want to use area afterwards, well, it's got to figure out which one of those areas to use because it might have 8 threads, might have 8 different areas. So it takes time and effort for it to do that. So in general, we'll just ditch it. So if it's something like a for loop and it's very clearly defined what the last value of area should be, you could say last private, and then it'll go to the trouble to find which one of those private variables corresponds to the last iteration, and it'll copy it out. So they're basically just variations that will initialize or carry the value through. Now, what is automatically private? There are a few things that are automatically private. And this slide here, on one hand, it's a little bit scary because it's got a bunch of rules here. In reality, it's very, very simple. It's just the basic things happen by default that would happen in the language if you just know Fortran or C and don't know OpenMP, that would just happen anyway. So basically, everything is going to be shared except for the things that can't possibly be shared. And a few things that can't possibly be shared would be like the loop index variable. So for example, we, of course, if we have a loop, and I'll go back to this early example right here. We have a loop index right here. We surely don't want index to be shared. The cores are splitting up the iterations. We want to make sure that core 0 is working on, index equal to 0, 1, 2, 3, at the same time that core 1 is equal to index equal to 1000, 1001, 1002, right? So index variable for a loop, it makes no sense for it to be shared. It has to be private. And so OpenMP does its best to just make that automatically happen. So it will take the outermost index in a loop and make it private just automatically, because you always want that to happen. And so it will do that. However, there's one little problem here in that in C, it's not entirely clear to the compiler what the loop indices are, because you can, in C, you can cram a lot of funky stuff into a for statement if you want. It's not generally good programming practice, but you'll see people do it. I mean, technically, I could have dozens of commands stuck in the middle of this for loop. In Fortran, life is a little bit simpler. A do loop, you're not allowed to do anything funny like that. But in C, you could do a lot of funny stuff in here. So it's not entirely clear which one is the index variable. So in C, it can figure out the outermost one, but if you have nested loops, which is very common, it can't always figure it out. So in general, in C, you should just make your loop indices private to make it easy on the compiler, and you don't have to worry about the rule. In Fortran, it can always figure out what the indices are, because Fortran loops aren't allowed to get funny looking. You're not allowed to get clever inside of here. And so in Fortran, it can figure it out. But at any rate, OpenMP will try to always make the index variables private, because they should be. And if you want to make sure that they are, especially if you're a C person, go ahead and make them all private individually. Even if it's redundant, it's okay. So we'll see some more examples of code and you'll see how that works. But there's nothing tricky here, funny going on. It's just index variables, of course, have to be private. They can't be shared, because the whole point of having different cores is they're working on different index values. Local variables in any called subroutines are going to be private too. And that's because you can have in OpenMP, so far we're talking about a very simple case of just for loops here, but you're allowed to have some threads go off into subroutines and other ones do not. You can have an if-then statement, and some of the threads go off in a different direction than others, and some of them will be in a subroutine with some variables, and other ones might not even be in that subroutine. Those variables never even come to exist. And so therefore, if you think about it, since the variables might not even exist for some threads and exist for others, they have to be private. So if you make any local variables jumping into subroutines or local variables because you're making a block of code in C, a separate block, for some threads, those variables don't even exist. And so that's why they have to be private. So basically, again, this looks like a complicated list of rules, but it's really not. And if you start using OpenMP, you'll see it. It's basically everything is shared except for the things that can't possibly be. Mostly the index variables is what you're going to care about. And so, for example, because things that are declared locally are always private, in C, one thing that's clever, and you'll see a lot of people do, is use this thing where you declare your index variable inside the for loop. You're allowed to do that in C, but any modern C since C99, you're allowed to declare any local variable that you want. If you declare the variable local inside here, then it's going to be private. So this is like what somebody was asking about this last question. Somebody was asking, what if I declare this double inside here? If I declare it inside the block, it'll be private here because it's declared inside the block. So probably that's subtle, and somebody looking at it might not pick that up. So I'd probably just declare it private separately, but you can do that. So again, in other words, this looks complicated, but it's not. It's very, very simple. Everything's shared except for things that have to be private. And if there's any doubt about it, you can make them private here or make them shared here using the directives. And if they override or if they're redundant, that's fine. So in C, though, you'll often see people do this, take advantage of the fact that if they declare the index variable inside of the for loop, then it's automatically, because of this last rule, going to be private, and they don't need to make it a separate private. But here's what I suggest you do. I suggest you just always, especially if you're a beginner at this, always make everything private. It needs to be private. Like here in C, I know these the index variables I and J, I'm going to make them private. In reality, if I'm really smart and experienced, I know that the outermost one, I, is automatically going to be private because the compiler is smart enough to see that. So I don't need to make it private, but it doesn't hurt. So I just made them private. In Fortran, for example, it always knows the loop indices because the language is a little bit more straightforward and clean. And so therefore, I never need to make these private. I never need to do my loop indices, but it doesn't hurt. So I did it. So anyway, when in doubt, make them private, make them shared explicitly. But once you do a little bit of OpenMP programming, it'll be very obvious to you what's private and what's not. By the way, the outermost loop is going to be the one that by default things get broken up over into. When we say how do things get spread out over cores, it's the outermost loop is going to be the one that's spread out over the cores, not the innermost loops. Unless you get funky later on, we'll look at there's a collapse clause that allows us to collapse loops together, and that can be useful at times for performance. If your outermost loop is really pathetically small, let's say our outermost loop goes from 1 to 3, right? Well, then it's going to be wasted if it tries to spread those iterations out and we have a machine with 28 cores or 32 cores like we have here. Like on bridges, we got a machine with, 128 cores. So if our outermost loop only goes from 0 to 3, which can happen in codes, right? Maybe it's some three-dimensional code and the outermost loop goes over your in. Anyway, if your outermost loop goes from 0 to 3 and you're running on a 128 core machine, that would be a waste. There's nowhere for it to spread out the iterations. In that case, you can tell OpenMP, let's mush these loops together here, collapse them together, which is a thing you sometimes even do in serial coding to improve performance. And so it'll do that, and you can use the collapse clause, it'll do that automatically, and then it can spread things out a little bit more. But I don't want to distract you too much with some edge cases like that, but the option's there if you need it. Okay, so let me see what questions we got here. Let's see the case, nested loops need to specify the I is private, yes. So I'm at J is private because it's the outermost one in the state. Okay, well, I answered that. C. Same case for C++. Yes, it is the same case for C++. C++ has the same ability for you to get really clever in for loops. In Visual Studio, collapse clause not work for me before. Yeah, so Visual Studio, as I mentioned, Visual Studio has a few. It's for whatever reasons, they're always lagging behind in things they support. So if you're a Visual Studio person, you want to go and pay careful attention to the implementation notes on OpenMP and see which weird things they decided to leave out, and because it's a handful of weird things. None of them are critical and you can't make do without, but some of them are annoying, and I can believe collapse clause might be one of them. I haven't run into that, but I could believe it. So if you're a Visual Studio person, go and read the OpenMP, implementation notes and see which things they decided to ignore. Okay, so we're almost there now. We got the case where we know we can recognize the data dependencies, and we got the case where we got these shared scalar variables that are that would be a problem if we didn't make private copies of them. But we got one more case, little extension of this last thing we did, which we fixed with private variables, which is what if we actually want to use those private variables after we're done inside the loop? We have an issue of which copy do we keep, especially what if it's the case even where we want to combine them together because we're looking for a maximum or we're looking for, say, a sum of those private variables. I think an example here will explain it better than I can ramble on. So let me walk through the example and then we'll see exactly what the problem is. So here's a code that finds prime numbers. And it's not the most sophisticated way to find prime numbers, but it certainly works well. It basically just counts through all the numbers from 1 to 500,000. It'll count through all the numbers and it tries to divide by smaller numbers. And if it can't divide by them, if it can divide by them, it's not prime. It's not a prime number. And it goes through it and says, if it can divide, great. And when it's all done, it says the number of prime numbers is just the number we looked through minus the number that weren't prime. So very simple brute force way of figuring out how many prime numbers there are less than 500,000. Fortran and C versions. And if we run this, we might say, okay, all the work is done in the main loop. We're just going to put this private clause in front of J here to make sure that that works right. Unfortunately, we don't need to worry about that. And then we can run this code. And if we run this code, we're going to get inconsistent results. We're going to get that dangerous thing again of, every time we run it, we might get a slightly different result. And what we're running into here is a data race. We're running into the problem that we have a scalar variable here in our code. So a non-array variable that's being accessed by all the iterations at once. And that's always a bad thing. So anytime you throw a parallel in front of a for loop, you say, do I have scalar variables in here? In our case, we certainly do. We have not primes here. It's a scalar variable. And all the threads are accessing it at once. And you might say, well, okay, it's fine though, because if thread 0 is adding to not primes and thread 4 is finding some not primes, they're just going to keep adding to it. So shouldn't we get the correct total when we're done anyway? And the answer is no. If you've got multiple threads accessing the same variable to write to it here, even though they're doing something as simple as just adding to it, there still is the possibility for this going awry. Because what happens here, and I can go into a little more detail on this next slide, is when you have a statement as simple as not primes equals not primes plus 1, it might look like, okay, thread 0 can just add 1 to this, and then thread 1 will add 1 to this, and thread 6 can add 1 to this. But in reality, when thread 0 goes to add 1 to this, what it really does, it goes out to memory and grabs the variable, and it brings it back to core 0, and then it adds 1 to it on core 0, and then it goes and sticks it back in memory. That's how it adds 1 to not primes, right? That's probably not news to any of you. However, while it's doing that, while it went out to memory and brought it back to core 0 to write to it, maybe core 1 at the same time went out to memory and grabbed it. So maybe we started out with a value of not primes equal to 100. And core 1 went out to memory and grabbed 100 and brought it back to add 1 to it. And at roughly the same time, core 3 went out and grabbed 100 to add 1 to it. So they both went out, grabbed 100, they both add 1 to it to end up with the result of 101, and then they both write it back to memory, and we end up with 101 in memory instead of 102, which is what we wanted. We wanted each core to increment it, but instead they both incremented it internally, wrote it back, and we only incremented it by 1. So in other words, the correct way to phrase this is the operation might look atomic. Atomic is a term that means this can only happen in one single step. There's no opportunity for it to be divided up into multiple pieces. But it's not really atomic because the processors do have to go out and grab it and update it and write it back. So when we've got a situation like that, we can see how our answers can become unstable and invalid. So our private clause, we might think, could fix this. If we make this variable, so first of all, we looked at our loop and said, this is bad news, even before, just from what we knew before about making private variables. We've got a scalar variable. So we want to make it private. So we can make this private, and we might think that fixes our problem. The only problem is that if we make it private, we're going to end up with, say, 8 copies of it for 8 threads. And then when we're done with the loop and it's time to print out our answer, we've got 8 different copies, subtotals basically, of the not prime numbers. We need somehow to combine them all together, add them all together. And how do we do that? Well, this is a common enough thing, common enough issue to have a private variable that needs to be combined together when it's done, that there's a term for this called a reduction. Reduce a bunch of copies together. And this applies in OpenMP, and we'll see it applies in OpenACC and MPI. So it's a common term, a common thing, and a common algorithmic concern to have in parallel computing is they need to do a reduction, where you need to take a bunch of copies and reduce them together. And there are different ways to reduce them together depending on what you're doing. In our case, we want to add them all together. We want to do a reduction of, we want to do a sum on this not prime variable. So that's what this clause is saying here. It's saying do a reduction on not primes. So it makes not primes private. It's a special kind of private, a reduction type of private. Makes it private, and it says when you're done with this variable, don't just abandon it like you would for a normal private variable. Instead, add them all together. And therefore, not primes, when it's done, will take the 8 copies that might exist, add them all together, and we'll end up with the proper value for not primes when we're done with this loop. So that's a reduction. Now, there are other reductions you might do too. The most common ones you'll find otherwise are minimums or maximums. As a matter of fact, somebody asked a question in chat, what if we have a max, we're looking for a maximum value in a loop? Well, then there's a reduction max operator as well. So there's a handful of them that are predefined in OpenMP because they're very common. But sum and minimum and maximum are the most common ones you're going to want to come across. So you'll see sum and minimum, maximum, reduction operations. So basically just think of them. There's variables that need to be private because there's a scalar copy. There's a single variable that's being accessed by and written by all the cores. Only it has to have some value after the fact. It's not just something that's temporarily being used in a loop. And so that's where reductions come in. So let me see where we are. Question-wise, does reduction set the variable to be used as private? Yes, it does. So reduction is a private variable. It's a variable. First, most people spot it and say, I need to make this a private variable because it's a scalar inside of this loop. And then they think about the particulars a little bit more and go, oh, it's not just a private variable, but it's one that needs to have a sensible value after the loop. And that's probably going to be a reduction. So that's what this is. Oh, here's the continuation line continuation somebody asked about earlier. So it's running out of space to cram it all in 2 columns on this slide. So a little backslash there, and you can make longer lines, which will happen quite often when you've got big, long loops, 200-line loop that somebody's jammed together, and you need to have a half a dozen or more private variables in it. Okay, so as I said, reduction, minimum and maximum and sum are the common ones, but there are a couple other ones stuck in there too. It's unlikely you'll use them. And the nice thing in reduction also does it initializes the variable to the sensible thing. Like if you're doing a sum, when it creates the private variable for sum, it should set it equal to 0 on all the copies, right? Because we're We want them to start out at 0. Same as if you do a max, it'll set it to the largest possible value. So it automatically does the smart thing when it starts out. So it's, again, convenient and clean. Okay, so here is our properly working prime number finding loop. It works just great. And so we'll come back later on and see how we can optimize this a little bit later on. But I hope everybody can make sense of what we've done here. We decided that we had a loop here. It does a lot of math, so we parallelized it. And then we said, okay, what needs to be private here? Well, for C, we need to make sure at least the index variables are private. And we need to make sure any scalar variables are private. And so we did that. And then we realized that this scalar variable doesn't need to be private. It also needs to be combined together when we're done. So that's a reduction. So if you kind of get these functionalities right here, you've got the core of OpenMP as it applies to a ton and tons of scientific codes where you've got just this case right here. You get big loops, do a lot of number crunching. You just parallelize the loop, and OpenMP will take care of the rest. It'll distribute all the work around for the iterations of that loop. But you need to be aware of if there's a data dependency in that loop, and you need to be aware of any variables in that loop that need to be private, which basically are going to be scalar variables that are written to in that loop. And some of those scalar variables that need to live on afterwards, you might even need to make reductions depending on if you use those scalars after the parallel region of the code. So I'll take another pause to answer questions because this is a good time to make sure you're clear with this. We're about to move on to our first real exercise here, and it's a serious one. So make sure you're clear on these foundational concepts. Is there a first reduction last? Well, no, for reductions, because they're initialized, there's no first reduction because they're initialized to these variables here. So that would be like first private means you're trying to initialize the variable. They're automatically initialized for reductions to this. They have to be. So there's no first reduction. And there's no last reduction because the reduction is coming up with the final value to have. So it's like last private's trying to figure out if you want to keep around a private variable. Well, of course you want to keep it around because that's the whole point of a reduction. Is you want it to linger around. So that's why there's no first or last reduction. I have not primes, array, and increment based on thread ID in the loop. So once again, it's similar to somebody asking previously about private variable for area. Could they make an array? I mean, yes, you could start trying to construct. Yes, you could construct your own thing like that. But why? Why would you now go and mess up your serial code to make life harder and do what OpenMP is going to do? So you could do it and it would work, but it would be ill-advised. So reduction makes it private as well as an accumulator, right? Yes, absolutely. So what variable will our print statement display now after the reduction? So after the reduction, it's going to use, there's only one, after a reduction, there's only one copy. Is there a full code? No, I don't have a full code. So if there's a print statement down here, it's going to print not primes. There is only one not primes left. After the reduction, there is only one not primes. So it's going to print the ones, primes minus n minus not primes. It's going to print, I do have the full code here, all right? Yeah. So after this print statement down here, not primes, after the reduction operation that we're going to stick on this loop, there's only one copy left of not primes down here for print to access. So there's no question which one it's going to use. Okay. I'll show an example of cancel. No, I'm not sure what cancel you're referring to. Just curious, what if one core X only died in the middle of running a prime counting algorithm being accurate because of it? Yeah, OpenMP does assume that your cores are reliable. OpenMP doesn't have some kind of fault tolerance or something built into it. So if the core dies in the middle of your code, you can assume your code's going to die. Same as a serial code if your core dies. So there's no funny fault tolerance rules or something in the background that we need to be aware of or we can take advantage of. So OpenMP is assuming that your cores are reliable. Discuss later how to make this more efficient by not dividing by non-primes. No, I will not. I will just suffice it to say this is a very, very simple-minded way to find prime numbers. It's about the worst way you could do it. There are many, many, many better ways of finding prime numbers. It's a whole subfield of number theory, which is very useful in the cryptographic field and other areas. So this is an incredibly dumb way to do this, but it's just meant to be show you how some loops work here. So we won't get fancier than this. Referring to the note at the bottom of the last slide where I say yes, there's our, so yeah, I think somewhere I say oh no, I don't know which. Oh, this right here. Oh, this cancel. Oh, so yeah, so if you're inside of a loop here and you want a core to cancel out of the loop, This is a new statement that's added in there. It's very rarely used, but that's the fact that they got away with it all the way up until OpenMP 3.2 or whatever it was. You can cancel inside of a thread of activity. This is going to be more useful with things that are really weirdly load balanced. And as a matter of fact, with the dynamic clause, I should come back to this when we talk about that dynamic clause at the end. We optimize this. We're going to take one more pass at optimizing this code right here. At the very end of the talk today, we'll come back and optimize that a little bit more, but not to make it a smarter prime number algorithm. That, like I say, is a different topic. What we are going to get into here is a real exercise. It's a much more interesting problem. And it's going to be the first hands-on exercise of the week here. It's going to be a serious one. And it's one that we're going to reuse again with MPI and OpenACC. And so I hope that's reassuring to you, because an awful lot of times when people are showing you some approach to programming or a programming language or a whenever they're trying to sell you on how great something is, they pick a problem and makes everything look just rosy, right? It performs really well, or it's really easy to write. And that's just not fair. I mean, it gives you a skewed perception of how easy something is to use. And then you go to apply it to your own problems and it's not quite as dreamy as they presented it. Well, you know, I don't want to do that here. I want to be fair. And so we're going to pick the same problem here, and we're going to use it with three very different approaches to parallel computing. We're going to use it with OpenMP, we're going to use it with our GPU computing, and we're going to use it with MPI. And so you're going to be able to compare things across the same problem. And this problem, so it's not rigged to make things look great here. And it's also a nice, simple, easy to understand problem intuitively. We're going to take a metal plate that's cold, and we're going to heat it along its edges. And we're going to heat it in a slightly fancy pattern so that we can get some interesting results. We're going to take this metal plate that starts out at 0, and we're going to heat it on its edges from 100 degrees down in this corner to 0 out here. And we're going to taper off these heating elements so it's 0 in this corner and 0 in this corner. And we might expect after we do that our final state of this plate is going to be some kind of gradient across the metal plate where it's very hot in this corner and it's very cold up here, right? That's a reasonable expectation, and that's exactly what we're going to find. So this is our problem, and we're going to use this again when we look at, it won't be our only problem, we'll do with these other things, but we're going to do this with MPI and OpenACC as well. So for those of you that are a little bit more proficient with the math methods here, I mean, basically we're solving the Laplace equation. And the Laplace equation is really just a fancy way of saying that every point in our space, in our two-dimensional space here, is the average of its four neighbors. That's all the Laplace equation tells you. But that drives a lot of physics in this world, including electrostatics and fluid flow, as well as our temperature problem right here. So it's a nice intuitive problem. You don't need to know any of this stuff. If you do, you can appreciate it. But we're going to throw some OpenMP at an existing serial code that does this and see if we can speed the code up. So our code does what's called Jacobi iteration over this grid to solve our problem for us. And this is a very, very, very simple, straightforward algorithm, but it's also nice and it converges well. It basically just says every point is the average of its four neighbors, which is kind of the physics I said that the Laplace equation is giving us. Every point's the average of its four neighbors. And again, this makes sense from the physical perspective too. If we had a number of rocks that we picked up off the ground, and one of them was very hot and one of them was very cold, and we sandwiched another rock in between them, we would expect that it would get to be lukewarm, right? It's the average of our neighbors, right? And that's exactly what happens on the metal plate, is every point's going to be the average of its four neighbors. And so our algorithm to solve for the metal plate, is going to go and take all four of our neighbors to the north, south, east, and west, add them together and divide by 4, right? That's the average of our four neighbors. And if we do that over the metal plate, we're going to get closer to the correct answer. And if we keep scanning over the metal plate over and over, we're going to converge on the correct solution. So this is Jacobi iteration, and it's very straightforward and very simple. And here's the entire science. Here's the code that implements the science of what we're doing here. Is the C version, the Fortran version. They just basically go over the rows and columns, and for every point, add it together, the four neighbors, divide by 4, and boom, we've got our new, better approximation. And if we keep doing that, we hope that we home in on the correct answer. So here's the entire kernel. This is, again, a term used a lot of times to say this is where all the actions happening in a code, both the numerical intensity as well as the science. So here's the kernel of our code. It's a while loop that says, let's keep doing this, solving this problem until the worst case temperature change. Our biggest change between one time step and the next is less than some value that we're going to call max temp error. It happens to be set equal to 1/100th of a degree in our code as it stands right now. So this basically says, keep going over and improving your estimate until no point changes from one time step to the next more than 1/100th of a degree. So this DT is the worst case change of all of our million points. It's 1,000 by 1,000 metal plate we're going to work with. So this is the worst that any of our million points have changed. And we're going to keep doing this until no point changes more than 100th of a degree. We also have one other escape condition here, just in case the user gets bored. The user also has an input statement at the beginning that says they can input the max iterations. They can say, keep trying to find an answer or stop at 1,000 iterations and let me know what it looks like. So we keep going until either we find the correct answer or until we run out of users' patience, how many iterations they allowed us to run. So this is the outer logic. It's going to keep going over and over. Here's the calculation that just finds the average of our 4 neighbors right here. And that's all well and good and straightforward. And then we find out after we calculate our new temperature, we actually, we want to have another temperature array to keep that while we determine the next time step. We need to have the last temperature stored, because if we keep going over, let me go back to our plate here. Yeah, I'll use this one right here. If we're scanning over our metal plate in a raster pattern, and we don't have a backup copy. So this goes back to, somebody asked this question about our weather model too, and said, what if we don't have we only keep one copy of the weather in memory? Well, if we're scanning over this right here, and we're going in this order, maybe we updated this point, and we kept going over our rows here, and we're down here, we updated this point, and then we're calculating this one. When we go to calculate this point right here, if we only have one copy of the array, then we're going to update it based on this updated version, and this updated version, and this not updated version, and this not updated version. We're dealing with data from 2 different time steps to do this. So you might even try to take advantage of that. That's a hint. Sometimes people try to take advantage of that and use that this might be more accurate data, but it gets to be a more complex analysis to figure out what to do. Instead, to keep life simple, you want to say, whenever we're updating this point, we're definitely taking it from the last time step. So if we're on time step 1000, these are all 4 values are from time step 999. Not this one's from the new time step, and this one's from the new time step, and this one's from 999, this one's from 900. So that's why we have a temperature and temperature last. So that when we're updating temperature, we can refer to all values from temperature last and not have a mix of old and new values. So that's temperature last down here. And that means we need to take temperature last and copy temperature to temperature last every time step. So we update our temperature and then we copy temperature to temperature last. And when we're updating our temperature, we're using temperature last to update it. So this way, our new temperature uses all values from the last time step. And then when we're done, we copy those values in the temperature last. While we're doing this, this might be a nice time also to check this DT, to check our worst point. Let's find the worst point that's changing the most from temperature to temperature last. And we'll do that in the same loop where we're copying all these values over, because it's nice and efficient and all sitting in memory right there for us to look at. So this DT right here is going to be the worst case value for temperature. So that's really our whole loop, except every once in a while, we might like to print some results out to see what's going on. We're not going to print out all million elements because that would be a mess. Instead, we'll print out a few elements here and there every 100 time steps. So this is the guts of our code. Let me see if questions are piling up here. Let's see. DT here stands for D temp, not D, that's exactly right. DT is for delta temperature, is what I think I'm in my head is delta temperature. It is steady state, so we're finding a steady state final solution. That's right. Duplicating code to avoid copying the array. Duplicating code to avoid copying the array. Not sure exactly what you're suggesting there. Let me think if something pops into my head, but at the moment I'm not getting the gist of your remark. Okay, so this is the guts of our code right here. It has a couple of supporting subroutines that initialize the metal plate to 0. That's no big deal, just sets it equal to 0. Also, we want to set those edges where the heating elements are, the proper values. And remember, on 2 of the edges are to 0, but the other 2 edges, they're kind of this increasing temperature from 0 to 100. And our print routine to print out the results, like I said, we're not going to print out all million elements, but we'll print out a little diagonal strip down in what we think is going to be the hot corner. The bottom right-hand corner is going to become hot. So we'll print out some values down there just so we can see as the time evolves that something's happening. And here indeed is the entire C code. We're going to go over the Fortran code in a second, fear not. Here's the entire C code. Don't squint at this. This is just to give you an example of that it's not an overwhelming amount of code right here, but this is the guts that we really focused on right here. And as OpenMP programmers, we have the luxury of just worrying about this part of the code. Those support routines that we covered and talked about, we can ignore them completely for now because we only care about as OpenMP programmers finding the loops where the work is done and focusing on them. We can ignore everything else. So let me go over this Fortran code. It's exactly the same structure here, so I won't belabor the point too much, but it's the same thing. We got a do loop that says while our maximum temperature change is above some level, or while the user hasn't told us you hit the limit, keep going. And I keep going just to calculate the new temperature. Every iteration, copy temperature, temperature last, and find that worst case temperature change. And once in a while, print out some results. And it has the same kind of support routines to initialize the metal plate and its heating elements. And it has a print routine to print out a little diagonal in the bottom corner. And here's the entire code. Again, not a lot of code to begin with, but we have the luxury of just focusing on where the real number crunching is going on. So exercise 1, and we'll give you about 45 minutes on this. Let's see. Yeah, we'll give ourselves till, let's say till the top of the next hour. So we'll give ourselves the top of the next hour on this. And the idea is for you to parallelize this with OpenMP, the tools that we've covered so far. There's more to OpenMP, and we're going to talk about that after this exercise. But at least with what we've covered so far, you can take a pretty good shot at speeding this code up. So you can log on to a node. If you want to grab all 32 cores, max, so it's a maximum we're going to share for the way we're sharing things today. You can grab up to 32 cores if you want. Grab 32 cores on a node by typing interact-n32, and you got 32 cores to work with. You can edit the starting code. So you've got the serial code we just looked at, either Fortran or C, sitting there in your directory. Add in some directives where you think it's going to help. One thing I just briefly alluded to earlier, but I need to emphasize a lot more, is that these compilers, most compilers are very happy to give you lots of feedback about what they think they can help in your code or what you're doing wrong and warnings and whatnot. But compiler philosophy by default is to be very quiet, to not, to not give you any extra information outside of, hey, here's an error that you have to know about. And so compilers have tons and tons of useful information that people just completely overlook. Most compilers have something very similar to minfo. As a matter of fact, minfo is the name of the flag on a lot of compilers. It is on the NVIDIA ones and the GNU ones. And so with -minfo, we can ask the compiler to tell us additional information about what's up. And in our case, what we're most interested in right now is how well it's doing with the OpenMP stuff. And so if you type, in addition to your compilation, if you type -minfo equals, I don't have an example right here, equals MP, if you add that into these compilation commands, it will be happy to tell you that, that directive was parallelized or it couldn't do anything or just ignored that directive. It gives you feedback. It doesn't hurt to have that feedback. So I suggest that you ask it for a little feedback while you're doing this stuff and see what it has to tell you. And by the way, this is a good thing to do in general whenever you're trying to optimize code or there's just so much information compilers are anxious to give you and won't unless you permit them. But in this case here, I suggest you give this flag a shot while you're working on the exercise. Not necessary, but very helpful. And then, so you want to compile and run the code. After you think you've edited in some good directives here, compile the code, make sure you turn the directives on or nothing interesting will happen. I'm sure at least one or two of you will forget to do this and you'll put the right directives in and you'll run the code and be like, it's not speeding up. What did I do wrong? Well, you've got to remember to activate the directives with -mp and make sure you set a number of threads, increasing number of threads. You can go all the way up to 32 here. Increasing numbers of threads before you run the code and run it. The code has its own timer built into it, so it'll tell you how fast it's running. And let's see what you can do here. So here's exercise 1. Go ahead, get to work. Now, I am going to, as per our normal practice in exercise sessions, I'm going to be here answering questions. Those of you that just want to put your heads down and get to work can mute me and ignore everything I have to say. We're going to be back online at the top of the hour. So in 40 minutes from now, at the top of the hour, we're going to come back and look at a solution and continue on. You can ignore me until then. Those of you that are interested, have questions, or want to hear what my answer to other people's questions, you can stay tuned in if it's not too distracting. But everybody can get to work on this exercise. I'm going to start answering questions now.
Hey, John, just a quick interjection. We don't have quite enough cores for everyone to have 32 at the same time, but we definitely don't. I see some people out there using multiple nodes right now. So if people are taking up entire nodes, they're going to take the chance away from many of their fellow students to get any work done today.
Okay, what number would you suggest? And we'll emphasize it.
I think 32 might work out if people just, use it and then log off. Just don't squat on those 32 cores, but definitely there's at least 3 or 4 people right now that have multiple nodes. You definitely could not use multiple nodes today. We just don't have enough of them.
Okay, well, yeah, I hope we don't have to resort to naming and shaming. So please take note of what Tom just said. Please, just for the sake of us all sharing this resource, and 32 cores is way more than enough for this exercise. So I was going to even say we could trim it back to, if you're using 16 cores or whatever, we'll show the point. But certainly those of you that are using whole nodes and more nodes and cores than you need to, yeah, please, you're going to keep other people from being able to do the exercises because we have a large but limited reservation for the workshop because we've got hundreds of people. So yeah, please do not squat on more than 32 cores during this exercise session, certainly. Okay, let me catch up on questions now. In Fortran, we can perform the second loop in a vectorized way. So vectors, Fortran does lots of, we'll come back to this in the advanced stuff in a little bit when we come back. Fortran does a lot of this magic for you, does a lot of OpenMP stuff for you, and does vectorization very, very well automagically. So Fortran will do a lot of vectorization stuff, especially if you use Fortran 90 style statements in your code. We'll come back to that topic in a little bit, but yes, Fortran will do a lot of this automagically. The OpenMP can't hurt and can certainly help, but Fortran can do a lot of this magically as well. So the idea here, somebody has of using 2 loops to go from temperature to alternate, basically whether temperature or temperature last, basically. You try it and you'll find out that because of the fact that you still need to check DT, which is where all the expense gets, you still need to grab DT and compare it from each one. It's pretty much the same amount of time to do that. So I could do that. It would have made the code a little bit more complicated, but the main thing is it doesn't speed the code up very much because we still have to shuffle through all the data to find the worst case DT as you go. But you can give that a shot. Plus, this is not meant to be the most optimal version of this. There are, to solve the Laplace equation, there are better ways to do this, more optimal. Meant to be the simplest example that makes sense to people that aren't comfortable with either the Laplace equation or numerical methods or whatever. So yeah, there are lots of better and more clever ways to do exactly this problem, but that's not our objective here. So export should be used before MVC. No, export, the num threads variable, it only matters at runtime. So you can compile the code 1 week and come back a week later, and at runtime is when you set export. So we happen to be doing everything here at the same time, but export only has an effect at runtime. It doesn't have any effect on compilation. OpenMP compiles a code for generic number of cores, and at runtime is when you tell it how many cores to actually grab by launching this number of threads. 32 is the number of cores. How many threads are there per core? So 32 is the number of physical cores you're asking for here in this case here. And that means that you can launch as many threads as you want, but launching more than 32 threads isn't going to do anything except waste time swapping threads. We'll even do that I do that little experiment when I show some results when we're done here with the exercise, and you can try it yourself. So the number of physical cores you're asking for is what you're grabbing with this interact command. The number of threads you launch is up to you, but it doesn't make sense to launch more threads than you have cores. So for those of you interested in optimizing this, the very first thing you'll want to do is go look at, say, a Gauss-Seidel method of solving this problem, in which case you not only don't want to use temperature last, you actually take advantage of the fact that when you're half the points being updated can actually be a slightly improved approximation. And so it's a long rabbit hole to go down to optimize solving for the Laplace equation. But ditching temperature last, having one array actually buys us a better approximation. So that's the the first step you'd take in that direction. So again, I'm trying to do a simple example here, not an efficient numerical method. How do we make sure we're not occupying multiple cores? Well, however many you ask for in Interact, as long as you're asking for that number or fewer with the number of threads at runtime, you're not going to be using multiple threads per core, right? You're in charge of how many cores you have when you launch the Interact command, and you're in charge of how many threads you're asking for with the num threads. So in this case, if I ask for 32 physical cores, I'm good all the way up to 32. I know it because that's how many cores I've been allocated here. So, well, how do you know if you're using multiple nodes? Anybody using multiple nodes probably did something very explicit. You either did Interact with a capital N for multiple nodes, you asked for more than 128 cores, or you launched multiple sessions from login nodes. You have multiple login sessions. So if you're not doing it by accident. Anybody using multiple nodes is not following instructions.
Actually, John, I'm not so sure about that at the moment. It looks like maybe something odd is going on that's allowing some jobs to span nodes. So I need to look into this, but it's behavior that I did not expect.
Jobs shouldn't span nodes unless it asks for more than 128 cores.
I know.
Okay. Okay. Well, then maybe there's some innocent, maybe we're slandering people out there. Okay.
I think we might be at the moment. I'm engaging with the lead sysadmin right now to take a look at this.
Okay. Well, as per Tom's last note there, don't bother yourselves trying to figure out what's up. As long as you did this, you did the right thing. As long as you did Interact-N32, you did the right thing. It's up to us to figure out if something is giving you more than you asked for. So as long as you did this, don't worry about it. And if you didn't do this, then, well, quit what you're doing and do this. The minfo flag, you add that at compilation, you can just stick that right in here after the -np if you want to get that -info. And then when it compiles, it'll spit out that additional information for you. So if you person looking for an exercises directory, well, that happen when you run the setup script, it'll copy over the exercises directory into your home directory. So make sure you did, as per the intro slides, go back and make sure you did that setup script. And that'll copy the exercise directory over. You know, in speed demonstrations, you have examples of precision demonstrations. Define precision for me. That can mean a lot of different things. I'll be glad to talk about it, but you need to tell me what you mean by precision. And we're mostly interested in speeding up existing codes, which will keep the same precision. But if you mean you want to speed things up so you can have finer grids, you know, in other words, that's what's called weak scaling. We'll talk about that later on in the week with MPI, where usually that's more of an issue, but you have to let me know what you mean by exactly by precision. If you don't specify OMP num threads, the default number will vary from one platform to the next. I think on bridges, it defaults to one thread. But Slurm sometimes absolutely sets it equal to the number of available cores it has by default. So don't want to rely on it. Set OMP num threads manually yourself always. Different environments have different policies. In OpenMP, if one thread finishes the loop earlier than others, we'll be rating the rest of the core. So you are a little bit ahead of us. We talk about, that's a distinct possibility, is that one core can get done with its allocated work earlier than others, in which case by default it sits around and twiddles its thumb so the other cores can catch up. And that might be acceptable to you, or you might look at that as wasteful. And so we'll see, we can affect that later on. We have some control over that. We can change the scheduling of how that happens. And we'll talk about that later. How to check results? Well, easiest answer for you, it gets a little bit ahead of it. I'm assuming people are more concerned about the speed up than verifying the solution, but later on we'll be more concerned about the solution when we have more ways to go wrong. In which case, the easiest way is if your code's converging in the same number of time steps as the serial code, which is 3,372. When you run the serial code, I think it takes like 3,372 time steps to converge. So if your code's converging in the same number of time steps, you're probably doing the right thing. To find multiple privates at the same time, yeah, the private clause, and you just can stick as many variables in there as you want, separated by commas. You do a full operation within a reduction parameter. No, so reduction in OpenMP is just limited to the ones that I showed you right there in that table. That's it. That's all you can do. We'll find out some other parallel thing. Like MPI, you can create your own reduction operations. With OpenMP, you're stuck with the reductions that are available, which in most cases, and certainly in the one we've got here, is sufficient. So we haven't, one of the early inquiries here of how long it's taking to run is your OpenMP working? Well, you know how long it takes to run serially, right? Or that's easy enough to try, right? You run the serial code and see how long it takes. And it's not 53 seconds, it's less. And so then as you're using OpenMP, you would expect that you want it to scale, you want it to run faster. So you're using OpenMP with 4 threads, you hope it runs roughly 4 times faster than the old serial code. So start with the serial code, use that as your basic time, and then work your way from there to find your success based on the serial code's performance. And some of you that are already seeing some results on different thread counts are, I will present a table of my results, which yours should look fairly similar to when we talk about the solutions. But in general, you should expect to see a pretty steady improvement in performance as you get towards the number of cores that you're actually asked for. So you should expect it to scale somewhat, but not perfectly. I'm not going to spoil it for everybody and give specific answers yet. Sorry, I don't want to spoil it for people who are still plugging away. So your results, if you're speeding things up, you're on the right track. And the best you should hope for, right, is to speed things up by 32 times, but maybe that's unreasonable or not. But I don't want to give away numbers just yet. It would be a spoiler. You should not need the OpenMP header for the directive-based approach that we're doing. So if you think you're missing the OpenMP header, you're using some things that we haven't addressed yet. That's one of the nice things about the directives are compiler extensions. They're not a library. They don't need header files or anything like that. That's another nice thing about the directive-based approach. Variations in runtime. Yeah, with all of us sharing these nodes right now, in particular, if Tom says we're really pushing it on scheduling, there's probably some variability in timing. So doesn't hurt to run a couple of times before you get too confident about a particular answer. I'll show you the timings that I ran on a real quiet machine. I had nobody else. I wasn't sharing the machine with as many people as we are right now. There may be a little bit of variation in your timings, which is expected and shouldn't alarm you too much. Variation of 2, though, that's a lot. So I'm surprised you're seeing that, but we'll see what people come up with. We said the number of threads inside the program. Yes, there are ways to manage the threads more explicitly. We'll get on to that, but I didn't want to overwhelm people with options, so we'll stick with the most basic one for the moment. Timing is always, what timers to use is always a question in codes, right? Because the most portable ones are usually terrible resolution, and the highest resolution ones are sometimes not portable. So it's don't worry too much about any given timer implementation you come across. One of the things I'll point out to you later, it's nice that OpenMP and MPI have built-in high-resolution timers that you can use if you're sure that your codes are going to be OpenMP or MPI codes. Compiling and running is a serial code equivalent to compiling with OpenMP, but running with OMP num threads equal num1. It's very close. So you should expect with one thread, it's similar to serial performance. The difference is when it does compile for OpenMP, it does use some different features and switches and optimizations. So they're not going to be exactly the same, but it's generally going to be in the same ballpark. But it's not exactly the same. It does use some different, optimizations with the compiler. You do not want to nest OpenMP for and loops like this. It's no, so that's your abstract thinking is correct. Yes, so that's what would happen, but in reality, you can't do that. So you can't have with for loops launching for loops inside of them. If you want to do things like that, we're going to talk about that with tasks and more dynamic job launching in a second. But no, so don't try to do for loops, parallel loops inside of parallel loops, starting parallel loops. That's not a sensible thing to do in OpenMP. There are ways to dynamically launch threads inside of threads, but we'll get to that later. Don't do that with for loops. Sounds like a couple of you might be experiencing some lag in the editors. I'm sorry to hear that. That shouldn't be the case. Bridges should be able to handle hundreds of login sessions concurrently just fine. I'm going to just add one more data point to the mix myself and try it. So everything on the login nodes, everything seems to be spiffy to me, but depends on what node I landed on and everything else. You may be on some other node, but OpenMP can do while loops. You just got to ask if you're doing the right thing in those loops. We'll come back to those options later. But There's a big difference between a capital N and a lowercase n with interact. Capital N is asking for nodes. You don't want to ask for nodes. You want to ask for lowercase n. That's cores. Make sure you're using lowercase n. Use capital N, it'll ask for multiple nodes, and that's where people are hogging the resources, and there's no use for that right now. I'm going to step away for just a couple of minutes here, so I'm not far. I will be back in just a moment. So if somebody wondering about why the code can still work when you use so you should look at Laplace solvers, and you'll see that using half new, half unupdated things is actually a reasonable and maybe even more optimal way to go. It's a different topic. That Newman book that I referred to earlier has an excellent discussion on that topic. So if you're interested, but I don't want to distract us too much with a particular algorithm. Let's see. My pound sign. Yeah, your color highlighting on your editor I can't speak to. So, but the pound sign applies to the pragma, applies to the whole line. So it's just your editor's syntax highlighting is doing its thing. If you're using the -m info flag, then that's pretty much the most that you want to get at this point in time to tell you what's up, and it should tell you what's going on. Several people are mentioning it's OMP.h. You shouldn't be needing that unless if you're using directives. You only need that if you're using the library OpenMP commands, which we haven't jumped into yet. I'll talk about later, but definitely don't need yet. No header files are needed for directives. That's like a nice benefit of directives. There's no linking or libraries. It's just built into the compiler entirely. There is no data dependency in these loops here, so that's why you can get a correct answer. We can talk about that a little bit more when we go into the solution, but there isn't data dependency. I should say is not, to be clear. Yes, temperature and temperature last make it very clear, right? You're not, yes, there's no data dependency there. Let's see. Okay, so I'm caught up. I'm going to give you your last 5 minutes in peace to finish the exercise, and then we'll come back and talk about solutions and any more questions that should show up. Okay, we're not back yet, but I want to pick off a few more questions here. The alternative block syntax in C, it's just regular C, so there's nothing, there's no extension or anything about this. In regular C, anytime you put braces around some code, it makes a block, and that can be useful to make local variables or whatever. So if you had a piece of code, and it doesn't really apply to our sample right here. The blocks that you need to work with are kind of already exist. So I don't want to mislead anybody here and think it's necessary. But anytime you want to make a block of code in C, as long as you throw a couple braces around it, that just became a block of code in the event that you want your directives to apply to some particular lines or subset of lines. So that's just regular C, but it shouldn't be necessary for what we're doing just yet. So. How do the cores need to know they need to communicate with others on the boundaries? At the moment, they don't need to be aware of that at all. The cores right now are running entirely free. They're just grabbing data from last temperature, right? They don't care what the other cores are doing. So there's no need for them to explicitly communicate. As long as the other cores updated last temperature and the last pass through the loop, they've got all the data that they need. So it's another reason we're using temperature and last temperature here. It makes it very clear what you're doing in the current time step and where you're gathering your data from the last time step. So I hope that made sense, but when you look at a solution, maybe you'll make more. in general with OpenMP, the cores are treated as by default as being similar in computational ability. So it divides up our for loops here, equally. But we'll see we have some other scheduling alternatives. We could decide that there's vastly different speed in the cores or amounts of work to be done, and we can change that. But by default right now, we're going with the simplest case, which is almost universally true, which is the cores are equally powerful. And if you spread the same number of iterations amongst the cores, that's good load balancing, which is the term we're really after here. The parallel code can run even with one thread. It shouldn't be a ton faster, but can run faster than the serial code just because the parallel code -MP brings along some other optimization flags. So I'll talk about it briefly, but if you use the -03 flag, which is the real optimization flag for the serial code, then it should run even faster still. I didn't want to get into a lot of compiler optimizations for serial code because it's not the theme of the workshop and it's very platform and compiler dependent. But that's why we're not going to get too concerned with things speeding up or slowing down a little bit serially. Our goal is to speed things up, 10 times or 30 times or 1,000 times before we're done here. But yes, we're not using any of the optimization flags that we would normally use on just the serial code to compile it. So if you really want a fair comparison, we should start with the serial code compiled with -03, and that'll right away speed everything up by a factor of like 8. And that should be our starting point. But I don't want to. We're not here to learn a whole lot about the NVIDIA compiler. Okay, we'll come back. We're going to look at a solution. Oh, we're already we're on solution time. So let's jump into the solution here. We'll answer some of these questions as we go. Okay, so exercise session is officially done. Let us look at a solution here. And cursor, here we go. So here's solution, the C solution. We'll go over a Fortran solution as well. So here's a solution, my C solution. Yours probably look fairly similar to this. And so all you needed to do is add, first thing you do, look at the code and go, okay, where's all the work being done? We've got 2 big for loops. So that's the first thing you do when you want to, parallelize again, HPC code with OpenMP. You go in, where's all the work being done? We've got 2 big for loops. I want to make them parallel. So I want to throw MP parallel in front of these 2 loops. Okay, so far so good. Then I want to look at these loops and say, does anything need to be private here? Well, the loop indices should always be private. So I made I and J private. Now, technically, it could figure out the first one, I, and I didn't need to make that private, blah, 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 because it's only parallelizing out a loop. But I'm going to make them both private. So I and J are private. And first loop's great, and we'll speed up. And if I just ran just with that, I'd find out I got some speed up right there. But I also have a second loop that I want to do a parallel for in front of. And I do the same thing there. I look at it and say I and J, the loop indices should be private. But I've also got a scalar variable. I've got a non-array variable in here, dt. So I need to make it private as well. But not only do I need to make it private, but after we're done with this loop, it's used. It's used in a very important way up here in the while statement. So I definitely need to make sure that dt retains its sensible value when we're done. And what is dt doing? Well, it's finding the maximum value here for all these dt's. So I want to do a reduction of the max type. So I do a max reduction right here. And that makes it private, makes it a max reduction. So when it's done, it will collect all, if it's running on 32 cores, it'll collect all 32 copies and find out which one is the maximum. And that's the DT that will live on for the while loop to evaluate. So this is my solution right here in C. Here's my Fortran solution. It's pretty much the exact same thing. I said I want to make these 2 loops parallel. So I did look at the first loop. Is there anything in here I need to make private? No, in Fortran, I never need to worry about the loop indices, so I just didn't worry about it. So I made that parallel. And the next loop here, I said I want to make it parallel too, but once again, I have a scalar here, this dt. I need to make it private, but not only does it need to be private, it needs to live on to be used up here. So I need to do a max reduction on dt. So I do that. And if I do that, I find that my code runs a good bit faster here. So here's what I got. I got all the way from 2 to 128 threads I tried here because I grabbed some more nodes. I'm glad you didn't. Don't hog cores. Excuse me, not nodes, don't hog cores, but I did because I was doing this, last week. So I grabbed all the way up to 128 cores, and I found starting out with a serial code that ran on my quiet node in 20 seconds or so. That it sped up pretty nicely on 2 cores, on 4 cores. I got some pretty nice speed ups right here, all the way up to 128 cores. Did it speed up 120 times? No. As a matter of fact, once I got past 64 cores, it actually cost me a little bit. It slowed it down. But I got nice scaling all the way up to 64 cores, up to about 30 times. Okay, so on one hand, I can right away say, this is a big victory. I just made my code run 30 times faster with a couple of lines of directives, which as an experienced OpenMP programmer took me, maybe 5 minutes to do. So with a minimal amount of work that wasn't disruptive to my code, I sped it up by a factor of 30. And that can be transformative. Again, something that used to take a data run now takes less than an hour. I can do over my lunch break. So that's a big win. But let's see about the scalability where, it's not perfect. I'm not running 64 times faster. As a matter of fact, I can see here pretty much right around 16 cores, it started to taper off some. And again, this was on a quiet node. I wasn't sharing with anybody else earlier. So this is about ideal conditions. I can't blame this on other people. Some of you today, we're all crammed on these nodes and sharing, doing this exercise at exactly the same time. So pretty much the worst case. The exercises we do later on will be a lot more code editing, a lot less running. So we won't all be running at exactly the same time like we are here. But you might have been interfering with each other today. So you might have had a little bit worse performance. But still, even on a quiet machine, I didn't scale much past 32 nodes. It became kind of a pointless to scale past. 64 nodes, I'm saying nodes because I'm thinking about people using nodes. 32 cores became kind of pointless to scale past. 64 cores became pretty much a waste, and 128 cores was even counterproductive. And that is because of probably the number one bottleneck, not probably, certainly the number one bottleneck you'll run into with OpenMP codes is that memory bandwidth becomes a limitation. All the cores accessing memory at the same time, that becomes a bottleneck. They're all trying to get to that same set of chips sitting there on the motherboard, and at some point the contention for those chips becomes a bottleneck. And that's the most likely, with a well-written code, that's the most likely problem to run into. With a poorly written code, there's all kinds of things that can go wrong. But one of the things that you're actually happy to see is that you did such a good job with your OpenMP code that you're hitting the memory bandwidth limit. And that's what we're doing here. We hit the memory bandwidth limit, but we hit it by running 30 times faster. So that's a big win. We on one single node of a machine, on a single motherboard, on your laptop or whatever, on a single device, we got a code to run 30 times faster. So that's a big win. But we did run into eventually that memory bandwidth issue. And then once we ran with even more cores, which even went downhill at that point. So, okay, let me see what kind of questions we have here, because I want to make sure everybody understands this solution. Gonna back up a lot here. The questions are streaming in, so bear with me. I don't want to skip anybody. Okay, let's start with how OpenMP is overcoming the data dependencies. So that's one thing. So there is no data dependency here. Let's look at our code here. Temperature, any iteration of temperature is completely drawing values from temperature last. So temperature, at location 100, 100, and temperature at location 100 and 101 are completely reading from temperature last. They don't care about each other at all. So these iterations, every iteration of this is completely independent from every other iteration. So any values of I and j you pick don't depend on any other values of I and j to get their results, because they're all working out of this last time step array, temperature last array, I should say. So temperature last prevents any even thinking about concerns of any data dependencies. So, but I can see where, it's pops to mind. There's a dependence between these iterations because the points on the metal plate are next to each other or something, and we're scanning across the metal plate. Yes, but remember, you're drawing all of it from the last time step that you did. Okay. This shows OpenMP can be tricky. It's really easy to miss something like this. I guess that's more or less a subjective kind of thing, but to me, there's no possibility of a data dependency here when I look at this, because I see temperature depends on something that's not being set in this, written to in this loop at all. So to me, it's immediately obvious this isn't being changed anywhere in these. So we go through however many iterations we go through of this loop, this never gets changed. So how could there be a data dependency is the way I see it. So this doesn't seem to be subtle kind of thing to me. I mean, this is why compilers can spot these patterns, and compilers will start to tell you if it thinks there's a data dependency on something you're trying to vectorize or use OpenMP on. And tomorrow we'll see with OpenACC, because it's a newer standard, it assumes the compilers can always spot the data dependencies. OpenACC will never allow you to create a data dependency condition because it's a newer kind of technology. But at any rate, it's just a pattern. And looking at the pattern here, temperature is not dependent. One iteration of temperature is not the least bit dependent on any other iteration of these four loops of temperature. But okay, let's see. Define local variable. A local variable is a variable that's, I mean, technically, for those of you that understand your languages well and everything, a local variable is a variable on the stack that's defined only within the local context. For those of you a little bit less proficient in compiled languages, a local variable is a variable that exists only within the local region of the code, because that's where it's defined. So there are no local variables here actually that are created just within this region of code. They're all defined somewhere up above, and they all live above and below it. But we could create local variables in here. We could define a variable. We could say x equal, int x equals 2, and it just comes into existence right here in the middle of our code and would disappear after this while loop. That would be a local variable, but we don't have any of them here. Expecting more than linear speed up with thread count. No. Occasionally, you will see a super linear speed up. You'll see it with a graph like this. You'll see something that might speed up a little bit more than 2 times. You go, how is that possible? And the reason is sometimes as you break your problem up and spread it out, it can fit into caches better. And we're not going to spend a lot of time talking about caches and things, although they're pretty important from a serial performance code point of view. But if you break your problem up into smaller pieces, sometimes it can fit into cache instead of main memory. And sometimes then all of a sudden it can run even faster than 2 times. So I wouldn't be amazed if a problem this size, if on 4 cores it ran, say, 6 times faster for a given problem. It wouldn't be a complete mystery. Didn't happen here, but it does happen occasionally. Let's see what code takes. Okay, so a lot of people have comments about time, but now that we're looking at these times here, let me know if you have any mysterious questions about your own timings compared to this. Let's see. Difference between parallel private. Yeah, so there is a difference. Parallel regions are a different thing we're going to talk about in a little bit. They're a more complicated thing. So there is a difference. And so we'll get to that. How do we need? Do we need to keep the max since DT is now private? Well, you want DT is private in our solution here, but it's also, but we don't just want it to be private and then it dies at the end of this. It doesn't have any meaning. It needs to live on afterwards. So DT needs to be not just private, but a reduction variable, because that's its main purpose for living, is to let us know when to quit up here. So DT definitely needs to be a reduction, not just private. I used the collapse. Made it ran slower. It's hard to, this has a lot of parallelization in the outermost loop since it's got 1,000 iterations. So collapse isn't going to be super effective here. The overhead of it might be even a little bit more. I wouldn't think it would make it run a lot slower, but say the timings here. But yeah, collapse isn't really helpful here. Let's see. Parallelize the first. Okay, somebody parallelizes the first loop. It should speed up. It shouldn't run slower, which is even the first loop should be a speed up. Not as effective as parallelizing them both, but it should be faster. And we covered, let's see, I answered a lot of these questions by pulling up the table of solutions here. So, okay. Okay, I see a lot of timing questions. What happens if number of threads is larger number of cores? That's fine. It'll just spread. It'll just have, each core will be responsible for more than 1 thread. So it won't speed up. It might even slow down a little bit because of the overhead, but it won't break the code. It just will not be effective at speeding your code up. Is it possible that some threads go faster or slower than others? Absolutely, and we're going to get to that. We'll look at some dynamic scheduling later on to see how we can deal with that. What other compilers can you? I gave a list of compilers that work with OpenMP, pretty much all of them, and you know, any serious compiler that's not for just embedded computing or something at the beginning of the lecture. So if you want to go back and see those, they're there. I think I left off Clang, which we use a lot these days, but that's also works with OpenMP. Is there an implicit barrier after each OpenMP block? There is. We'll get to barriers in just a little bit. About hyper-threading, we have a lot of you are very upset. So hyper-threading, yes, hyper-threading. It's just like it's faking having multiple physical cores, and they work just fine. So no problem with hyper-threading. Once you get slower, if I have space between common separate values, it should not. Okay. The tricky thing about indices, well, I mean, that's why I suggest while you're getting comfortable with C, it never hurts to make everything explicitly private. Don't take advantage of any of the nifty things like, yeah, the indices are, you know, the first one's private. I mean, so when you're a beginner in OpenMP, make everything private or even shared. You can even use the shared clause if you have any questions about how things are behaving. And then as you get more experience with language, you can see why things are the way they are, and the defaults have to be the way they are. But while you're new to it, it does not hurt. Nobody will ever complain if your codes, if you make things private, nobody will ever be like, that was already private. That's fine. They just consider it better documentation. So if you have any questions, make things explicitly private or shared. Let's see. And so we'll get on to the parallel versus the OMP parallel. We'll get on to that, and they are different. Change. So OpenMP works with C++. We'll talk about that briefly at the end. OpenMP can deal with a lot of C++ constructs and everything just fine, but it's kind of an extension of what we're doing. But we'll talk about it briefly, and we can get into it more. But I don't want to take too much of a digression to it until we get to the next Q&A session, and I'll answer anybody's specific questions about C++ and after I introduce some of the basics. Okay, so let me, for the sake of keeping things moving, because we do have a lot more to cover, let's go ahead and get moving ahead. So this version also scales up. You can scale up. We have a 10,000 by 10,000 version of this that we use for a hybrid programming challenge sometimes, and it scales even nicely to more cores. That's where the memory bandwidth becomes a little bit less of an issue. It's a bigger problem, more spread out. So anyway, but before we move on, because we're about to jump into a lot of advanced OpenMP stuff. OpenMP has a lot of flexibility to it. It can do pretty much anything you can do at the lowest level with cores. But before we do that, and I expose you to all this diversity of capability, I want to make sure you take a breather and realize that with just the small number of tools that we've got right now, we were able to do great things. We were able to take and speed up a code 30 times with a couple directives. And it's a real code, right? Again, it's not some rigged code. We're going to use this code for GPU computing or use it for MPI. So it's not just something picked to make OpenMP look good. We're able to speed this code up 30 times with a couple directives. It didn't take long to do. So you've assimilated, if you understand this, you've assimilated the most important tools that you're likely to use in scientific computing with OpenMP. Now we're going to go on and do all kinds of other things that you may or may not ever find useful. But as long as you don't let that confuse you and think, oh my God, there's so much I didn't learn and didn't absorb. If you've absorbed what we did so far, you are in good shape. You know how to use the most important part of OpenMP, and you should be able to deploy that knowledge in a lot of different cases. So take that breather and recognize that before we dive into some other stuff. Okay, if you've done that, made that mental note, now let's dive into all the other many ways that you can use OpenMP and the many things it can do. So far we've done this approach right here. We take, and do for for loops, we spin off a lot of cores to get to work and work on our for loops. I said this is the most important thing in HPC type computing, scientific computing. But there's another approach we can take where we take all the threads and we have to manage them ourselves along the way explicitly. And so when we get to for loops, we have to do things a little bit differently. And in between, where we had the old serial code before, we need to pay a lot more attention to what our cores are doing, because they want to do stuff all the time. So you might say, why do we use this more complex approach? Well, For one thing, it means there's never any wasted cores. Here, where the cores aren't doing anything, you could think of that as wasted time. We're going to have all the cores are always going to be aggressively trying to do something, but it means we need to be on top of it more. And so this is where a parallel region comes in. So somebody just mentioned in the chat that they saw the parallel clause as a separate thing. And that's because the parallel region is how we take this approach to using OpenMP. We can start a parallel region, all the cores start working, all of them just start trying to run the code. We can do a lot of things within that region to try to tame things and control them. So a lot of these clauses we've seen, we can say which variables are private or first private or whatever. But the basic idea is that it's up to us within this region to control things. Within this region, we control the number of threads that are active. We can use what we've done so far, the OpenMP num threads, but we can also set things explicitly. So we have a lot finer control, but it's going to come with more complexity. Now, the one exception to this is one thing I do want to point out. Somebody asked this earlier about Fortran, is that Fortran, since Fortran 90, which is 30 years ago now, so I hope all of you are using at least Fortran 90 type constructs. Since Fortran 90, with its nice array constructs in it, which allows to do array operations, OpenMP just magically will do things. All you need to do is say this is a work sharing region, and then all these array operations. So for those of you that are Fortran people, these are array operations. All these array operations will work in parallel because it's just implicitly data parallel. So it's a huge bonus for anybody using Fortran 90 array operations. And again, I hope you all are not even for parallel computing, because it makes the code so much cleaner. I hate to see array operations written in some Fortran 77 style anymore. I mean, that's insanely obsolete. So that's a little Fortran thing, but that's all we'll say about that. Okay, let's look at a way we can work with different threads of code going through different sections of our code doing different things. So we can have our threads going off and doing, well, different chunks of work. And one way we can do that is with sections. So we have a master thread, and then we come to a piece of code where we have a bunch of sections, and different threads can work on different sections. Here's what this looks like. So here's sections, and again, we've got the C and the Fortran examples. We say here's a parallel region, and so the threads are, so if we've got, say, 20 cores going to work here, we've got 20 cores are going to jump into this, and each core is going to grab an available section of code to work on. And so one core might grab this section right here and do this for loop by itself. Another core might grab this one. Another core could be down here asking for input or something. The cores are, each thread is going to do one section and only one section. If there are more threads than sections, the extra threads will just come down here and wait. If there are more sections than there are threads available, then the threads will go back and pick off all the sections until they get there. But this is a way to have your code have each, under your control, each thread doing one chunk of work or another. They don't have to be for loops. Okay, the most flexible way, though, and the most advanced, and many people would say the most sophisticated way to deal with varying types of work in OpenMP is to use tasks. Tasks are an incredibly powerful and flexible way to work with different chunks and pieces of work. And the way it works is your master thread, that gets the parallel region, can launch, or your threads within a parallel region can launch a bunch of different chunks of work. We'll see exactly what this means with code. And those chunks of work then can get picked off by all the threads that are available, and they will pick those pieces of work off and then move on. So let's look at an example of this right here with, we'll pick something that's contrived. Again, I'm going to sum an array. I'm going to take an array and just add all the elements together. And this is a really simple-minded thing to do, but it'll be a good way for me to show you how these tasks work. So actually, the smartest way to do this would be just here. Here's the easy OpenMP version we already know how to do. We take this for loop and we just say, hey, we want a reduction on this total right here. Boom, this is done. So this is actually the simplest way to do this. But let's do this with tasks. Let's assume that we inherited a clever serial code that did this recursively. And the reason I'm going to pick this example is because there are lots and lots of recursive codes out there in the world. In particular, anything having to do with graphs. So any of you out there that work with graphs, which is increasingly important, it's always been an important part of computer algorithms. But if you work with graphs, a lot of, when you go through a graph, you're going to breadth first search through a graph. It's a recursive type of algorithm. So when you've got recursive algorithms out there, they work very well with OpenMP. Multi-core, multi-threaded versions of OpenMP, much, much simpler to do than the old pthreads libraries and whatnot that people would use. So I'm going to do a recursive sum of this array. So again, it's not because I think this is the simplest way to sum an array. This is the simplest way to sum an array in OpenMP. But instead, we're going to assume somebody handed me this recursive code. And the way it works to sum an array is it takes the array and it breaks it into two pieces. And it says, okay, if the sum the array then of those, do the same recursive call on those two halves of the array. So it keeps calling itself on halves of the array until it breaks it up into a bunch of individual lines, and then it sums those together. So let me say this again, so everybody's kind of clear with this. So if we have an array that's, say, 16 elements long, and we want to sum those 16 elements, we could say, okay, take the array and break it into the first 8 elements and the last 8 elements. Now call the sum routine again. Now that sum routine is going to get the array and say, break this into its first 4 elements and its last 4 elements, and then do that until it gets down to 1 element. So this is the recursive way we could sum an array. Again, it's this dumb way to sum an array, but it's, if we were doing a graph search or something, it would be the smart way to do it. Okay, we can do this in OpenMP with this task capability. So with tasks, we said we go into a parallel region, and in the parallel region, we have all of our threads working away, and then we have tasks that launch a separate chunk of work for each one of the threads to pick off. So the first task says sum the first half of the array, and the next task says sum the second half of the array, and this launches a new chunk of work. So the tasks are launching new tasks. This is the idea. Each task is launching new tasks. So OpenMP keeps track of all of these chunks of work that are being spun off. And however many threads are available when these tasks get spun off, it starts working on. And it will keep working on these, and it will wait to get the final answer until the subtasks, the children that spun off, actually complete their work. So it's going to spin off a bunch of tasks. So with our 16-element array, it's going to spin off a couple tasks for the 8-element arrays. Those are going to spin off a couple for the 4. And they're going to keep spinning off tasks until you get down to the last single elements. And then they're finally going to start collecting, reducing all their values down together. So this is how tasks work. And this is how we could sum an array with tasks. We can do this. Here's the entire program to do it. And we can be a little bit smarter if we want. We could say, for example, so here's the serial sum. Here's the parallel sum. This one's a little bit smarter and says if the size is smaller than some cutoff, it's silly to break it up into separate tasks. So maybe if it's less than 16 elements, we just sum them all together instead of going all the way down to the last element. So this might be a recursive way to sum an array that's a little bit more efficient and sensible. So tasks in OpenMP are just really nice abstraction whenever you've got something. It's not a for loop. Instead, it's chunks of work that you want to spit off and have a thread eventually, no matter how many threads you have, eventually a thread will get to it. If you've got lots of threads, they can jump right on it. If you've got lots more tasks than threads, it might take a while to get there, but they can do it. Here's another very, very popular recursive algorithm. People like when they're teaching recursion to use Fibonacci number generator. So here's Fibonacci number generator. If you know what that is, if you don't, I won't bore you with it. I mean, it's basically just summing the sequence of two numbers or the sum of the last two in the sequence. And this spits each one of those off recursively as a task, and it sums Fibonacci numbers. So tasks are really not just clever, but a really powerful way to deal with an unknown amount of work that spits off more unknown amounts of work. And tasks have a lot of flexibility to them. And we're not diving into all the details here. I just want to introduce you to the capability. So if you're writing one of these algorithms and you find yourself, most likely a graph algorithm, but lots of other things too, you find yourself wanting these capabilities, you're aware they exist. And so tasks have the ability to wait for their children, to wait for groups of tasks, to merge them together. So you have a lot of ability to manage tasks. As a matter of fact, with newer versions of OpenMP, they're not that new anymore, so all the OpenMP support it, you can even define dependencies in tasks. So let's say we have a piece of code that looks like this, where we have a result, and then we have a long computation that uses this variable X, and we have a short computation that uses variable Y, and then we want the result to be added to this variable X that came out of this long computation. And here we want the result to then add the variable Y before we print the answer out. So we got a lot of things going on here, chunks of work. And so if we actually graph this out by hand, we can see that, say, calculation 3 here. So 3 down here, it needs the result and it needs the X. So it really is depending on T1 to get the result, and it's depending on T1 to get X and T0 to get the result. So there's a dependency. T4 down here, this line here, it needs the result. So it needs what comes out of T3, and it also needs Y, which came out of T2. So we can see that the results of one calculation depend on other calculations here. And the neat thing is with OpenMP, we can define these dependencies like this. And this is neat because it means we can take this code down. When it runs on a bunch of different threads, the threads will make sure they'll try to jump ahead and aggressively do things, but they won't be able to jump ahead if they're waiting for a dependency from some earlier chunk of work to get done. They will wait. We can be sure that this computation being done here by one of the threads, T2, that it will be completed before T4 starts, because T4 says it's got an input and dependency from res. It's also an output dependency. Something else depends on its output down here. So these input and output dependencies are a nice way to make sure that no matter how many threads are working on this, they can't get ahead and out of order. The work will be completed in sequence. And this, again, when you start constructing complicated bunches of work, this is a really, really nifty thing for the compiler to automatically schedule for you to take care of all of this. So this is very powerful capability. As a matter of fact, you can even have mutual exclude. You can have a mutex type dependencies here, where we can say, for example, that these two right here, only one at a time can be done before we move on to task 5 here. They're mutually exclusive dependencies. So it's got a lot of capability here to define the sequence that things should happen in. They've extended this even further with OpenMP 5. So this is one of the more recent additions here, although it's implemented almost everywhere now, where you can even have an array that keeps track of dependencies. So you might have, say, 1,000 different results that you're working on, and you can stick those results. You can have an array that flags and says which ones are done, which results are completed, and which ones are not. And so that's a pretty nifty bookkeeping capability to just have OpenMP take care of for you. So tasks are very powerful. Again, we're giving them very short shrift right here. We're not diving into the details nearly enough for how powerful they are. But I just want to introduce you to the concept so that if you find yourself writing an algorithm that does have this kind of dynamic work spawning capability, work farming, however you want to think of it, that you recognize OpenMP is very good at managing and scheduling that stuff for you. So it's not only gives you the multiple threads to work with, it can take care of all that dependency analysis and scheduling. So tasks are very powerful, and people that use them are incredibly grateful to have these capabilities. Okay, now let's see. We have a bunch of questions here. Let's see. An example of web scraping for multiple websites and processing data. Now, I do not have that particular example. There are plenty of those out there, but I do not have that. We get to the point where spawning more threads do not help. This is about Amdahl's law. Well, we'll talk about Amdahl's law later, but partly about Amdahl's law, mostly about memory contention and bottlenecking. So the main reason why you'll find your performance doesn't scale perfectly with a well-written OpenMP code is the memory contention. You know, you have enough threads all going aggressively using memory, which is what you want. They're grabbing results out of memory and sticking them back. At some point, they're going to use the memory bandwidth available up on your computing platform. And that's typically where you hit the bottleneck. That's where we did in our code, for example. And that's, you know, it's a good thing and it's a bad thing. I mean, it's bad that hardware isn't magical and doesn't, you know, have infinite bandwidth, but it's good that you've now got your code, so it's using the hardware to its maximum capability. And very often that will be its maximum memory bandwidth. Okay, so parallel regions. We also have the ability to even control in a more finer degree our for loops within parallel regions. And so this is an example of making life a lot more complicated for ourselves, but it shows you how you can get into lower level details. So most of you will not want to do this, but I'll show you the capability if you really want to optimize things silly, or for some reason you think, well, I'd like to use OpenMP, but I don't want to handicap myself. I want to make sure that I can still aggressively optimize things and get good efficiency. Well, OpenMP is glad to turn all the details over to you. So here's how this happens with our kind of even simplified version of our current Laplace code. So we have a parallel region. At the beginning of a parallel region, all of the threads are going to launch and start trying to work. So they're all trying to do work right here amongst these two for loops. Instead, before we had the parallel for. So this is not. Notice that this is not a parallel for. This is just a for. This is an OMP for. It's not an OMP parallel for. The parallel starts outside of the loop. That means within here, it's up to us to manage everything explicitly. We got to worry about the details. So now instead of a parallel for, we just have an OMP for. And that means that all the threads will work on this loop together cooperatively. Okay, that doesn't sound any different from what we did before. The difference is when they are done here, any threads that finish early will race ahead to the next loop. They won't wait here. They won't synchronize. Our old parallel for loops were nice and simple and managed themselves in a very civilized fashion. Now we're going to find ourselves with the cores all eager to race ahead. And so they're going to start racing ahead and doing this second loop here. And this is the way we do this with Fortran. And this would actually cause a problem, because what will happen is if we did this, we're going to find our output is a mess. And because what's going to happen is all the threads are going to race ahead, and they're all going to be working on the output down here. In addition, some of them might start trying to do the output before these threads up here are even finished doing the calculation. And so we have a case right here where threads are racing ahead because we wanted to set them all free and not waste any time with idle threads, because we were going to optimize our code to the utmost degree. And so we did it, but we started introducing problems. Now OpenMP has the ability to deal with these problems. So now we can start finding we have directives to start to control things. Like, for example, on the output where we're writing things, where we had all the threads before which start writing simultaneously, now we can say we only want the master thread. So when we have a bunch of threads, there's always a master thread. So we only want the master thread to write output. And so we can do this. And so this says only one thread's allowed to write output. Okay, that solves one of our problems. But our other problem is that some of the threads are racing ahead already doing the next for loop. So they're out of sync. Some of them are at the whole time step, maybe ahead of others. Now we need to introduce barriers. And the barrier command says all the threads need to wait here before any of them are allowed to continue. So if some threads race ahead, they have to wait for the slowest thread to catch up. And so the barrier is a concept. We'll come back to an MPI because it's very important there. But you'll see in parallel computing in general, barriers show up a lot. But the main thing about the barrier here is that it starts to synchronize the for loop so that some of the threads can't race ahead. Okay, if this all sounds very confusing and error prone, well, you're not wrong. This is the price you pay to manage things at the lowest level. On the other hand, if you're confident you know what you're doing, I can make sure that I'm not wasting any more cores than absolutely necessary. All my threads are going to be 100% as busy as they can be. So this is, I'm just showing you here, OpenMP allows you in parallel regions to manage each thread and what it's up to every step of the way. But it comes with a lot of responsibility. So as a matter of fact, we can now start to manage threads by their individual numbers. Some of the people doing the exercises were probably straying into this territory since they were looking for the OpenMP header file. If you start to use, instead of directives with OpenMP, you can actually use library calls. OpenMP also has a library version. So the directives are nifty in that they're built into the compiler and you can turn them on and off. But instead, if you're willing to commit to writing it as a dedicated multi-core code, you can start to stick in library versions, function calls, basically in the middle of your code. These aren't directives. This is an actual function call right here. So in the middle of my code, I can stick in some function calls. Now I do need to include the header file to do this. And now my code no longer can I switch it off and it goes back to being a boring serial code. This is 100% full-time multi-threaded code. But if I do that, I can now use library versions instead of directives, and I can manage threads by thread number explicitly. And so I can say only thread 0 gets to print the results out, and the other threads won't be allowed to do that. So there's a lot of capability to manage things at a low level here. We can allow only single threads to go through regions of codes. We can have a region of code that only one thread is allowed in at a time. We can have lots of low-level synchronization and coordination details. I'm not diving into these here. I'll be glad to talk with any of you that are interested about these individual commands. And if you have algorithms that you think might be particularly asynchronous, where they might apply, I'd be glad to talk with you about those. But I just want to expose you to the capability. So if at any point in time you get convinced that the drawback to OpenMP is because of this high-level, wonderful OpenMP parallel for loop that we've used so far, that it doesn't have low-level capabilities and there's not optimizations that you can do and it's not flexible, well, remember this part of the talk. So remember, oh no, OpenMP can go as low level as I want it to go, and I can control threads, instruction by instruction if I want to. As a matter of fact, you can now use hints to control. Well, we'll get onto a few slides later about how you can have regions where things are locked. Well, we'll get into the slides. So it was a forward reference. I'll skip for now. The library routines, as I said, are available for almost all the directives. So if you want to write a code, instead of using directives, you want to write it like it's an actual function-based calls. There are library versions of all the directives and all their capabilities. So feel free. But again, don't be intimidated by this. These are all available as kind of directives too. And you can mix and match them with directives if you want. So there's a lot going on there. But again, I want to emphasize, if this stuff is starting to seem tricky, including the stuff we've yet to talk about, remember, the parallel for and the parallel do loops bought us a ton. We got a lot done with some very simple directives. So don't let the real flexibility and power of some of the lower level OpenMP stuff confuse you and make you think you have to master that before you can do useful stuff. So let me see if I have some extra things here. Programming, yes, can't compile automatically figure out and decide how to parallelize tasks. So the dream of compilers figuring out how to do all of this stuff has been around since before my career. Somebody's always promising an automagical parallelizing compiler. And the answer is no. There's always one a couple of years away, and that's been true for 40 years. Literally, you go back 40 years and find somebody saying their parallelizing compiler is almost good enough. The answer, at the end of the day, algorithms are complex and different enough from each other. It takes a human being's intelligence to come in and enhance what the compiler can do. Compilers have gotten much better at doing the boring stuff. That's why OpenMP, like say the OpenMP Parallel 4 does all the scheduling and spreading stuff out. So it does all the boring stuff, but you as a human being are still necessary to know when data dependencies and data races can potentially creep into your code. So, and that's been the case for a long time. But somebody's always promising automagical parallelization. It's always right around the corner. Somebody's got a sketchy product they're selling, but not a reality. Let's see. A loop to create extra tasks or any issue that arises when too many tasks are initiated. Well, sure, you can. So with tasks, if you're not careful, you can have spin off way too many tasks, and then you just have a bunch of overhead in your system, and you've got millions of tasks going on. The threads it's just tracking them as it takes all the effort. And that is why tasks also have the ability to manage things. You can manage the depth of tasks. You'll notice that there's a task final. You can say, I don't want to go any further than this. So you can manage that to make sure that things don't spin off too many tasks if you want. But yeah, it would be, there are times when the tasks start to be nothing but overhead. The barrier goes ahead of the iter statement in the print progress part. So in the print progress, the barrier could go ahead of the print, or it could go after the print, as long as, in either case, as long as the print's a master or a single region. Let's see. Yeah, but believe me, if there was a way to automate this, I'm not up here talking because I just like to hear the sound of my voice. If there was a compiler flag called parallel, that would be it. That would be our workshop. Hey, yeah, use that parallel flag and you're done. Everything's parallel. And believe me, there wouldn't be the need for this workshop, and there wouldn't be thousands of parallel programmers out there working on algorithms and whatnot to make things parallel. It requires a human level of intelligence and understanding of algorithms. And that is the facts. And by the end of this week, you'll have that intelligence, and you'll probably have a better understanding of the kind of diversity of algorithms that make it hard for a compiler to do. And you'll be able to use all the intelligence compilers do have, but you'll be able to supplement it with your human knowledge where it's necessary. Okay. One of the things that's very common in certainly in threaded programming, but parallel programming in general. So I'll introduce the way you can implement this particular bit of functionality in OpenMP or locks. A lot of times you have resources, data structures in particular, where it's necessary that only one thread at a time be able to access that data structure. So I'll give an example on the next slide of, say, a USB drive that you plug in, and you only want one thread to be able to write to the file, so not overwriting the file. But it's very common to have in a code have let's say I'll pick something more mundane. Let's say we're just got a generic database. We're a bank and we got a database and we got all these customer records. And you might know that to update one of the customer records, you only want one thread at a time in any given record. You don't want multiple threads. Or here, I'll give you here's an even simpler example, is a linked list. If you've got a linked list where one item is linked to the next in a linked list, any thread can go in and link a new item in that list. It's perfectly safe. But if you have two threads at the same time messing around with a linked list, they can very easily unlink the list and destroy it, because one goes in and unlinks the list to insert its item, and the next one goes in and it unlinks that to insert its item. Now all of a sudden we've got a dangling node in that list that's not connected to anything, and because they're both messing around in the same data structure. So if you got a linked list, you want to make sure that that list is accessible to all the threads. They all might need to update it, but only one at a time is allowed to access that. So you want to lock the list, and you might have hundreds of data structures floating around that you want to lock. And indeed, since we have a lot of people asking Python questions here, this is the main reason Python has limitation on multi-threading. As part of the Python interpreter is the global interpreter lock, the GIL. You'll see this if you're a Python person. You've come across this countless times whenever they talk about performance or what things are compatible. The interpreter has a lot of data structures going on. It's tracking all kinds of things. It's whenever it executes a line of Python code, it actually goes and builds some separate byte code, and it's doing all these things. Well, because it's got all these data structures floating around, you can't have multiple threads messing with stuff at the same time. So in Python, they did the easiest thing back in the early 90s when Python was being developed, is they went and they said, okay, let's have a lock, a global lock that locks down pretty much everything the interpreter does. So there's one lock when we start accessing things. So this is locked, only one thread's allowed to access stuff. Well, having that global lock was a nice, easy solution, but it's very coarse. It means that you can't have multiple threads because you got one lock for everything instead of one lock for smaller things. So it's a limitation of Python. Well, if you're building a code today and you want it to be multi-threaded, instead you want to apply locks to all these individual data structures. So only one thread at a time can mess with the data structure, but while this one's locked, the other ones are available. So you don't want a global lock, you want a bunch of local little locks. Each data structure is locked down. So this linked list is being accessed by thread 0, so nobody else can mess with it. But this linked list over here is free, and a thread can go ahead and mess with that. But when it messes with that, it needs to lock it. So locks are very, very common across parallel computing and certainly in threaded computing. Here's how locks can be implemented in OpenMP in a very straightforward and classic way. So OpenMP gives the ability to define a lock, and then we can take a section of code and we can set a lock around that section of code. In our case, we're gonna make this little section of code here that just spits out a for loop here that says a thread is in this region, and it spits out I'm in this region 5 times. So thread 2 is in this region, and it gets the printout 5 times, and then it moves on, and some other thread can lock the region. So what we have here for this section of code, and this could be in the real world something that accesses a data structure, we put a lock around it, and then the first thread to get down here sets the lock. In this case, it happened to be thread 2. Could be different some other time we run it. So thread 2 got here first, set the lock, got the printout, hey, I'm thread 2, I'm here. And then it unsets the lock and moves on. That means the next thread that's waiting in line, which happened to be thread 0, can set the lock. And then it gets into this region. So locks around different resources and data structures are very, very common, and OpenMP makes it very easy to implement locks. Now, implementing locks, though, takes a little bit more thought than just throwing them around everything, because you can end up with deadlocks. Here's an example where somebody thought they were doing the right thing. They were locking, they had a USB drive, and they were writing a file to it. And they said, okay, when I use the USB drive, I want to lock out the other threads. So I'm going to lock the USB drive. And then I've got this file that I'm copying to the USB drive. I'm going to lock that file. Then I'm going to copy it. Then I'm going to unlock the file and unlock the USB drive. I did the right thing, right? What could go wrong? Well, what if somebody else over here on thread B says, okay, I want to put a file on this USB drive. Well, they lock the file, and then they want to lock the drive. Only problem is, if once in a while these things happen at the same time, and it might only be once in a great while, it might only be once in a blue moon, but once in a while, what might happen is that thread A locks the drive, thread B locks the file. Okay, then thread A wants to lock the file. Well, guess what? It doesn't have the lock for the file. Thread B does. Okay, well, eventually thread B will get done with that lock, right? Well, except for the fact that thread B is trying to lock the drive, and thread A has locked the drive. So what happens is they get stuck here forever, and we have a deadlock. So multi-threaded programming has this reputation for being dangerous, because people can introduce deadlocks. And indeed you can. So if you start doing things like this and start locking data structures, you need to be careful that you don't introduce the possibility for deadlocks. And so this is the kind of thing OpenMP allows us to manage, but we need to be responsible for. So again, it's more advanced stuff. But it's a lot better than doing this stuff with P threads at the lower level, which is how people used to do all of this stuff. Okay, here's an example of some really fancy stuff that OpenMP does with the same kind of idea, that we've got data structures that need to be accessed in memory. And this is a common thing. Again, a lot of applications. You got a bunch of data structures in memory and you're accessing them. And this has become so important that modern computers now have something called transactional memory, which means that they can keep track of, you can be accessing a bunch of stuff in memory, and they can keep track of it speculatively, so that in case some thread of execution doesn't actually get triggered, in case it was speculative execution, it was just something that might be done, and the thread started working on it in case it might be done, but it turns out that it didn't need to be done. Speculative execution on computers, that's what it's all about, right? Is that it does stuff in advance instead of sitting around waiting, hoping that it might be done. And then later on, it finds out, I mean, a few hundred cycles later, it might find out that the code took a different branch and didn't do this. And it needs to unroll all the stuff it did in memory. Well, this is actually something in software would be very difficult to do efficiently. In hardware now, transactional memory actually allows the hardware to back out a bunch of references, things that it already did with registers and even memory, and back them all out, undo them. So it's kind of the undo at the machine language level, if you want to think of it that way. And it's really powerful and quite nifty. OpenMP allows us to actually interface with this kind of hardware at a low level. This is really amazing stuff. It basically allows us to say, we can suggest to the hardware and to the compiler, which works with the hardware ultimately, that this data structure is, say, very low contention. So it's unlikely to have a lot of threads messing around with it and for us to need to back out, to use transactional memory to back out of that contention. Or we could say it's very likely this is a really intense shared data structure and lots of things are using it. And so therefore we can expect that there are going to be transactions that need to be backed out. And so OpenMP has a lot of capability to use what is extremely sophisticated, leading edge, bleeding edge, but effective hardware like transactional memory, just by giving hints to data structures. Likewise, today, you find that memory has a lot of hierarchies to it. Memory in a modern computer is not just some RAM chips and here's your CPU. Instead, if we look at, here's a pretty regular chip. It comes from a supercomputer, so you might think it's fancy, but actually it's quite regular chip right here. And it basically just says, I hope that that landscaper going by hasn't made me unintelligible here. Here's a fairly regular computer chip. Like I said, it says supercomputer here, but it's a pretty regular computer chip. It's got a couple of processors, each one with 8 cores. So this is a pretty normal node, I should say. Node, I should say chip, normal node. There's a modern computer node. That modern computer node, you might think, oh, it's got 64 gigabytes of RAM on the board. That's all there is to it. There's just some memory chips and there's a couple processors. In reality, this is the kind of connection between these things. It turns out that each processor is actually connected to 32 gigabytes of the RAM, a little bit closer than the other processor. So this processor can access all this RAM, but it actually has to go through this processor. Each one of these cores in here can access any of the memory, but it also has its own local cache, which greatly helps in speeding up computations, but also means data sitting in this local cache is a lot easier to access than data sitting here, certainly data sitting here. So for you as a programmer, all this is 64 gigabytes of memory. But from the hardware perspective, data can certainly sometimes be a lot closer to one processor than to another processor. And this is the reality of modern computers. They're all like this. There's a big hierarchy of stuff. The registers are closer to the CPU, and then there are caches, usually a couple at least, sometimes 3. And then there's your RAM, but the RAM might be in separate chunks, which are non-uniform. NUMA, you might have heard that term, non-uniform memory access, means some of the memory is closer than others. And this all looks just like 64 gigabytes of memory, but there's vastly, it takes a cycle to access this. It usually takes 2 or 3 cycles to access the closest cache here, maybe a dozen for further caches. Usually takes 100+ cycles to access this. But this is all just 64 gigabytes of RAM as far as a typical programmer is concerned. And then we can even add on stuff on top of this, the high bandwidth memory like accelerators have and accelerators themselves and non-volatile memory. So you have this really complicated bunch of memory that as a generic programmer, you just think of as 64 gigabytes of RAM. Well, the neat thing with, and by the way, this can be accessed from loops in your code, which might be running in threads, which might be running in processes, which might be on a certain core or on a certain processor, right? So the code that's actually trying to access this byte over here might be running here, could be running here. So it's very complicated what's actually going on at the hardware level. It's neat that OpenMP gives us a nice high-level way to let the compiler help us with this. It can allow us to suggest affinities, basically to say that, you know what, if I'm accessing an array A that's sitting here in memory, maybe it would be nice if you kept me here on this core, this thread state here for accessing stuff that's in memory here, or even that fits into cache here. So the ability to start to say what things should be grouped together is really very powerful and effective. It can make a big difference. And in the past, it was all a lot of low-level, horribly low-level non-portable stuff where you try to pin processes and everything else. It's very, very non-portable, very platform-specific. Here with OpenMP, we have a standard way now that you can in your code start to suggest how to deal with this. So this basically is saying, hey, here's a task, it's a generic OpenMP task, but it's got some dependencies in it. So this is just normal OpenMP, but here's the newer stuff, which is nifty. We can say this thing right here has an affinity for this data structure A. So as a matter of fact, we can see here it's used to compute. B is B is computed by using A. So it'd be nice if A could be close to this B data structure. And likewise down here, there's an affinity for A. Here we're updating B. Well, B is computed using A. So it'd be nice if these two could kind of stay close together in memory. And that's what we'll suggest to the compiler, and the compiler will do its best to work with the operating system and the hardware to make sure that A and B maybe are both located here to start with. And if they start moving into cache, that they stay close together. So this kind of low-level stuff, OpenMP makes addressable in a very portable way. So this is really powerful stuff. and really fancy and really leading edge, but very easy to use in OpenMP. How hard is it to add this into your code? Is to say, yes, A and B are, used together. Simple thing to add in, all of a sudden takes care of a lot of terrible low-level stuff. And for those of you that have ever dealt with this in the past, you know that thread placement and keeping threads in the right place and pinning threads has always been a pain in the butt to try to help with some of these issues. Well, this makes it very much easier in OpenMP. You can start now to try to pin threads and to allocate memory in a way that's tied to the threads. As a matter of fact, here is a very nice high-level way to start to specify some of the characteristics of your data structure. For example, I mentioned you might have non-volatile memory in a modern computer. SSDs basically might be treated as main memory. Well, that has very high latency, but it might be fine because you only need to fetch that data at the beginning of your run. So it's okay to have data that has high latency. You don't want to, on the other hand, put small data structures you're accessing all the time in there. That would be bad. So we might instead want that on the low latency, or you might want high bandwidth. Anyway, the point is that we can start to specify some of the characteristics of our data and where it should live at a very high level, and let the compiler and let OpenMP worry about the terribly low level stuff. So landscapers going by again. Hopefully they're gone for the day. I'm sorry if that's if you're picking up all that noise. Okay, so OpenMP has lots of other things to deal with low-level stuff like vectorization. Somebody asked a question about vectorization earlier. I said, okay, well, OpenMP does have some concern about vectorization. Vectorization is this low-level hardware stuff that likes to work on a strip of memory at once. It can load a whole strip of memory in and work on that all at once. Say you want to multiply something by 10. You can grab a whole 100 elements of that, load it into the hardware at once, multiply it by 10, and write it back out at one as a single instruction. Not a single cycle, but a single instruction, which is a lot more efficient. And so that vectorization stuff used to be very much pragmas and directives to compilers. OpenMP allows you to start to specify at a higher level in a portable way that vectors can be worked on at once. It basically says there's no data dependency on, in this case here, we've got 18 elements in a row. I can tell the compiler it can strip off at once and work on. There's no data dependency for up to 18 elements. So I'm glossing over this stuff very quickly. I don't expect you to absorb it in detail. I just want to introduce you to the idea that it's there for those of you that have struggled with vectorization in the past. So this SIMD thing, SIMD is the way of telling it it can vectorize things. This SIMD stuff can also be applied to routines. It can say, go ahead and apply this routine over an entire vector of data. The routine won't introduce any dependencies, element by element. So, and the last thing, I have a reminder, a step too far, is we can even deal with flushing stuff in and out of caches at the very lowest level if we want. If we want to even break all the rules I've talked about so far about when you can write shared variables, you can have multiple threads. I said we can't have multiple threads writing to the same variable. We need to put some kind of lock around them or make them private, right? Well, maybe you think that your algorithm is so finely controlled by you that you can do that. You can have multiple threads writing. Well, you can do that in OpenMP. If you want to break all the rules, OpenMP allows you to do it. You can control at the lowest level. This is getting really fancy, but it just, again, make sure you're aware of the fact that you can get as low level as you want with OpenMP. So, but to take a big step back and clear our heads, I've been wandering very, very far into complexity here and low level stuff. And we found an awful lot of power out here on the simple end of OpenMP. So we don't need to be diving into this stuff if we don't need to. We can stay in the simple, less error-prone world of the parallel for and the parallel do, or we can go over here and start managing things bit by bit in memory. And if we're expert operating system, multi-threaded programmers. So OpenMP gives you the ability to work anywhere you want on the spectrum. And for an awful lot of you, this is going to be where you're going to want to work because it's less error prone, it's easy, and gives you huge gains. We've had huge gains without having to do much. Okay, the last thing we'll do here is a quick exercise that we don't have time for, but I thought we might run out of time today. Like I said, I anticipated this, and we are at the top of the hour. So I'll tell you what we're going to do is we will save this exercise for the start of tomorrow. And it's a simple hands-on exercise. We'll save it till, we'll do this exercise right now, real quickly. That way you can work on it if you want over the evening. This is our prime number finder here. And several of you have raised the issue of what happens if cores finish faster than other cores or have more or less work to do. And I said that can easily happen. Our prime number example is a very good one. Our prime number example, you can imagine that a large prime number is going to go through a lot of iterations on this loop because it's never going to stop until it finds out, oh, you're actually prime. On the other hand, the number, say 8, is going to be a very short trip, right? Oh, you divide by 2, we're done, right? or the number 256. It's a very short trip. You divide by 2, we're done, right? So all the even numbers are very small amount of work. A huge prime number, so the amount of work distributed here is going to be very uneven. And so this is where our for loops, just breaking them up by iterations, might not be the best load balanced way to go. Instead, we might want to do something a little bit different. And we find out that OpenMP has some very friendly scheduling clauses. So this is an example where we can do optimization that is still high level, not error prone, not tricky, but will get us some wins. So can you take the prime number problem and using these scheduling options, which I'll show you right here, can you make it run better? And the options we have are static, that divides the iterations evenly. That's kind of what we've been assuming is the default. Dynamic, it says as each thread finishes, it gets another one. That's going to have more overhead. It's got to do more thinking about it, but maybe that's fair when we've got things that are very different in amount of work that's being done. But we can set chunk sizes for that too. We also have got it. It can go with smaller chunks as it gets smaller. So if you can take and play around very easily without a lot of effort by trying these different scheduling clauses on the end of our loops, and can you get a better performance thing? So here's a very simple exercise. That's why it's only a 10-minute exercise, but I'll leave you with this that you can do. Give it a shot and see if you can speed up our prime number solver, which is sitting there for you. So we're going to quit on this exercise. Now, we'll come back tomorrow, and I know tomorrow is supposed to be OpenACC day, but we need about, I guess about 15 minutes for OpenMP to wrap up OpenMP. And it will dovetail perfectly into OpenACC. So I don't regret that at all. So we're out of time. Now, what I will do is I will answer any pending questions we have here before we call it a day. But those of you that scheduled to leave right now, you can leave unless you want to hear the answer to questions. You can work on this exercise. Otherwise, we'll see you back here tomorrow at the beginning, the scheduled start time. So 11 o'clock Eastern time, whatever time zone you're in, we're going to get started promptly. We'll finish up our OpenMP, and it will lead us right into OpenACC. And tomorrow's got a lot, it's a lot less crowded of a day, so we'll make up this time, no problem. But I will answer questions and back up and see how many questions I have. Hopefully not that many before we call it a day. So, but otherwise, those of you that want to leave and don't care about questions, thank you for your time today, and we'll see you tomorrow. Let's see. Okay, we have a lot, but I'll try to get through them quickly here. Let's see. We have a resolving deadlocks and parallel computing environment is an important task. I'll let that continue for. Yes, resolving deadlocks is an important part of serious parallel programming. Fortunately, for a lot of you in HPC, since we're working with for loops and everything, those problems don't creep into for loops. They do creep into more complex things like, operating systems and whatnot. Laplace code, you found yours running slower. Well, without looking at your code, I can't say, but you can compare it to our solutions and see what differs there. And you could also try, it'll be a little bit quieter if you want to run some tests, now that everybody's not working away all at once. It'll be a little bit quieter. You might see less variability in the timings too. Let's see, it's all the same thing. It goes slower. Let's see. Something like changing the code if I use a different compiler. If you use different compilers, the switches are different, well, as you see right here. So for GNU, it's -F OpenMP is the switch. You shouldn't get a segmentation fault if the code is take our solutions, for example, it should work just fine with the GNU Portrait. Solutions, let's see. You're all quite welcome. And okay, the rest of that was thank yous, which again, you're all very welcome. Okay, I think I've cleared the questions then. So, and we'll have more opportunity, of course, over the coming days to answer questions. So if we have to come back and revisit this material, I'm happy to do so. Otherwise, we'll see you all back here tomorrow at again, 11 o'clock in the Eastern time zone. And we're going to get off to a quick start picking up right where we're leaving off here. So thank you all. And thank you, Steve and Tom.